capacitor. So the power loop or the current, the direction in which the current is flowing follows a lateral or a horizontal path through the top switch, bottom switch, and the capacitors. Or you can have a vertical power loop where the capacitor is on the other side of the PCB, and therefore the current is sort of flowing through the height of the PCB. So if you compare this versus this, and just again remind yourself that the inductance is, let's say, proportional, loosely proportional to the area of the loop, then when I look at this, it turns out that because the lateral spacing on the board is always going to be much wider than the height of a PCB, lateral power loop in terms of inductance cannot compete with this kind of structure. Of course, the lesser the number of layers, the lesser the height here, and therefore more beneficial this approach is. But let's say if you go to even 6 layers, 8 layers, and slowly the inductance here will start increasing. Okay, the switches and the capacitors are placed on opposite sides, which is a bit of an advantage actually in some cases, because here, if I had to put a heat sink on the top side, these are all actually incidentally happen to be top side cooled devices mostly. If I had to put a heat sink on the top, these capacitors, they might interfere with that because the height I have to match and things like that. Whereas if I'm putting the capacitor on the bottom side, then I don't need to worry about this. This I can just basically just put any capacitor and any design, any sort of form factor capacitor I can select. But there is another approach, which is the recommended approach if you're just trying to look at reducing inductance, which is basically known as the return to mid layer 1. So what you do here is, it is similar in some way to the first one, wherein the switches and the capacitors are on the same side of the PCB. But if you look at from the sidewise, you will be able to see that the direction that the current is taking, and again, this is why it's important to visualize how the current is flowing. It's flowing from this switch, let's say the top switch, bottom switch. It's going to the capacitor, and then there's a sort of via here and a via here, and the via is used to transfer the current to the layer just underneath it, which, as I just discussed, is very, very close to the first layer. So the sidewise, if you look at it, the area of the loop here is much smaller. Let's say again, this overall height might be 5 to 10 times the height between these two. So you can just imagine the loop area would be much smaller here, and therefore, if I look at this structure, the loop inductance is always the lowest amongst the three. It does not depend upon how many layers of the board I'm looking at, like this one. So that's the advantage of this approach. But as we'll see, there are some issues also that can come here, which is why it's not going to be a good idea to always in all implementations go for this. And then there are some additional tricks that you can play with regards to around the device packages only. So if you look at this EPC chip scale device, the terminations are arranged in a very peculiar fashion. This is the gate and the source, and the power, drain, and source, they come in sort of an interleaved fashion where you have drain, source. This is drain, and the next odd one is drain, and the other ones are source. Okay, that's the package. So let's say you have to connect drain and source. So the very basic thing you can do is maybe put copper like this. So the current comes in from here, let's say from the drain, flows to the device and comes out to the source. Okay, but a slightly better way of achieving this, connecting the device still to the drain and the source, you still have the, let's say, the drain copper largely on this side and the source copper on this side. What you can do is you can put some, of course, this copper here, which is going into the device, but you can also have vias here, and the vias go to, if this is top layer, the vias go to mid layer 1 again, come down the, just underneath this drain tab, and then there are vias again here. So this is again, so the drain current is essentially dividing into two parts. One is directly flowing into in this direction, and then this little bit less, maybe 30% or so of the current is coming down, going through the one level low, again coming back and flowing into the drain terminal from here. Okay, and the same thing you can do with the source. So why are we doing this? The reason is because here you can see at each side, because this point and this point they're much closer, you have current flowing in opposite directions. So even in this package, in this tiny minute package, if you see, you have sort of magnetic field cancellation effect happening to a greater extent than you would have here, which means that the just the peripheral inductance of this arrangement would be higher than opposed to this. Okay, so this will give rise to even lower power loop inductance here. Of course, the challenge here is that because these pads are very tiny and the clearances are very small, so you have to make sure that your vias can be manufactured in that way. Probably it's going to be mean an expensive PCB, and of course that's not always an option. So that's the trade-off. But if you can do this, you are actually benefited in two ways. One is because it's high frequency current and inductance, of course, is reducing, but also because of magnetic field cancellation, there's a phenomenon known as proximity effect, which gives rise to resistance in high frequency conductors. Because you have magnetic field cancellation effect here, you can essentially reduce the losses in the high frequency losses arising due to proximity effect, because you reduce the magnitude of the magnetic field. So it also means that the termination resistance, the interconnection resistance of this device to the rest of the circuit is lower if you do something like this. Okay, so that's a bit of detail. What you can do is, if the best way to probably go about adopting some of these practices is there are various, because these devices are really tiny and switch really fast, their layouts are critical. So what various manufacturers do is they have open source reference designs. So this is an example reference design, and now if you want to look at specific circuits, for example, this is a reference design of a full bridge phase shifted full bridge converter. So there are 4 switches forming an H bridge, and you can look into the PCB files, the layout files which are there, and you can slowly sort of find out and reverse engineer and try to identify some interesting layout aspects, like where is the switch node, how is the switch node placed, and what is coming, and not only this, and what is coming in the first layer, what is coming in the mid layer one. Okay, all those things you can slowly, carefully find out. So let me just walk you through one such layout of the full bridge. So these are 4 switches, 1, 2, 3, 4. This is a single sort of half bridge gate driver which drives a pair of switches here and here. And these are peripheral circuits, resistors and capacitors around the gate driver. These are decoupling capacitors around the switches, these ones, and these are bulk capacitors. So and this is a 4-layer sort of board. So if you look at it very carefully now, and all these bullet points sort of describe the salient features of the layout. Essentially, what you can observe here is the DC plus, and so this is top layer and mid layer one. So we are sort of trying to again conceptually pair them together, and middle layer 2 and bottom layer we're trying to conceptually pair them together. Okay, so you can see here DC plus and DC minus, they are occurring in a pair in 1 and 2, and then again at the bottom and the third layer. The motivation here is we're trying to sort of reduce inductance and resistance of the bus bar itself. DC plus and DC minus, we're trying to keep close. We could have just done it for this 2 layers, but further we are doing this here because we're basically dividing the current, we're exploiting the fact that 2 other layers are available. So we want to reduce inductance further. Then you can see that on mid layer 1, you have this sort of cavities present. Okay, the reason being, if you notice mid layer, top layer, this is one device, this is another device. This is the interconnection between this device, which is the switch node, which is the high DVDT node. This high DVDT node and this entirety here is DC minus, is the so-called ground plane for the rest of the circuit. So if I could have just blindly put copper here, but sometimes putting copper does more harm than good. This is an example here. If you kept the ground plane underneath this switch node, then there would be large switch node to DC minus capacitor. So we have intentionally removed the copper from here. Um, the rest of the current, the power loop can flow as we'll look into in detail, but this is the first observation. And similar strategies for source plane, islands beneath the gate drive in mid layers 1 and 2. You can see here some portions are etched out. Let's look into a few more nuances as to what a simple change and how you need to carefully observe the direction of the current and what qualifies as a good layout versus a bad layout. So if you look at this is essentially a zoomed in version of the last slide only, and I'm just looking at one half bridge now. So this again, this is top layer, and on the right is a mid layer one. So that the arrow indicates the direction in which the current is expected to flow. Okay, so it goes from this is where the capacitors are present. So it goes from the capacitor to the switch node, ground, okay, and then you have this VRs here. So it comes to mid layer 1 and it goes right back here and it flows back to the capacitor. So that is the path through which the current is flowing. What I have done here in this layout is I have just removed this small piece of copper here. Let's say someone does not put the copper here, okay, because otherwise, the top layer looks exactly same. So what that does is it completely changes the layout totally, because now the current, while it will flow like this on the top layer, going from the same path from capacitor, switch node, the switch, and then it comes back to mid layer 1 through the vias. Remember, it has to go back to the source. Current flows in loops. So now, unfortunately, this pathway is not available because you have removed copper from here because of some whatever reason. And therefore, the current has to take this roundabout path and come back here, which means that the entire loop inductance is going to be much larger. So the key learning and lesson from this is you have to very carefully, and this again applies for if you're doing any sensing circuit layout and stuff, you still, same principles still apply. You must not have interruptions in the ground plane at the wrong place. So just two things we learned, right? If you put copper here, this helps because that helps you to route current in the proper direction. Whereas here we have intentionally removed the copper. If we just blindly put copper here, thinking that, oh well, what if there is an interruption in the ground plane? Well, we would end up having a higher switch node. So knowing where to put copper and where to remove it is critical, and you can have that understanding only if you clearly visualize the path of that the current is taking, and keep going back to those two fundamentals that we want to reduce the loop inductance and we want to reduce overlap. Okay, let's now delve into this a little bit deeper. I'm going to talk about some other packages now. These are we've been essentially talking about the EPC GaN, which are low voltage switches. You also have higher voltage gallium nitride devices, which can either be bottom side cooled, or I talked about the newer generation top side cooled. So let's look at bottom side cooled and what are some of the challenges and interesting. So bottom side cooled means the thermal pad is underneath, all the electrical pads are also underneath, they're facing the PCB, which means that the so-called heat extraction happens through the PCB through the action of thermal vias. Okay, now if it's a bottom switch, okay, and as I showed you in one slide, the thermal pad is essentially the source. So if it's a bottom switch, then this is not much of a concern because the source is DC minus. Okay, so you can have thermal vias going straight through. You don't care. Okay, but if it's the top switch, the source is the switch node. So you can't really afford to put thermal vias here, because then you remember, to try to reduce inductance, our preferred pathway is going around the top layer and then coming back to mid layer 1. And this is, let's say, the ground electrical potential. So if I want to bring thermal vias in this path, there's going to be a collision, there's going to be a clash. So I cannot put either I will not have to put thermal vias here, and then I can route the ground plane black for low inductance, or if that's clearly not going to be good for heat extraction. So if I put thermal vias here, I I cannot route my ground plane back here. So what I do is, as is shown in the top view now here, you of course need to put thermal vias on both devices for heat. So the current would flow like this in the top layer, and in the mid layer one, you would actually try to, you will not put copper just underneath there. You would be forced to take a detour, something similar to what I showed in the last slide, and come back here. So as you can see, this essentially results in, even though you are doing the transition from top and the mid layer one, is essentially a quasi lateral power loop. So this is not for high frequency loop inductors. One way in which you can sort of make this problem a little bit better and address this a little bit better is, if you have two decoupling capacitors, instead of putting them this left right as is shown here, you put them top down as I've shown here. So what then happens is, current would try to find one path in this direction to arrive at this capacitor, and one path in this direction to arrive at the other capacitor, and therefore the current is flown in two parallel paths, and essentially two inductances in parallel you can think of, and therefore the inductance comes down. And this is shown with numbers in this presentation, that with this geometry you can just make this small modification of moving around the capacitors by 90 degree. You can reduce the inductance from 8.8 nanohenry to 6.2 nanohenry, right? So that's good. But probably the best thing to do is if you have top cooled devices, and this means that the thermal pad is on the top of the package. That makes thermal and electrical parts decoupled. Things become much more easier. Here also you can essentially do the layout in two ways. So this is the approach 2 that we had seen before, where current is traversing in the top layer, and the return path, the capacitors are on the bottom side of the PCB. So you will have to have vias which are running through the height of the board, but there's no worries now, because the thermal, you don't have thermal vias no longer are needed, because the thermal pad is on the top. So you can have vias coming in, and in any case these are DC plus and ground vias, so that's also not much of a concern. And you have this connection between Q1 and Q2, which is a short switch node connection. Or you can do something what is similar to the mid layer one, or this third approach that we talked about. However, you must note that, then this is what I alluded to a little while earlier. If you do this, the switch node is invariably going to be close to your mid layer one return. So you would end up with high parasitic capacitance. So you might have to take a little detour and make sure that you don't have overlap, at least underneath the switch node. Okay, that is what we had sort of done here. Okay, we could have still filled it up with copper. The inductance would be low, but the parasitic capacitance would be probably not allow us to work too much. So it's that trade-off that we live with. We etch out the copper and we make sure that the current does not flow. There's no potential here. The switch node does not. The switch node does not overlap with the DC minus here. So that's the sort of trade-off you have in this circuit. And also they mentioned there's a capacitance height constant that you might run into, because everything is on one same side of the PCB. And then if you look at we will only be talking about the device, but there's also the gate drive. So what does that do especially with bottom cooled devices? With top cooled you do not have this problem. With bottom cooled, if you consider the gate drive circuit that needs to also be routed, there are other further challenges that come in. So this is the small gate drive IC, and this is the on resistance path, on path, and this is off path, and decoupling capacitors on the gate driver, and so on. So this is the layout from the top side, and I've just redrawn here with just the switch just removed, so that we can see all the nodes and stuff. So you can see here, this is the power connection, and the yellow connection here is in the mid layer one, the return connection. So you have one switch here, another switch maybe somewhere here. Current is flowing in the top layer, going through the vias, going to the mid layer one, and it's taking this yellow path and tries to go back. But you also have this gate drive circuit just sitting very close to it, because you want to reduce the inductance. And same principle, if you want to reduce the loop inductance or the gate loop inductance, you would want an island of copper in the mid layer one, just underneath where all the traces are placed. Okay. Now the problem here is that you have an island of copper here, because that's on mid layer 1. Ideally, if you remember, you wanted the current to go back, so you wanted some copper in this position also. Now that is again colliding with your requirement of having a reference plane for the gate driver. Okay, so what can you do? Well, the first option you can think of, let me not put a plane underneath the gate drive circuit. Let me just use the mid layer 1 and just do the power layout as I wish to do it, prioritizing power layout. And you can see here this trace here, which is present here but not present in this layout. This trace is the return trace. So the circuit, you basically is becoming equivalent to a lateral layout. And this would mean that you would have low power loop inductance, as I mentioned, but the gate inductances would become high. And perhaps more importantly, you have this gate drive signals are also going high and low, remember. And if you put the, let's say, especially if this is the, let's say, the high side device, then this return path is the switch node. So if you have the gate drive circuit right sitting above the switch node, that's also not good. You have capacitive coupling. So this is not a good solution at all. You should never try to do this. This does not yield, certainly not will yield good result. Okay, so a much better strategy is to do something. If you're forced to use bottom cooled device, is to push the gate drive circuit on the other side of the board. So use the top side, the top layer and the mid layer 1, as is shown here, to do the power loop layout. Put the gate drive circuit on the bottom layer, all the devices on the bottom layer, and have its return plane on mid layer 2. Okay, so, and again, because mid layer 2 is much far away from mid layer 1, you will not have overlap, and the capacitance effects are not to be worried about. And because this is in mid layer 2 and this is in mid layer 1, they are not also colliding. Okay, so in many ways this is much better. The power loop in the is good because it's happening between a pair of layers. The gate loop is also quite good because it's happening between the bottom pair of layers, and there is very little intervening capacitance. I'll quickly skip through this because I think I'm not doing very good in terms of time. How much time do I have more, Sriraj? Can you hear me, Sriraj? Hello?
Hello, can you hear me?
Yeah.
Yeah. So another 5 minutes to 10 minutes.
Okay. Please give me 10 minutes because I have a lot of stuff to cover. So I was not very careful of the time. Okay, so maybe I'll skip this part. This is essentially detailing of the same thing that I've talked about. This is for silicon carbide module. This is slightly different, but essentially the same principles apply. This is an example of a bad layout. Okay, so this is essentially, if you look at the terminals, it's a half bridge module. As I said, it's a half bridge, not a discrete device. You will have DC plus, DC minus, and AC node. So this is a bad way of doing it because there's several undesirable things happening here. First, the DC link capacitors are far away. You can see the blue here is DC plus, the black here is DC minus, so it's much far away. The AC node here is overlapping with your DC plus, so that's again a terrible red flag. And you have asymmetric connection of the DC plus and DC minus. As opposed to that, if you just again turn around the module by 90 degree, that's the best way to do it. You will see that the AC is on one side, the DC plus and DC minus is on the other side, and you can nicely interleave them. You should, on the PCB, wherever you're doing this, again, you should have the blue plane and the the black plane on adjacent layers. So that really helps you to reduce the busbar inductance, and you can put capacitors here. There's a slightly even better version of this, where you don't just put the capacitors like this, but you alternate the directions of the capacitors, the plus and minus and adjacent capacitors, you alternate. The reason you do that is that helps to, sort of, in this structure, all the, black nodes are sort of, you can see the arrows, length of the black arrows, which are the current directions going into the DC minus, and the yellow are the current directions going into the DC plus. All the black arrows are sort of longer than the yellow arrows, which means that the paths are sort of asymmetric in some sense. So there's less optimum magnetic flux cancellation on the DC plus and DC minus happening here, as opposed to here, we sort of, because we have an even number of capacitors, if you place them in a sort of staggered, alternate fashion, you'll see that one yellow arrow would probably be the same as one small short black arrow, and sort of this in summary, this means that you have better magnetic field cancellation happening. So just small changes like this also can provide incremental benefits. So I'll quickly skip gate drive PCB layout. I have talked about it, since I really want to talk about this aspect, which is double pulse test. You are probably aware of that. This is a way to doing a switching characterization of the device. We talked about E on and E off. Supposing I don't want to load the converter at any power, but I still want to go up to requisite voltage and current, if the switch is going to work, and I want to find out for a given gate resistance, how does the switching waveform look like? How good is my layout? How much is my E on and E off? So we do this double pulse test. First pulse is for generating the current, and the second pulse is to bring it down. And then we really, at the start of the second pulse, is where we are doing the hard switching at the relevant voltage and current. And this is where we look at for turn-on switching characterization. So this is the way to do it now. But I want to just talk about a few things about, because how do you measure switching loss? You would probe the switch current, and you would of course probe the drain voltage. You would probably want to see how is my gate drive circuit looking? Is gate drive oscillatory? Is it staying within acceptable limits? Is it not hitting the lower limit or the upper limit threshold? All those things you want to look at, right, before you start putting into the converter. So certain things which you have to be aware of about, especially when you're talking about very high frequency converter design, is what is the scope or the probe that you need. Sometimes we're talking about 1 gigahertz scopes and 5 megahertz scopes. Well, of course they're needed, but there is a very systematic way of finding out what is the bandwidth of the scope and the probe that you need is discussed here. So if you have an oscilloscope connected to a probe, it's like two cascaded systems, and the bandwidth of such a system is given by this expression here. Essentially, it's it's lower than either of the bandwidth. So let's say you have a 1 gigahertz oscilloscope coupled with a 200 megahertz probe, differential voltage probe. Then the bandwidth of the system would be 196 megahertz. So you can clearly see here, it doesn't matter whether you have an excellent oscilloscope if you're coupling it with a low bandwidth probe. The system bandwidth or the measurement bandwidth that you have of the measuring system is about 196 megahertz. The size number you can find out from this expression. Why is it important? Once you know the system bandwidth, that tells you this expression. Roughly from control system, we know that settling time is inversely proportional to bandwidth. But this empirical expression sort of tells you what is the rise time of a waveform that you can observe based on the system bandwidth that you're operating with. Okay, so if you put these numbers here, you can see that you can observe something like an 8.10 nanosecond, okay, waveform. So if you are trying to see something which is 5 nanosecond, then this is not going to be good enough. You need to, let's say, increase the bandwidth of your probe. So that's one thing for you to be aware of. If you're observing things on the oscilloscope, you need to make sure that you have the right probe bandwidth. You don't need a 1 gigahertz probe necessarily, but it's going to be defined by what are your expected rise and fall times, okay, or what do you see on the oscilloscope screen. And again, same thing is just looking at what device you're using and what is your expected inductance in the loop. You can find out what is the expected frequency of oscillation, and the measurement system's bandwidth needs to be at least 10 times or 20 times higher than that. That's another way of looking at things. If you know the device and if you have some idea of what kind of loop inductance you are working with, you find out the resonant frequency, and your measurement system bandwidth needs to be at least 10 times higher. Other things is when you are measuring the waveforms, you need to make sure that the fidelity of the waveforms are good, which means you should be really seeing a true version of reality and not a distorted version. So if you have long leads like this, which have also maybe high input capacitance, then that impacts your measurement. Some specialized adapters are also placed, are also available. So this is also great because you can just physically attach the probe in very close proximity with the PCB. It's safe way of doing experiments also, and it's also very low inductance insertion measurement. So this kind of probe grounding adapters are also wherever applicable, mostly for low voltage passive probes you can do this, and some differential probes also, I guess. Okay, the next thing I want to talk about is about common mode noise and how that you should be aware of that. So, what is common mode? It's specifically illustrated for measurement of high side device gate voltage waveform. Let's say we want to. So, we normally use differential voltage probe here because it's high voltage. And this is measuring ground voltage with this gate voltage with respect to reference potential, same for the switch node. And if there is large parasitic capacitance, there is current, that potential in itself is not flat, and there could be oscillations or noise voltages. So what happens when we use a differential probe is, apart from the true differential component of the voltage, this so-called common voltage, or the voltage at the reference plane with respect to which all the voltages have been measured, that voltage also gets comes into my measurement in the form of what is known as common mode voltage. And this comes because of the fact that the any differential probe, just like in some sense like an op amp, has some common mode gain. If you look at this, is just very similar to an op amp. If you open the data sheet of the differential probe, there's a CMRR chart, and they tell you that what particular frequency, what is the ratio of the common mode gain and the differential mode gain. You want this to be, of course, as low as possible. So as you can see that as the frequency is going up, CMRR value is increasing, which means you will have more common mode component coming into your measurement. That is not good, because now you are seeing a waveform, differential waveform, but that's polluted with noise, which actually is not there in your true circuit. So how do you first find out whether how much of common mode noise is present? It's a simple experiment that you can do. You can put both probes of both the leads of your differential probe or the switch node. Okay, so now at any point, basically, switch node is 1 point, and then what that does is it kills the differential component, and you'll still see something on the oscilloscope screen, and that is purely common mode noise. And if that is, let's say, of order of a few volts or so, then you know that all your noise, that's like a noise floor of your measurement. If that is there, then you know that all your measurements, you need to be be careful about it. So it's not that the differential waveform has that, but your measurement is going to read that. If you don't see appreciable common mode noise, it's much below the thresholds of gate voltage and stuff, you don't need to worry. But if you do see, then what you need to do is, if you want a clearer view, you need to go to probes which have better CMRR ratings. These are the so-called extremely expensive optically isolated voltage probes. And you can see here one experimental result where you use standard differential probes and you use these optical probes. You can see this, this sort of noise coming, and you might be worried that what is happening here, but this is just an artifact of measurement and nothing else. So again, if you had done the measurement with found out the common mode, you would probably see this even when you put both these leads here. So that's something that you need to be aware of. And that's right at the end, I want to talk about a couple of aspects on current measurement also. So current is typically measured in, especially in high power. This is not true for gallium nitride devices, which are very tiny, and measuring current is a little tricky. So people have different approaches there. Just probably use shunt resistors and so on, or other some research is going on really. But for high power circuits like silicon carbide, discrete devices, or GaN discrete devices or modules, people either use what is known as a current viewing resistor or a Rogowski probe. So the Rogowski probe, you can just have this loop and you can put in, but you must be aware that the Rogowski is essentially not as accurate. Its bandwidth is not as good as that of a CVR, and therefore if you're trying to do switching loss characterization very accurately and for very high switching speeds and so on, you will miss out on losses, and therefore the Rogowski will give you an optimistic version of your switching losses. So that is something to be um, you must keep in mind. The other similar thing or error that can creep into your measurement is with respect to alignment of the voltage and the current probes. All the probes have intrinsic delays associated with them. If these probes, they are not sort of synchronized in some sense, or the delays are not matched, then you would see errors. So you can see here that for about 1 or 2 nanoseconds of mismatch, how much microjoules of energy calculation can come in. It's extremely sensitive to this kind of alignment between the voltage probe and the differential probe. So to address this, we need to do what is known as deskewing. The probes are skewed in the sense that their delays are not matched. So we need to reverse that. And one simple way of deskewing is reported in literature is utilize the fact that because of inductance present in the half bridge loop, this is where the half bridge loop inductance can actually help you in some sense. When you analyze that switching transition, you will see that when the device is turning on and the drain voltage also falls, initially the voltage will fall and then the current rises. There's going to be a notch, like this, okay? And this notch exactly corresponds with the rising instant or the rising peak of the current. So in your measurement, you see that this first notch is not aligned with the peak of your current waveform. Then you know for sure that there is some delay, and you can then just try to adjust the delay of the either probes on the oscilloscope and try to arrive at a waveform like shown in the dotted line. And when these two peaks sort of coincide, and you can verify these things from SPICE simulations and so on, where of course there is no such delay, and you can be convinced that this is in fact the case, that this L di by dt and this drop that happens, this corresponds with the current commutation peak. So that's again very important, deskewing, and that's how you can ensure that your measurement, instrumentation losses are you're being accurate enough. So I'm sorry I hurried really through the slides at the end, but that's essentially the end of my presentation. So thank you again, and in case I skipped some of the slides and you have some follow-up questions, of course I'll share this copy of the slides with you guys so you can look through them in detail. But if you have any follow-up questions, please feel free to email me, and I would be very happy to discuss over email. So with that, thank you again, NIT Goa team, and I hand it over to you.
Thank you. You able to hear me, sir?
Yes.
Yeah. Thank you, Professor Shailadri, for your valuable talk. We also have our next speaker, Professor Narayanan, over here. I'll just tell you hi.
Hi, Shailadri.
Hello, Professor. How are you?
I'm doing good. So I think they're going to turn on something. Then you may be able to see me.
Oh yeah. Is my video not turned on?
Camera. Sorry?
Yeah, my video is turned on. Okay. You are there. You're trying to flip it at your end. I see.
Yeah, at our end. Yeah. Okay, yeah, now I
Yes,
think.
I can see you. I can see you.
Good. So thank you for your nice talk. Yeah, very interesting. I'm sure a lot of people
Thank you
should
so much.
follow with you. Yeah. Bye.
Yeah. Thank you. Thank you. Yeah. Bye.
Thank you, sir. Yeah, we can start our regular session. Just help him close us.
You check if you're able to hear me clearly. Yeah. Repeat at the back. Able to hear me. Today we really want to hear is motor drives. Okay. What do you mean by motor drives? I see some example. Okay, not that you have to understand this entire now. There is something called lateral control. Okay. There can be vector control of induction motor or something called common magnetic motor. Or there can be there's a motor called VADC. VADC control. Okay. So, and you want to. This is typically what you learn from. And most typically as a master's course. Correct? You get course 11, course on motor drives. So what is motor drive? Motor is a motor. All electronic control can actually control motor aspects. Because this all electronics, you can make a motor to generate motor very easy. So you have to learn about motor control. That is using power electronic control how you make a motor to get the way you want. And how you deliver power. That's the subject. Right? You have to master. I say, next is already a master of it. Okay. So there are many others who want to master the values in a subject. And these three issues, let us say, the difficulty is if you have to learn so much of the control, there is a variety of control here. There are variety of machines and there are different kinds of plants, different kinds of control and validation. So that's a huge variety. More important than that, you need an understanding of machines. You cannot do this very effectively unless you have a good understanding of electrical. This is an essential prerequisite. What are those machines? Firstly, let me put DC machine. That is the simplest that all of us know. And let me say IM stands for induction motor. Right? That's very common. Sriraj, maybe you can also come forward so that other people can move forward. Huh? All right. Yeah, check. Yeah, you're fine? All right. Okay, Yesh, anything interesting? Okay. Sriraj, you can come to the front now here. That is only my notebook. You only have to take care of that. Nothing more than that. There's no competitor to you there. Yeah. So the black cat commandos at the end can move forward. Move forward. Why don't you move forward? Rather than a trickle effect towards the end, somebody, hey, Alok, come here. Come. Take those seats somewhere behind Kirti. So 2 more seats are here behind Kirti. Yeah. Okay. So this for the motor drive class, right? You need to be good at electrical machines. What are the electrical machines? DC motor is the simplest. Induction motor is the most commonly used motor, and synchronous machines are another one. Widely used, most widely used as generators. And then there are many other
special machines. Okay, special machines are something that will mostly need a power electronic controller. If you have this knowledge, this becomes easier. You certainly need a good knowledge of the conventional machines like DC motor, induction motor, and synchronous machine if you have to step in there. And a knowledge of special machines also will help. Okay, I'm just putting the problem from a learning teaching point of view. This electrical machine now, for various reasons, now we are doing very few courses. There was a point of time that we are doing 4 or 5 courses. Now it is 1, 2, the undergrad level. It is a little too cramped. And there are too many varieties. Okay, so it's not very effective by the time you come into this class. And to cover that, there are too many motors. That itself will become a course or a course over a couple of semesters. So, considering the variety here, it's not possible to run through everything. So, you need what is fundamentally binding all the machines. There is something binding about all the electrical machines. Let's call them as electromechanical energy conversion principles. Okay. If you want to relate to something like this, right? Let me put some symbols here. Right? What is this? Flux linkage, psi, flux linkage. So you will hear terms like that. What is this? Back EMF. What is this? Torque. So you have to know what do you mean by flux linkage? What is flux linkage of a coil? How does it lead to induced EMF? How do I calculate induced EMF? When so much EMF is induced and this much current flows, what is the kind of torque? All these are electromechanical energy conversion principles. If you are good at those principles, learning a particular motor or other motor becomes easy for you. So you have to handle the problem at that level, at a more fundamental level. And this electromechanical energy conversion principles itself, you no matter what, the machines always require magnetic fields. Right? The entire torque generation is all based on the interaction of the stator magnetic field with the rotor magnetic field and so on and so forth. So magnetic field is really at the bottom. And you cannot have a strong magnetic field at all without magnetic material. Correct? You would have seen what is called as core, iron, SiFe, right? With high permeability. You need this high permeability material. You open a transformer, choke of the olden days, you will find a core inside, right? CORE, core. So that is a highly permeable material. Without such material, you cannot realize a high magnetic field. And in the presence of these magnetic materials of high permeability, the magnetic field actually reduces into magnetic circuit. The magnetic circuit is all that MMF, right? That's electrons. Where a magnetic field is reduced into some kind of equivalent circuit. Correct. So this is something which comes at the bottom, and actually the inductors and the transformer, these are all very good examples of magnetic circuit themselves. So this is what we need. So what we'll do is, in today's session, we'll start from there and try to reach there. We'll start from there and try to reach the end. It's a long journey. God willing, we should be able to do that. Given time, we can certainly do that. Given time, we can certainly do that. This is probably the most systematic and foolproof way. What do you mean by fool? There are no slips. If you miss something, you'll catch that somewhere else. Some error you make, find it somewhere else. If you miss out on some detail, that will show up somewhere. If you don't do a particular motor, doesn't matter. You know the principles well. You can always handle that. Whatever work, let's say, I have been doing or many others have been doing, it's not because we have learned about all the motors in our classes. It is just because we have to develop an ability to learn about what is required and do the needful. So that's why we always keep saying, you need to learn how to learn. What you will be doing at your 51st year in an industry, they cannot certainly be teaching you in your 21st year when you are in college. Correct? You should know what to do then. So you should develop your fundamentals that are necessary. So I was telling Alok yesterday that people get old. When they get old, they retire. Correct? They cannot earn. So what do? They earn wealth. When do they earn wealth? when you are young and in your middle age. In your young age and middle age, you earn wealth. Similarly, earning education or learning knowledge becomes difficult even in the middle ages. So you have to learn when you are young. You'll have to learn when you are young. And that learning is what you can see through all your middle and that, and tell you how to handle many situations. It is not about a technical problem. If you can analyze a technical problem and solve that, very good likelihood you can solve a real life problem also. Except that you should not get entangled. You should not get entangled. If you're able to think objectively, you'll be able to solve the problem. So this is what it is, and this is the journey that would be recommended finally to go to motor drives. That's my submission to all teachers. The question is how to do that. That is my request to all the students. If you really want to master that, start from there. Okay, that is the route. That's what I would like to say based on whatever little I have experienced. So how quickly we can do is the only question. Let's try our best. So let's start with magnetic fields. Okay. I'm sorry, today I think my shirt or something is coming there. When I'm writing, maybe my cuff is also writing something. Okay. Again, I say, we are never at the starting point. We are never at the starting point. We have already learned something. You know what is a magnet. Correct? You know what is a field. What is a field? What is the common terminology for a field? Again, English. This is the place where the effect of a magnet is felt. That is what my high school teacher told me. I still value that. It has its meaning. Okay. Given a particular magnet, the region around the magnet where you can feel the effect of the magnet. The only thing, as a kid, when she told me, I thought it was bar magnet. Later, when I came to high school, higher secondary, college, I knew it could be electromagnet also. There is something else called electromagnet, and it could be for that also. Still, that's a valuable thing. So I would like to finally little bit detach and look at the word field, which is an English word. So what do you mean by field? Like kshetra in Indian languages. Means like this field of study, etc. Like science, business, all these are also called different fields, right? And then where do we use the term field? Yeah, paddy field, football field. These are all flat surfaces. And in here field, so field can be used in terms to refer to a certain area, physical area, or some area of study or something like that. And field can also be used for a three-dimensional space. So this is what we are trying to say. This is one meaning of field. There is another field. Okay. That's called, let's say, thermal field. Have you heard some term like thermal field? So what do they mean by that? Temperature. We have different temperature. There's space here, temperature is 41.2, here 41.1, here it is 39.7, here it is 38.2. So there's a distribution. So field also has the meaning of certain distribution. It also has a meaning of certain distribution over a region. Okay, that's yet another thing that we have. Here, what we say is, this is a distribution of certain quantity. What are those quantity? One is what can be called as flux density. And here also, we knew this already because yesterday we had done the electric field. That is the electric flux density. This is the magnetic flux density. This is a function of XYZ. This is a function of XYZ. And there is also, we had, like D, we had seen E also. Sorry. We had seen E also in the electric field. Similarly, here you have H as a function of XYZ. It need not be XYZ. It can be R, theta, phi, whatever. It's a three-dimensional magnetic field. So it is a distribution. It has that sense of that. And when I say magnetic field, the quantities are B and H. And the quantities, equivalent quantities are D and E in an electric field. We can leverage our ideas of electric field here and there. Because why? We have D is equal to epsilon E. Now here B is equal to mu H. The two quantities are related in a similar fashion. It's not that they are same in every line. The magnetic flux lines are closed lines, electric are open. That's one difference, but this there. So these are called what? There's a specific name in the electromagnetism textbook for this kind of equations. Are you aware of this? Are you able to recall? For those two equations, the electromagnetism textbook. This will come in which chapter? Maxwell's equation. This is not Maxwell equation. They would have given 4 equations. Below that, they will be giving these 2 add-ons. And then they would have given a name for that. What is it called? Constitutive. It will be called constitutive relationships. Okay. Right away, I will warn you on something. I'm not so much familiar with left side, but right side I'm more about talk about. Right? Have you seen the BH loop? Have you heard of BH loop? How does it look? This is B, this is H. What does this equation say? B is equal to mu H. How should it be? It should be a straight line. But what is the loop saying? It is in fact a multi-valued function. For a particular H, I can get 2 different values of B1 and B2. For a particular B, I can get 2 different values HA and HB. You understand? Something contradicts. These are the things that you have to note. We have to understand why there is a contradiction. What does it mean? How do I resolve? You get me? Okay. This, you will imagine the curve is like this. The curve is like this. That's what you will imagine. But the BH loop is like this. Okay. You have seen this also in the book. You have seen this also in the book. Both cannot be incorrect. Both have to be correct. You only have to understand when is that, when is not this. Does anybody have an answer to this at this point in time? Huh? Huh? This is true for almost all materials. For every material, you will have different kind of loop. Ideal. Equation is for ideal case. What does ideal case mean? There is no what? No, not necessarily saturation. Huh? Air core. For air core, there is no B and H. Air has got B is equal to mu naught H. Air is very best for our analysis. Is equal to B is equal to mu naught H. This problem doesn't come. Okay, if you conduct a BH loop experiment for air, you will only get a straight line. No area inside. Okay, that is clear. No area means what? It is some sense of idealism only. What is that? No area means what? No core loss. No area means no core loss. Okay, so you have to take this thing out and come up back and do this now. Continue to think about that. Okay, in about 15-20 minutes or so, we will reach this particular point. By the time, you can say why the contradiction. These two are not corresponding to each other. Why? Okay, let's resolve that out. Okay, you continue to think about that. What is the question? B is equal to mu H is a straight line. Mu can vary. If mu varies, let me do that. Pen here. My pen. Something has changed now. It has gone there. I have to pull that here somewhere. Okay. I think I've also learned a little bit. Okay. So here, if there is saturation, this curve will be like this. The black curve is without saturation. The blue curve is with saturation. And this is the actual measured BH. Okay, we'll try to resolve that. So we'll start with this magnetic field. I've already troubled you with D is equal to epsilon E and B is equal to mu H, the constitutive relationship. Now let's put down the Maxwell equation. For the electric field, you have del dot D. D is equal to how much? Correct? Yes. And del cross E. That is how much? Minus dou B by dou T. Alright? This is where the electric and magnetic are getting mixed up. Del cross E minus dou B by dou T. B is magnetic flux density. That is what tells you about induction. dou B by dou T B. That means that when the magnetic flux density changes with time, there could be induced EMF. There could be induced EMF. That could result in E vector. That's what that says. Okay. So these are equations more directly pertaining to electric fields under the Maxwell equation. So how about Maxwell's equations pertaining to magnetic fields? Instead of D, I have B. Correct? What is del dot B? That's the easiest of Maxwell's equation. Right? We love that equation. Incidentally, not now, some years back, I was called to look at the statistics of gate solutions nationwide. So when they studied many portions of how the gate electrical students are doing, some sense related to EC also, but more to electrical, the place where students had performed the lowest was electromagnetic fields. Okay. Where they had done quite well, for example, was digital electronics. What aspect of digital electronics? Like truth table, Karnoff map, and those kind of things. That particularly, and DC circuits. These were all the better ones, and some standard math. One that were particularly weak point was electromagnetic fields. In electromagnetic fields, if at all you see where the student responses have been good, that is more students have attempted and marks have been correctly, that is all application of del dot B is equal to 0. Okay, that's the easier part of that. This is where, that's a problem that we have to address. That is not for scoring marks. As I said yesterday, electromagnetic fields are required for you to understand electronic devices. They are required for you to understand electrical apparatus. They are required for you to understand electromechanical devices. So please don't ignore them. So like D, I have B, del dot B. What is the other vector now? I have H. I have H. Now what is this? This is del cross H. What is del cross H is equal to? What is del cross H is equal to? Huh? No. Does anybody remember Maxwell's equation? Nobody. Yes, madam? Yes, sir? Volume material. Del cross H is equal to what? Del cross H has to be a vector. D dot ds is a scalar. What is this vector? H. Okay. That is where think. H is about what? What field? Magnetic field. Right? To create magnetic field, what is necessary? Okay. Without that, it is not possible to generate. When you have this common sense, now you will know what is on the right side. Somebody murmured that I want it to be louder. What is that on the right side? You murmured something. Something related to J. What is J? Current density. Why not J itself? Why not J itself? Man. So del cross H is J. That's an approximation. There is one more term. There is one more term. What term will be added there? UC B vector. This is magnetic flux density. Similarly, equivalent is electrical flux density. What is that? D vector. That's Maxwell's equation. It really surprises me to see undergraduate classes not knowing Maxwell equation. Not correct. No, not acceptable. Yes. So I also gave you the reasoning, right? Del dot D rho. There's some way you can remember that. Del dot D is equal to rho. Del dot B is equal to 0. Now del cross E is where electric and the magnetics are connected. They are getting connected. And del dot B is equal to 0. There is no divergence. This is actually related to the magnetic flux lines being closed lines, etc. And del cross H, the magnetic field gets generated only because of current. And that is J. There is no such thing called current at a point. There's no such thing called as a current as a point. You have only current density. If you integrate current density over a surface is what you will get current. This is something that we had discussed in our first day. So that is J. And there is a relation between magnetic and electric. These are the dynamic portions. The last term will bother you only when you have higher frequencies. We are not looking at higher frequencies. Therefore, we will consider a simpler version here. Del cross H is roughly J. At low frequencies. This is when your frequencies are low. You can ignore the next term. Sorry, it has come to the bottom. What I have written is del cross H is equal to J. I am rewriting the equation here. Del cross H is equal to J. That's really the main equation that you have to solve. You have a software which solves the magnetic field and gives you, right? What do you think is the equation that software solves? Del cross H is equal to J. It solves del cross H is equal to J. Okay. You may tell the software, I have iron pieces like this, and I have J in this area. I have J in this area. J is defined in this area. And you will say, this machine, this has certain permeability. This has certain permeability. This is the information that you're going to tell the software, and tell the software, don't go beyond this. And you will say that the magnetic field effectively is 0 by setting appropriate boundary condition. So you will set a boundary far enough, set appropriate boundary condition, and within that you will be defining where it is air, where it is permeable material, where there is current density. And the software will solve del cross H is equal to J and give you the output. Okay, that's what you can learn to do that. How many of you did Samrat's course here? Samrat does his course here. Yes, Samrat must have talked about all this. Samrat must have talked about all this. Okay. So this is how the software does. So this equation is most important to us. So I'll go to the next point. Whatever the software does, you must be able to predict it to some extent. Only then you are capable of using the software. You understand? So you should know the software is for doing it faster, doing it for greater details, and doing more complicated things that you can solve. Not to back up for your ignorance. Software tool is not a backup for your ignorance. It is to support your knowledge. It is to multiply your knowledge. When I'm ignorant, I go and take refuge in a software. That's not correct. I have to be knowledgeable and use my software so that I can work with 10x efficiency. Okay. Otherwise, not knowing and therefore asking a software is basically getting into a danger. Okay. You don't know what you're doing. Now, let's start with understanding magnetic field. Simplest case. There is long current carrying conductor and the current is dot. Dot means what? The current is flowing out this. This is the simplest of the cases, right? Can you draw the magnetic flux lines for this? Can you draw the magnetic flux lines for this? The flux lines will be circles around the conductor, right? Okay, I'll draw a circle. And what will be the direction? That will be in the anti-clockwise. There will be a lot of flux lines closer to the conductor and it will become rarer as it moves out. Okay, something. Actually, there is an automatic eraser provision here. When you're drawing something, it erases something else somewhere. That's probably sensing some proximity with something else. That's something we'll figure out later. Because when I'm attempting to draw something, some other portion vanishes too. Okay. So these should come farther and farther. Okay. Everybody is clear about this, right? Everybody is clear about that. Okay. Now let's get quantitative about this magnetic field. Let us get quantitative about the magnetic field. Qualitatively, we know. Okay. Now, can you calculate the B or H at any point at a distance R from this conductor? How do you calculate? Biot-Savart law. Simpler than that, you had the Ampere's law itself. Okay. What was that we said earlier? Del cross H is equal to J. This is in the differential form. There is an integral form to this. What is the integral form? What is the integral form? H dot dl, that is equal to that is, you take a closed curve C and along the C you do integral H dot dl. If you do that, you will get the current enclosed. Okay, we had talked about line and the area and volume, all that in the first 1 or 2 classes. Those who have not there, you can still find that out. You can see that J and I are related, right? Can you relate J and I? Are they related or are they unrelated? They are related. Let me ask those who are there, who are not there previously. Some of the second year students, you are not there, right? Are J and I related? Yes. How are they related? What is J? Current density. What is I? Current. Current density and current have to be related, obviously. How are they related? Can somebody try? Can you? How are they related? J is equal to I by A, he says. Okay. So he says J is equal to I by A. Correct? The area is his area of cross section. Is this correct? When is this correct? When is this correct? You consider certain area of cross section here and J is uniform here. If J is uniform here, then J into A is I. In the simplest case. But what happens if J is non-uniform? What is a more general one? So what are you doing here? You are multiplying J by area of cross section. So if you generalize it, what are you doing? You are generalizing, what are you doing? J getting multiplied by area, what is its generalization? Integrating J over an area. Integrating J over an area is the most general thing. Multiplying J by A is the simplest portion. So what you're doing is, I have J at various points. I'm going to integrate J dot ds. And J is a vector. And ds is also a vector. Okay, on the first day we spent considerable time. ds is surface. Surface means what? It has some dx and it has dy. It is dx cross dy. Dx cross dy. So the magnitude is dx into dy. And its direction is x cross y, that direction. So for this surface, x is in this direction, y is vertical direction. So if I do x cross y, I'll be rotating this my x direction and this is my y direction. So when I do x cross y, I'm rotating a screw from x to y. The screw will move towards me. This is the direction of ds vector. So ds is a vector and it is normal to this here. So when I do j dot ds, j is also normal to the board. J is also normal to the board. ds is also normal to the board. And this is over this area. Over this area. Okay. That I've indicated. Since j is also normal to the board, d is also normal to the board, I can say integral j ds. What I have done? Not this portion. Sorry. What I've done, I've removed the vector signs because both of them are the same direction. So then no point dot product. Correct? A dot B is equal to AB if A and B are in the same direction. So J and DS are in the same direction. So J dot DS is J. That is magnitude of J, magnitude of DS. Okay. And if J is constant everywhere, then J comes out of the integration. J comes out of the integration and you have DS over this area. Okay. And what is integral of DS over the area? That is the area A. So this is the general thing and this is the particular simplest thing. So when you know at least the simplest case, and from the simplest case, move towards generalization. Don't think, having learned the simplest case, you have learned everything. That is the biggest Maya students can get into. If you say I have learned everything, that means you have stopped seeing, you have stopped hearing, you have stopped thinking. Okay, we started off with this, some of those proverbs, which says that what you are yet to learn is the size of earth. What you have learned is a handful of mud. So there is no one who knows everything. There is no one who knows nothing. Okay, all of us know something. We are leveraging that and going back. When I say, oh, there is nothing, man, that means not that there is nothing. I am not capable of seeing anything. That's the caution. Okay. So this is now come to del and J now. So this particular portion, I just wanted to tell you, right? I'll just move to something else here. I'm going into the application of this. So what is this? Let's say I put a circle C here. I put a circle C, call the circle C1. If I do integral J dot dl over that circle C1, what is the answer I'll get? What is the answer I'll get? Huh? Louder. 0. Why 0? There is no current enclosed. If you look at the left side, H is in some direction here. H is in some other direction here. So obviously H is in various different directions on the circle. If I really do an integral H dot dl, it is not that H is 0 on the line. It is not that H is 0 on the contour. At every point on the contour, H has got some value. But that H dot dl over different lengths are cancelling out. They are ultimately cancelling out. And there is no current enclosed, which is the reality. That is one contour. Now I'll do another contour. I'll call this C2. If I do integral H dot dl over this contour, what will I get? I enclosed. Why? It is enclosing that. You will see different H at different places. Still, if you integrate, finally, you will come up with that I enclosed. Okay. So, now, I'm using this itself as C3. I'm using this curve itself as C3. What is that curve? The flux line itself as C3. If I use that, what will happen? If I do that, dl vector and h vector are in the same direction. H vector and dl vector are in the same direction. That is what I primed you for a little back. So when I do it over C3, I have integral h dot dl over C3 is simply integral h dl over C3. Okay, integral h dl over C3. Now, what can I do? If h is a constant, I can pull the constant out of the integration and I can do integral dl. What will be integral dl? What is integral dl? Circumference of C3, 2 pi r. But is h constant? Is h constant? That's the question. Just like you said, is h constant? it is on the same magnetic flux line. It is on the same magnetic flux line, and the material is not changing. And the material is not changing. These are all indications that the H could be the same. And if you look at H is related to B. How are H and B related here in air? B is equal to mu naught H. The relative permeability in air is 1. B is equal to mu naught H. So whether I consider H or B is equivalent. How can I see B from a visual representation? The flux lines are dense, then means B is better. The flux lines are weaker, means B is low. So the flux lines, if I go around the circle C3, the density of flux lines is same everywhere. The density of flux lines is same everywhere. That means B is constant over the line, H is also constant over the line. Therefore, I can bring H out and do integral dl over C3. What is that? That is H into 2 pi r. That is equal to I. Therefore, the H at this point at a distance r is I by 2 pi r. So I have used Ampere's law. To calculate the value of H at any point. I have used Ampere's law to calculate H at any point. What enabled me to do that? Yeah, what enabled me to calculate H? First, even before that, because what Ampere has said is only integral H dot dl is equal to I enclosed. In this specific case, a number of things have enabled me. The next 2 minutes, I want you to come up with all of them. What are the things that have enabled me? If I had done integral H dot dl over C1, I would not have got my answer. If I had done integral H dot dl over C2, that would have given me I enclosed, but it would not have helped me calculate H as a function of R. Only when I considered C3 as my contour, I was able to calculate H as a function of R. So what are the things that helped me here? Direction of magnetic field and direction of contour are same. I somehow made the direction of magnetic field and the contour to be same. That means what? I chose a contour that is same as the magnetic flux line. I chose one of the magnetic flux lines as a contour. I encourage eye contact. There is nothing to be shy away. There is nothing to be afraid of. Okay, humans need eye contact. I strongly encourage. Okay, not for the class, but for your life. Don't turn away. You don't know something now, you're not sure about something, doesn't mean you have to turn your eye away. That is all the more the time you have to look into somebody's face. That is all the more the time you have to look at someone's eye and look for clue. That's what I'll say. Oh, I don't know. I'll look what Soumitra is going to say. I look at what Vajit is going to say. Oh, Otherwise, when they're saying something that I know, I may think of something else. But when they say something that I don't know, okay. You understand? Here, I chose C3, contour. That is one of my magnetic flux line. So, how could I do that? I could visualize the magnetic field in this case. I could visualize the magnetic field and I could choose a contour which is same as the magnetic flux line. Because I could do that, it is integral H dot dl over C3 only. That is valid for any magnetic flux line. That is valid for any magnetic flux line. That is not valid for a contour that is not a magnetic flux line. You understand? I could have done this integration over C4. That is this. It would have given me that answer, HR. But anything that is not a magnetic flux line, like this ellipse, I'll take some other ellipse. I would not have got my H value. So I knew my magnetic flux line. and I used one of the magnetic flux lines as my contour. Therefore, the job became easy. So the lesson is not just in this case. In any conductors, when you have set of conductors that may have air or that may be through air, iron, whatever, if you know the magnetic flux line, somehow if you know the magnetic flux line, you can set that magnetic flux line as your contour and do this line integration. That will give you advantages in calculation. So this should encourage you to see how the lines are going to look like. There's one more motivation to look at how the lines are. Clear? Okay, so when I did that, then H and DL were in the same direction. H is a vector, DL is a vector, both are in the same direction. H is a vector, DL is a vector, both same direction. In this side, both are same direction. Here, same direction. And therefore, integral H vector dot DL vector is becoming integral of H DL. Cos 0. Angle is 0 between them. It is H into DL into cos 0. H DL. And next, what did we argue? We argued whether H is constant. When the line goes through iron and air, this could be different. You have to be careful. So you have to look at B. If you have to look at B is uniform, and from that you have to try to see, and in the same medium. I saw that B is uniform and it is in the same medium. Therefore, mu is also same. Therefore, B by mu is same over the line. And therefore, I pulled H out. Okay. So this I by 2 pi r, many of you have derived, right? How many of you have done this? Raise your hands. Well, I'll ask the question differently. How many of you have done an electromagnetism course? Raise your hands. Except the second years, everybody must have done. Second years must be doing it now. They have also done. Then the whole class should raise your hand. What is the problem in raising your hand? Frozen shoulder. Get a physio. I'll tell the director to get a physio in your health center. Raise your hand. If you've done electromagnetism, raise your hand. So almost everyone. Thank you. And you all did fresh people, right? Only I am 35-year-old electromagnetism per student. Now, did you not solve this magnetic field to your current carrying conductor? You did. You would have come up with this I by 2 pi r also. Right? Now tell me, why did you miss this point? Tell me, why did you miss all that? We also done the same thing, right? Why did you miss all this? Did you miss all this in your class? No, you didn't miss anything. Okay, I think there's no connection happening here. Leave it there. Okay. In electrical, loose connection is the biggest problem. If the circuit loose connection is okay, your circuit here, it is a bigger problem, not to you, to others. Okay. Circuit is loose, it is your problem. Make sure, no matter what, your circuit is not loose connected. Okay. So if I know that, that is how it is going to. This is now, we have just done long conductor, infinitely long conductor, and only application of Ampere law. So we have understood Ampere law a little bit. Correct? What I was asking is this I by 2 pi r, everybody has done here. But why is that there were so many points in between? I asked you whether you looked at those points. That was my question. Okay. If you don't understand the question, it is all right. At this point, if you pretend not to understand the question, it is all right. You understand the question and don't want to tell the answer, that is also all right. But have the question in your mind. Okay. Honesty is what gives you true value. Honesty is what gives you education. All right. Now, I'll take a slightly different case. This is also a conductor. This is also conductor. A current I is entering here and that I is leaving here. Okay. Now I'm telling you calculate H at this point. Calculate H at this point P. This point is called P. Calculate H at this point P. Can you do this? How do you do that? It's a bent conductor. Is the context becoming clear to you? Is the context clear to you? Is the context clear to you? What is the context? when you are considering this kind of an L-shaped conductor. Correct. How do you calculate that? How do you calculate that? What is the approach to calculate? What is the approach to calculate? Is it a little hot here? Will it help if it is closed or something like that? No. Okay. Directly into your brains. You don't have a notebook with you? You haven't brought a notebook? Huh? Get a sheet of paper from somebody. Get a sheet of paper from somebody. How do you calculate this? Is it as easy as the previous case? No. Why no? Why no? Why no? You cannot visualize the magnetic field. Somebody said something. What is that? The conductor is not in the same direction. Therefore, the magnetic field lines are now confusing. The magnetic field lines are, when you don't know the magnetic field line, earlier we knew that. And we could fix a contour. One of the magnetic flux lines is a contour. Now we cannot fix because the magnetic flux lines are not clear. Right? I am not even asking for a magnetic flux line. Note the point. I am asking you only what is the H at a particular point. Okay. So now Ampere's law cannot directly help. You can do this by doing what? Del cross H is equal to J and numerically solving it. And numerically solving that. That is what a software will do. That is what a software will do, and it will give you H at these various points. So, what is the approach for you to calculate if it is asked in an exam? Yes. If this is an infinitely long one, it is easy. If this is infinitely long one, that is easy. But both are not infinitely long. They are finite and they are bending. At the corner, there will be deviations. So, finding out the magnetic flux lines are very difficult because at least if I know points of same H is so many units, there also H is same, then I can connect them and construct a flux line. No, I cannot do that also. Okay. This is why there is another law. What is that law called? Biot-Savart law. So, you can use Biot-Savart law. If I am not intelligent, okay, humanity, there is someone else who has been more intelligent than me in this respect. And they have done that, and I should learn from them. I should learn from them. It is stupidity if I don't learn from others. Okay? And when I get an opportunity to learn, and when I have a need to learn, this is Biot-Savart law. I'm not going to go into that. So, does somebody remember Biot-Savart law? I will have to consider some length dl here. I have to consider some elemental length dl. Current flowing through the elemental length dl creates some magnetic field here at this point. So they will have this, there's some distance is r, and there's a vector. Okay, this will say dh vector. Does anybody remember this? Does anybody remember this? Ideal I. This dh is certainly proportional to I. The dh is certainly proportional to I. Then it is also depending on dl. Correct? Okay. Okay. But dl is a vector. dl is a vector. If the left hand side is a vector, the right hand side should also be vector. And this should depend on r vector also. dl cross r hat. dl cross r hat. Okay. You have to check whether this is right, that is right. When you do that, you can check that by saying if dl is in this direction, r is in this direction, rotate, what happens, right? And you also know for this magnetic flux line, how will it be? It's going upward. So the line, this is flux lines are dot and the flux line is cross here. The flux line is cross here. That is known to you. That is what you have to do to check that point. The flux line is actually a cross flux line. It is getting into the direction of the board. Okay. Do that dl cross r hat. This gives you the direction. This is elemental, incremental quantity. It is incremental quantity. So this side is also incremental. That is why it is dl. And this has to be divided by r, some power of r. Huh? I'll leave that to you. Is that correct? Correct. Is it correct? Normally H is what? I by L. Okay. H is I by L. I have I here. I have one L at the top. I have L cube at the bottom. So it is I by L square here. Okay. The question is whether it is R cube or R square. You check that out. Okay. I'm not going to do that. You should know and you should not memorize. You should not memorize. You should digest. At least when I know, I read the formula, I say yes, I is in the numerator, y, it is proportional to that. I should say it is a cross product of the two. Yes, that is the direction. This side is elemental quantity, that side should also be an elemental quantity. And this should be some inverse proportion of radius and its power. And it should satisfy the dimension of h. These are all the checks that I have to do. I'm not going to do this for you. You do this. This is what? It is the h contribution at P due to an elemental length dl. This is not enough. What I need to do now? Actually, I have to do an integration of this over, let us say this is A, this is B, this is C. I have to do this integration over AB, and then I have to do the similar integration over C. If I do all this, I will get h at that point P. If I do all this, I'll get that point. So you know, by the time you calculate for some practical case, you will be close to retirement. Okay, but this is Biot-Savart law. This is fundamental. You have to understand. It becomes difficult if it is not a straight line. So understand this and go ahead. So now I'm looking at the same long straight conductor carrying current I in this direction, and I'm looking at the flux lines. How will the flux lines be? Normal to the board. Correct? So there will be flux lines here. These flux lines will be dot or cross. Dot. I can't put them very clearly. You can put them bigger. Okay, what are these? 3 flux lines. I'm drawing the flux lines here. There are. This is actually a little closer. This is a little farther. Okay, I'm being not very accurate here. These are all flux lines. Here, what do I mean by dot and cross? Everything is a flux line. Okay. Clear? Now, we have seen the problem of evaluating magnetic field. You can use Ampere's law when it is easy to know the flux line. You can use Biot-Savart law when you cannot find out the flux line. That is, it is our level of understanding. Both are difficult. Computer Namaha, software Namaha. Give that, and that will give you a solution. At least you should know whether it is meaningful. You should know whether B must be high here, low here. Correct? What is the peak value? Is it meaningful? It should not say that 1000 ampere of current is flowing through a small 10 gauge wire, right? It should not be like that. It should not be meaningless results, right? You should be able to at least find that out. So you do this now. Here what I'm trying to say is, with that, you know how to calculate the magnetic field. We are not getting further into calculation of magnetic fields because Software is there. If you don't know the software, there's AI tool is there. Hey, great software tool. Please tell me how do I use this software? Then that will tell you. Correct? Yes or no? You can say that, oh, I'm able to open this, but I'm not able to handle that. He can tell you more and more. It only depends on the subscription you're willing to pay. They can write a book also for you. If you're willing to pay big subscription. What comes out of what goes in, that's a different issue. But it can do that for you. So I'm not going to go further in calculating the magnetic field. I'm now going to go in the direction of creating a strong magnetic field. Going in the direction of creating a strong magnetic field. So many times I know qualitatively, unless I create a strong magnetic field, my task is not going to be done. Is it clear? So how do I create a strong magnetic field? So what do you mean by a strong magnetic field? When the lines are closer. When the lines are closer. So I have one conductor like this, and the magnetic lines are like this. Okay, using the same current I and using the same conductor, can I create a stronger magnetic field? Huh? Very good. How? Excellent. Excellent. So what do you do? The same conductor, let us loop this conductor. Same conductor. What is going to happen to all the flux lines now? The same direction of current I. I is like this, like this. How will the flux lines be? Outside all of them, dot. There will be dot lines here. There will be what will happen to cross lines? All the cross lines will be inside. Earlier, all the cross lines that were there over one semi-infinite plane, have now been confined into circle. The flux density has gone up by a factor. What kind of factor? Semi-infinite planes area, the very large area divided by the area of circle. You understand? There are 100 lines over a very large area. Now 100 lines within the cross-sectional area. This innovation of electrical engineers is nothing short of invention of wheel. Nothing short of invention of wheel. These are all the true innovations. We don't even know who did that. You'll always say coil, right? In any electrical engineering class, the first basic electrical engineering professor came, oh, let us consider a coil. Always they talk about coil, right? I used to wonder why they are asking about coil. Why electrical engineers are so very obsessed with coils. It is much later I understood that this particular one of coil. Why do we use a coil? Why do you think we use a coil? Huh? Yeah, now we know. We are explaining it in this fashion. But prior to this, what was your understanding? That's same. Okay. So you do this. It becomes a strong one. Now, how do I increase the strength of this? That is the next question. What have I done? I'm looping it into a coil and I've made it stronger. Next, what do I do? I can increase the number of turns. So if I increase the number of turns, that will look like this. This is a 4-turn coil. Okay, there's dot and cross. Now these are currents. These dot and cross are currents. This is what you can call actually as a air core coil or air core inductor. How will the magnetic flux lines look for this now? Draw a few magnetic flux lines. Draw maybe 4 magnetic flux lines. Draw. So 2 of them loop around the left side, 2 of them loop around the right side. They will not curve inside. There will be more straight inside. Curving will happen. Outside they'll loop around. Outside they'll go much farther. The lines will not meet each other. The lines will not meet each other. And they won't be going, they'll be going farther. These lines will be much farther. Okay. So what is happening is, all these can have lines. Every dot can actually have a line around itself. Every car can also have a line around this. There will be some lines. And there will be some lines around these two. There will be many lines around these 4. Similarly, some lines around these 2, many lines around these 4. So let us look at lines around all the 4. It will be more like this. On this side, okay. The field is stronger within the coil. The field is stronger within the coil. Many lines have come corresponding to all the 4 turns are flowing through that. Therefore, it is stronger. You can draw many more lines. These are only illustrative indicative lines. Okay. So we have gone to from a conductor to a single turn coil and single turn to multi-turn coil. Yes, Toshi. May not be straight because of the gap between the two. I have exaggerated that. It is all right if you have drawn these as straight lines. Okay. But there is a gap between the conductor. There will be notches. See, my fingers are not perfect. So I cannot reproduce that. But if you draw all the 4 lines as straight lines, it is all right. Except that you should know that between the conductors, they may get a little farther. Okay. And I did this purposefully to tell you something else. Next, I'm going to make it even stronger. How can I make it even stronger? I have run out of my ideas with copper. I have run out of my idea with copper. I conducted in to turn. I made multiple turn. Now I have to bring iron. Now I have to bring iron. So what do I do? Let me have the same 4 turns. Okay. Let me put a piece of iron. Loha, Yanamaha, that is iron. I put in there. Now how will the magnetic flux lines look like? This will be straight line. This will be much more straight line. These 4 lines this line will like this, like this. They should not touch each other. Okay, sorry that these lines more straighter there. Okay. Mm. Mm. There are many interesting points when you put a few conductors together, but you can think it over. Okay. Some other time we can even discuss that. So what happens in this conductor is, for example, this is a dot, right? It is going to drive anti-clock. This is also going to drive anti-clock. So sometimes between the two, they will cancel each other. Between the two, they will cancel each other. And that is how they start circling all around. Okay. Yeah. So this is now because I moved from the to iron. So now, what does iron say? Inside the iron, there is some regularity. If you put some iron, there is regularity, there is predictability. Kids used to be running around, kaka boka, something there. Principal sir walks. Tak, tak, tak. The old school principal, I'm saying, not the now. Then the kids are all in their place. HM ma'am is coming. So you mean there is a regulatory influence it is having. Correct? Something similar with iron. Something similar with iron. You understand that when iron is there, the flux lines will go in some pattern. What is that pattern? Roughly the direction as shown by iron. Okay. Next, not just that. Can I make them behave just along the line, or can I turn them around? I can turn them around. What happens when I put a C core like this? Draw a few lines. Draw a few lines. In 5 minutes we'll close. Why only one? Draw a second line. Second, third. Will there be no line to the left side? That's not how it is. Done? Yeah, these all will go much farther. Much farther. Can there be a line on the left side? No, this will not turn around like that. No, it cannot turn around. This cannot really turn around. The lines will come on this side. The lines will only move towards and close here. Yeah? The lines have to turn around and do that. Draw them. Unless you draw, you won't even know whether you have to correct yourself. That's not what it will happen. It will go and complete itself here, this side. This will go complete. Somebody called? It won't bend, Kana. It will go further, like what you have drawn first. It will not go directly. It will go farther and come back. Yes, in some sense like that. You draw a second and the third line. That is what? The first line will be there. The second line will be farther. Correct. That will not be the case. There is no turning around. There is no turning. Everything has to enclose certain set of conductors. Okay. Yeah, these will not happen, Kanna. Okay. This is probably okay. So from these lines, I'm not saying where the conductor or where it is. I think from here the line will go like this and go back to the C. This is correct. This is correct. Except that they can get farther. There can be some line here also. And yeah. All right, good. Unless you try, you won't get started. Static friction is the highest friction. Okay. This will go further and come back. Not well. Not well. Huh? Headache. Why don't you take rest? Go have a break. He is also not well. Huh? You're not well. You're not well. Go have a break. Tell Johnny fatigue. Go have a break. Go have a face wash. These lines cannot go around like this. See, the lines won't go longer. They like very short path. Lines. Why you haven't tried? Why you haven't tried at all? This is reasonable, but the lines will be farther. This and this will be far. Okay, this and this will be farther still. Only if you have done something, I can tell you something more. I can read your mind. I can only see your paper. They don't stop. They have to complete. They have to complete. No, this is correct. This will be farther. This will be even farther. They will not be equidistant. Okay. I've seen quite a few responses. Okay. So, let me do something now. Let me take a line like this. Okay. There will be a line. Though this fellow is sharp, this fellow will turn smoothly. The magnetic flux line will turn smoothly. There is no such thing as a sharp turn for a magnetic flux line. Why? If the line turns like this, it means it has this direction and also this direction. The magnetic field can never have two directions at the same point. Therefore, there is no sudden change in the direction of a magnetic flux line. Okay. This fellow will turn smoothly. This is more or less a straight line. More or less a straight line. And very gently is going to turn around here. It's going to turn around here. And take that. Right? It comes here. Comes here. This is a part of one line. Let me start tracing another line. They also look almost parallel here. Moment I bring in something else, I'm losing. So, these lines are roughly parallel inside the iron. Okay, when they go out, they can actually diverge. This can be like this. This fellow can go farther. And another fellow can go get my point here? They'll be farther and farther. There can also be a line like this. There can also be a line like this. This will be very close to the black surface. There can also be a line like this. Okay. There can also be a line. They're ballooning out. Inside the iron, they are confined. Like military soldiers walking. Outside, it is like some general janta. So I told you iron makes them disciplined. I gave you a rough analogy. Outside, when they are back into iron, hey, kids coming out of school, long bell, over. Home. They go. Yes. At these corners, it will increase the concentration. There will be local saturation there at the corners. That is correct. Absolutely, yes. Absolutely. See, previously, how was it? Previously, how was it? I will not talk of H and B. I'm talking only about flux line now. I'm talking about visualizing the field. We'll come to that later. You first visualize the field. 8 out of 10 of us here, 3, 4 out of 10 out of here are not even able to start how the lines are. Another 5, 6 out of 10 here are grossly incorrect in how the lines are. Okay, let's clear that up. Let's visualize how that is. Let me finish this. So this line, I'm not going further. Okay, I'm leaving it incomplete. Left side, there can be a line like this. This can be a line. If I go to correct that, something else happens. Left also, there can be a line. Every line will enclose current carrying conductors in a particular direction. There can never be a magnetic flux line that does not enclose current carrying conductors. It will be enclosing non-zero current. You cannot have a magnetic flux line here. For example, let me take some other color and draw. There cannot be a magnetic flux line like this. It doesn't enclose any current carrying conductor. And some people have drawn, for example, the line comes all the way here and goes back and comes around like this. This is all not expected. That is, the line is turning here. There is no reason for the line to turn around. There is no reason. Such a turn will happen only if some current sits here. Some current sits here. Only then such a turn can happen. Otherwise, such a turn cannot happen. You understand? They are all enclosing them. The path is now changed. Yeah, it can happen. Many things can happen there. Left side lines are not too important. The right side lines are more important. The right side lines are 80 to 90%. The left side I have drawn only one line to show that there could be lines there, and to show if there's a line, how typical it is. These lines will be very close to the edge of the iron, and they will be almost right angles here. They will leave the iron almost at right angle. Okay, and they'll loop around. There can be a line leaving like this. There can also be this is also possible. What is the question? Can they speak out?
Sir, good afternoon.
Yes, sir. Yes, sir.
Yes, sir. When there is an extended iron to the right, why there is a short line coming and getting connected before that?
Hey, something gone off. Oh, okay. Oh, because we changed to this. You have saved the previous ones. This is Raja from NIT Ruchi. Come again, Raja.
Sir, when you have this L shape or U shape, when the lines are moving towards, say, right, till there is a change of material, why they should take a shortcut to reach?
There is a change of material, and why there are sharp cuts. I'm sorry, not able to. So you are talking of the case where the flux line is moving out of the iron?
Yes, sir. We have the horizontal bar on the top now, sir.
Correct.
So I feel that line will go till the end because it has got a iron till there. Then it will exit, right now, sir? Why it should exit before itself?
Some lines can exit prior to that.
Oh.
Some lines, okay. Yeah, you go back to that. I see what he's saying. You can go back to that question. I think when online we should not do anything. We should just listen to the question from them. and should not try any other changes here that affects the. I'll probably do this again. What Raja is asking. So I hope all the previous things are clear for you. So these slides have been erased. They should not be erased from your mind. They should only get clearer. Then these slides are not necessary. There used to be one big scientist, right? He used to have a very huge book. Every day he'll read 2 pages from the book and he'll throw them away. He used to read 2 pages and then throw them away. He's a European. And in 600, 800 pages he finished over a year and a half. The chemist. Yeah. Go back to that and let's. Hey, don't worry. Huh? Which one? Say this new one now. The old one is gone. Hmm? The recording is there. Okay. Open this page and I'll answer what Raja is saying.
Sir, sorry, that screen alone will generally get projected, sir. That is not coming now. The entire camera is getting.
Yeah. They're not doing that. I mean, we have lost the previous slide. Now we are just starting something. Wait a minute, Shahbaja. There is Shubham missing the key. Huh? Okay. Yeah, what Vaijayanti is saying is that you save this file, give a name and all that. But where did he go now? Huh? We are all of going for tea anyway in a short while. Okay, shall we break for tea and then come back? Yeah, I think we'll break for tea. Raja, sorry. We'll break for tea and come back.
Yes, sir, I will join. Yes.
Yeah, sorry. Yeah, 10 minutes we'll meet back. Okay,
You are audible, sir. You are audible.
very good. So what we are now trying to say is, in this, the red lines that are flux lines, they are all kind of, reasonably uniform, parallel to each other inside the iron. Okay. So if I have to draw that a little more clearly, what happens at the edges, there are drawing imperfections. I can show you some, it is always good to do a field plot using a software, and you can come up with that now. In this, you can see that innermost line. Raja has a question. Lines could be there, because if you see this innermost line is covered all these 4 conductors. Okay, so there could be lines there. The only thing is number of such lines can be lower. And there's a drawing inaccuracy at this point. You see here and you see here, there's a very, very big drawing inaccuracy. What really happens is, when it leaves here at this point, there is tangential flux density, there is radial flux density. And the tangential flux density here inside the iron and outside the iron are very discontinuous. The tangential flux density will be very high, and here will be 0 in the air. Whereas the normal flux density will be constant. So this line should leave normal. That line should leave normal. Again, this portion of the line also should leave normal. I don't know if I can correct that here. Yes, so if I do this, and let me take a pen and let me take a different color, let me correct this. This will come like this. This will come like this. This going out and coming back like this is a better representation of this. There can also be a line like this. It's difficult to draw many lines on this, but goes in normal. And this kind of a line that the students, some of them have drawn, is incorrect. So that is why I wanted to, but I cannot now probably erase that, but doesn't matter. Let me go back. Okay. So all these lines will leave normal, and here also you can see this line is actually normal. These are also, this actually leaves normal, and then it kind of goes around like this. It balloons out. That is how you will have the typical thing. Okay, I can show that. That is, I think, we can show, you can plot it yourself. I can show a plot also myself. Raja, is your question clear? Anything else to be answered now?
Yes, sir. Yes, sir. Thanks.
Okay, thank you. I can move this now. Here I can start writing now. Okay, so now I will go to the next point. I'll say dot cross dot 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 cross cross cross, and I have this. It is turning right, and it is turning inward. It is turning inward. Here also it is turning inward. Here also it is turning inward. This is the next step. So I know I can direct the flux lines through the iron. They'll obey whichever direction iron changes, except that iron's edge may be sharp, but the flux lines will change smoothly. So now you will see that almost all the lines, there can still be a very few line here as an exception, right? A few line can come here. For example, some line can come, go out like this. There can still be a line like this. Many of the lines will now come there. For example, a very typical line, normally it is best to draw the most typical line that will give you the direction on how to think and how to proceed. And if I look at a line here, actually a line can be like this. I'm not drawing the remaining portion of that. And actually a line could be like this. I'm not drawing the remaining portion of the line here. Okay, so the point that I'm also trying to make here is, this could be ballooned out and this could be like this. That is, I've made all the flux lines move through this gap, but still it is non-uniform. Still it is non-uniform. So I have created a strong enough magnetic field. I've created a strong enough magnetic field. Why? Initially we started all of them in one semi-infinite sphere is confined here, right? And all of these fellows are going through this, right? So you will have many of the lines coming up here. There are actually more lines here. There will be much denser lines, and there are fewer lines like this. But it is non-uniform. It is non-uniform. So now let me make this uniform. How do I do that? with everything being the same, I'm reducing the gap. I'm reducing the air gap. Okay, and the same conductors are there, dot and cross. There are conductors. Let's say this is same cross here, dot. Now what will happen? Now what will happen? The flux lines are more uniform. Yes, the number of extent of fringing will come down, and the lines will more or less cross like this. There may be a small occasional line like this, but most of the lines are going to be straight line. And it is also a uniform magnetic field. It is also a uniform magnetic field. It's a strong magnetic field and is also a uniform magnetic field. Why it has come? It has come with a small air gap. Come with a small air gap. So how small is a question. The answer that generally the experts say, G, that is related to the area of cross section. The area of cross section is big, the gap can be correspondingly big. But gap is L dimension. Area is dimension L square. So it is related to square root of area of cross section. You have to consider the square root of area of cross section. And if your gap is much less than the square root, they say fringing will be negligible. They say fringing will be negligible and you can get a uniform field. So here what is happening is, if you observe this, these are actually leaving at 90 degrees. These are actually tangential. Why it is like that? Inside there is a tangential component. Outside there is a tangential component. The inside tangential component is very high. The outside tangential component is. If the material is infinitely permeable, outside tangential component will be 0. So inside tangential component, if it is say 1 Tesla, the outside tangential component will be 1 Tesla, let's say divided by 10,000. If the material permeability is 10,000. So 10,000 is like 0.1, not 1 millitesla. So it is very negligible. Whereas the normal flux density is continuous at the iron air boundary. And therefore these lines leave normal. The lines leave the iron surface normal and they enter back into the iron surface normal. That is because of the high permeability of iron. Now what is happening when the air gap is small? They are leaving it normal. They are leaving, all of them are leaving normal. After that, they will have a tendency to diverge. But before they diverge, they are entering again into the magnetic flux line. And when they are entering, they have to enter normal. When they are entering, they have to enter normal. So the gap is so small that they are completely normal. You get my argument? While the lines are leaving, they have to leave normal to the surface. While they are entering, they have to enter normal to the surface. And the gap is so small that they cannot really diverge. And there, so that's a qualitative reasoning for this. So this is now, we have now created a strong magnetic field, also of uniform reason. Okay, yeah. So any questions on this? Here also you can occasionally have a leakage line. Okay, there can be a leakage line going around like that. It's possible. And to calculate leakage, you normally have to put the exact conductors also and do your simulations. So this is now how we are kind of visualizing a strong magnetic field. Okay, so now I'll finish a quick thing next. Why do we create a strong magnetic field? Okay, if you see, actually Fitzgerald and Kingsley kind of books, they give you 3 reasons why you know magnetic fields. One is they say it is for measurement. You need a strong and uniform magnetic field for measurement. For example, like a galvanometer. Like a galvanometer. That's an example. Sometimes that is for certain force production, right? That is like relay, okay, electromagnet, etc. Solenoid, okay. These are all, you produce certain force and act something on them. The third variety is electromechanical energy conversion. Clear? These are three things where you need strong magnetic fields. The books kind of classify them into this. Let us look at one by one. Let me first look at the galvanometer. Okay. Here you have very strong magnetic field. Let me try to use a different color. You have strong uniform magnetic field. Let me go to another color. What is placed here is, what is placed on this is a non-magnetic former. The green fellow is a non-magnetic former. It does not affect the original magnetic field. It does not affect the original magnetic field. On top of it, it has currents. It has currents. Okay, it can have dot and it can have cross. There's a coil wound around that. So there is current in a strong magnetic field. The original magnetic field is unaffected. The original magnetic field is unaffected. So now these will experience force. The current carrying conductors will experience force. So let me say there are n number of turns here in the green coil. N number of turns are there and they carry a current I. So you use this BAL. So let's come to how that BAL is done. Okay, what is force in a magnetic field? QE, that is if it is electric field. If it is magnetic field, it is Q times V cross B. Okay, now V and B. If I look at force per unit volume, this is force per unit volume. Q will become charge per unit volume times V cross B. So, charge density multiplied by speed is my charge density multiplied by V vector of the charges. What is that? This is charge per unit volume. This is speed, distance by second. So what is that? And by time. Charge per unit volume, right? Multiplied by area. So that means charge by, and then it divided by time. You are dividing it by time. Charge divided by volume. Charge you divide by volume, right? And multiply that by linear speed. Linear speed is what? Distance by time. So it is going to be charge by time. Charge by time is what? Current divided by area. That is going to be current density. That is going to be current density. This is J cross B. When you really have a uniform magnetic field and there is a current density J there, J cross B. You do J cross B to get the force per unit volume there. Then you have to do a volume integration of this. In this case, what happens? B is constant. In this case, what happens? B is constant, J is constant. And they are normal to each other. They are normal to each other. So J is, like say, in the direction of your board, outward or inward. B is, let's say, vertically downward. And therefore, what will happen to force? Force will be horizontal. So depending on this, the force here can be in this direction. And the force in this can be in this direction. Because one is dot and one is cross. So this produces a couple. And how do you get this force? I have to multiply this by volume. So J cross B, I can forget it is JB, sin 90 only. So how do I go to volume here? I have to multiply this by area of cross section. So this FV, I have to multiply by volume. What is volume? Area of cross section of the conductor multiplied by the length of the conductor. So if I do that, what will I get? Current, if I multiply the area of cross section, is current. And this is B, and that is the length of the conductor. That is why you get the force BAL. That is why you get the expression BAL here. That comes from Lorentz force. Okay. Force is Q times V cross B. Then force per unit volume is rho times Q has become volumetric charge density. Rho times V cross B. and rho into V is J. So J cross B. So F is J cross B. In a magnetic field at a point where it is B vector, and if current J is sitting there, then the force experienced by the current is J cross B. And in the case of a galvanometer, J is constant in those small regions within the conductor, and B is constant, right, in the vertical direction. And J cross B, J and B are normal to each other. So it is sin 90. So I can multiply it by J into B, and I have to multiply it by the volume. What is volume? The area of cross section of the conductor and the length of the conductor. That will be BAL on one conductor. That will be BAL on one conductor. I can multiply it by N. I can multiply that by N. So this is the first is for single converter, and you can later multiply this by, yeah, the whole thing can be multiplied by N to come to this final value. And it's going to be a couple. And to be a spring, and there's going to be a change in the angle in the spring. That is what will give you a galvanometer. So that is a case of a measurement instrument. You need a strong uniform magnetic field, and what you are placing in the gap is non-magnetic. What you are placing in the gap is non-magnetic. So now let's go to another case. What's happening? I should do a plus now, right? Just save it first. Okay. But God creates the world. At the end, everything goes inside. So if it has gone inside Yash's head, it can come out. No, not only one, there are many of them, right? Clear? Yes? Clear? What is clear? Huh? You know how you got BAL now? Yes? No? That's fine? Okay. If you are saying yes, you should look at me and say yes. Huh? Okay? What's okay? So you understood how force is getting generated. You understood Lorentz force law. You knew that before. You know. So you knew this. Why is it blank? Huh? Huh? Ah, man. So what is in your mind, put it on the paper so that we'll be happy that, oh, he has so much in his mind. Grant us that happiness. Huh? Everything okay? How about your name? Okay. Where is that man? Everything in mind. Put something down. It's like wisdom in some jnani's head, you know. But we are all low-level people. Utter some pearls of wisdom. Okay? No. So that was the case of a galvanometer. Now let me take another case. Okay. Is there anything interesting there? Is there anything interesting there? Is our jnani saying something there? Okay. All right. So let me say I have current carrying conductor here, let us say dot and cross. Okay. Let me say I have what is this? Some kind of a plunger. When I excite this, this fellow will get attracted. This is high permeability mu r. This also high mu r. This also has a high mu r. Now this does not have a current carrying conductor. This does not have a current carrying conductor. Yet there is a force. Yet there is a force. How will the magnetic flux lines flow here? How will the magnetic flux lines flow here? Oh, sorry. You can just. Okay. There may be some line like this. There could be lines. There are lines flowing through that. And these lines are stretched out. These lines want to become shorter. These lines want to become shorter. That's why I say, hey, ajao, andar ajao. That is why it's getting attracted. Whenever the flux lines are stretched out, it doesn't want that. They want it to come to normal situation. Someone is like pulling your hand and leg. You don't want that. You want to be left alone. So that is what is happening. This generates a force. Here, there is force, but there is no current. So you cannot say that force is BAL. That is what my professor told me. You say force is BAL. That is what my professor told me. With that, you cannot calculate. There is no I sitting there. And if I don't have the magnet in between the plunger, the magnetic field is different. If I put that, the magnetic field is different. At different positions of the plunger, the magnetic field is different. Okay. Here, that is not happening because of force acting on certain J. Here, this is happening because of change in reluctance. This is happening because of change in reluctance. The minimum reluctance position is when the plunger comes and settles itself means minimum. Okay. Such kind of force is called reluctance force. Such kind of force is called reluctance force. Okay. So, the switch reluctance machines, synchronous reluctance machines are all stepper motors. All these are all basic derivatives out of this now. So, this formula is not applicable. You have to go to do something with force. That's one point. I'm not going to get into the details of how do you evaluate that. Maybe that is sometime. Okay, we can mark this as a question. Calculating force on this is not a straightforward thing. It is not BAL. Okay, then how do I do that? Okay, let the question remain. If there's a question, you will get an answer sometime. Okay, otherwise we can discuss the answer at some other point of time. What happens in a motor? What happens in a motor is the motor has a stator and the stator has windings. Correct? There is a rotor. The rotor is highly permeable and the rotor also has winding. You see the point? You have a stator. You come to the third point of electromechanical systems, that is particularly motor generator. Okay. You have a stator. So stator has high mu r core. The stator core has high mu r and it has winding carrying current. It has winding carrying current. And you have a rotor. The rotor also has high mu r. It also has high mu r and it has winding or permanent magnet. So you see the gradation there. Correct? The first case of galvanometer, uniform magnetic field. And whatever is put inside the magnetic field is non-magnetic. Second is a case of an electromagnet, plunger, solenoid, whatever. Okay, what is put in the magnetic field is a magnetic material. Is a magnetic material and no current carrying conductor or this thing. The machine is the third level. Okay, in the stator's field, you will be putting a rotor. The rotor is made of highly permeable material, as in the second case. And as in the first case, it has current carrying conductors. It has current carrying conductors. You see the gradation. Now you have to see how do you deal with motor. How do you deal with that? As the problem became clear, it is because we are not understanding the second and third. We stop with one, BAL. We don't learn how to deal with the second and the third cases. That is why motors are challenging. That is why every motor looks different. If we understand this, we will be a long distance into electromechanical energy conversion principle. And from there, understanding any motor, modeling it, controlling it won't be that difficult conceptually. Still, like we were discussing during T, implementing is difficult. Building an inverter is difficult. Making it short circuit proof is difficult. Making it switch at high frequencies is difficult. Okay, losses, keeping it cool is difficult. Right? Reliability is difficult. EMI is difficult. Those are all other complementary difficulties in implementing it. But this is at least from the understanding point of view. Okay. Now, motor has a stator, and the stator has windings. The stator has windings, correct? And it has a rotor. I'm showing the rotor with an exaggerated air gap. This rotor also, for example, has, let us say, rotor bars, or it can also have conductors. So, the stator produces a magnetic field, the rotor also produces a magnetic field. And the books generally say that the torque is on account of interaction of the two systems. That is how torque gets produced. But on the other hand, the previous case of what? The plunger, it is not because of interaction of two. Only one magnetomotive force is there. That magnetomotive force is seeing difference in the reluctance. And it is because of difference in reluctance, it is working there. Okay. So we have put these three types. They are clear. Okay. So I'm not going to get into force directly. I'm still with how do you establish magnetic field. We establish magnetic field for case 1, that is galvanometer. I want to establish a magnetic field for case 3, that is electrical machine. Clear? That's what we'll do in the next 5 to 10 minutes. Okay. I cannot think how to do that. So, I did my old job, okay? Of putting a similar core. This is basically an inductor. That's basically an inductor. It's an air gap that is there now. I'm saying I'll put a rotor here. That is a magnetic material. Not a permanent magnet, but a highly permeable material. Its mu r is high. Let's say several thousands. Okay. That's what I'm trying to do. What is my job? I want to create a uniform magnetic field. So, and the magnetic field has to be radial. Here it is not radial. So, note my first step. Now I'm going to erase this. So I'm saying, let me make this curved. Let me make this circular. And let me put my rotor inside that. Now what will happen? The flux lines will be tend to be radial. Okay, the gap is not a rectangular gap. The gap is annular now. The gap is between two arcs of circle. This is better for me. Why? My conductors are there. The conductors are moving tangentially. I want them to cut the magnetic field perpendicular. That is, magnetic field has to be radial. The magnetic field has to be radial. So I'm going towards radial magnetic field. Now if I do this, okay. Now this is still small. It is not covering a larger region. So let me say, let me make my stator like this. What I've done, I've slightly expanded their mouth like this. I'm having the same rotor here. So what is it I'm doing? I'm making that fellow hug the rotor. Literally hug the rotor. So when you are when to hold something, you don't hold it like that. You're trying to hold that, correct? And there's a small baby, there's something or something very sensitive, something challenging. You try to hug. So now you will have radial things all over. You will have radial lines over a longer stretch. This is why you do extended poles. Okay. So now I'm trying to look at the flux path. So the flux line coming here, this flux line coming here has to go out somewhere. Has to go out somewhere. I'm thinking that it's better that it turns left here and it turns right here. So what happens if I say, let me go back to my blue. Instead of one side, I can make it two side. So some flux lines will turn this side and some flux lines will turn the other side. I drawn with green. Okay, the flux lines will go around, come back. So some line will go around like this. And you can see these edges are all unnecessary. These edges are unnecessary. From the top to bottom, I can provide a smooth semicircular path. I can provide a smooth semicircular path. So if I do that, what is this? A two-pole DC motor. Where are the windings here? Where are the windings here? Their sense of windings are current in this are in the direction that both of them will drive the flux in the same direction. So this will be radial. Okay. All these lines will be radial. They are very exaggerated. The gap is shown very exaggerated in drawing, as I've told 100 times before. So they will turn around, they'll turn around, they'll turn around. They'll turn around, turn around. So my request to teachers of DC machine, when we have discussed the construction of a DC machine, first let's make sure that the students can understand the magnetic flux lines produced by the DC field winding. So for students, I would say that once you know the construction, take a two-pole or take a four-pole motor and see how the flux lines will be inside that in a DC motor. DC motor is the simplest motor. Two-pole DC motor is simplest. For a two-pole DC motor, if some field winding current flows, don't worry about armature current yet. Don't worry about armature current yet. See how the field windings, how the flux lines will be. That will give you some clarity on what's really happening. This I can make it four-pole also. This I can make it four-pole also. So there will be north-south, north-south. So I'm not doing that. So what have we done now? What have we done now? We have shaped the magnetic path for electromechanical energy conversion. I have created a strong magnetic field in the air gap. I have created a strong magnetic field in the air gap, radial. Strong magnetic field. And it is a radial magnetic field. Where? Where? In the air gap. Is it clear? This is what I have done. Fine. This is one example of how do you establish magnetic field. Where did we start from? We started from Maxwell's equation, particularly Ampere law, and then we looked at Biot-Savart law for calculating magnetic fields. Further calculations have to be done using del cross H is equal to J. Solve them numerically. That's what you have to do. And we looked at how do you establish a magnetic field. So how do you establish strong magnetic field? Conductor becomes turn, and turn becomes a multi-turn coil. And after that, you introduce iron. So iron directs flux. and produces a strong magnetic field in an air gap. Produces a strong magnetic field in air gap. So you can place some measurement device in the air gap which requires constant magnetic field, and any kind of transduction measurement which requires a constant magnetic flux density can be carried out. But in the air gap, if you place some magnetizable material like an electromagnet, the situation changes. There the force is on account of reluctance. The force is on account of reluctance. Further still, you have a machine. Okay, machine has a stationary portion, has a rotating portion. The stationary portion has highly permeable material. The rotating portion also has a highly permeable material. And embedded in the stator is some winding that produces magnetic field. Again, rotor may also have winding or permanent magnet, which will produce a magnetic field. Okay, I am looking at how can we produce a magnetic field using the stator in the air gap. One example is here. One example is here. Is it clear? Okay. So now we have produced some kind of a structure. I have this is air gap, and this is my angle theta. What is my angle theta? As I rotate. Let us say theta is equal to 0. Theta is equal to 0 is between the two poles. So, is between the two poles. The flux density is 0. And what happens? The flux density sorry about that. What is this? This is the flux density. I have a magnetic field in the annular region, that is the air gap. Magnetic field B is a vector, but I am not worried about the direction. Why? The direction is taken as radial. The direction is radial. So I am not worried about the direction. This is really the radial component. When I measure that, what happens? When I measure that, what happens? I have a high flux density inside this pole region. A very high flux density inside the pole region, and that falls. Here, if it is positive, if the flux lines are coming in this direction, the flux lines are going out here. So if it is positive here, it is negative here. Okay. So I am having, this is under the north pole, this is under the south pole. So I am having typically a flat-topped air gap flux density waveform. I am having a flat-topped air gap flux density waveform. So what did I try to do? I tried to construct a way by which I can establish magnetic field in the air gap, and I have come to a construction that is typically used in the 2-pole or a 4-pole DC machine. And what I find is the air gap flux density is flat top. It is not sinusoidal. It is not sinusoidal. Do you expect anything? Okay. So this is the magnetic field is over. Up to this point, you have established the magnetic field, and somebody measures the magnetic field and shows this is what has come. Okay. But this is not the end of the machine. This is not the end of the machine. Machine means it should function. It should spin. It should produce torque. That is not happening. So what is the next step? What is the next step? Question is clear? Huh? Change the magnetic field where? No. The stator is now only active and it is producing magnetic field. So what should I do? I should do something with the rotor. I should do something with the rotor. Correct? So what do I do with the rotor? I should make the rotor produce another magnetic field. I should make the rotor produce another magnetic field. So if I have to make the rotor produce another magnetic field, what do I need? I will need some conductor sitting there. And somebody has to drive Somebody has to drive something through that. Okay. Okay. So let me say I can look at two problems. One is I can look at it in the motoring mode. If it is in the motoring mode, no matter whether it is motoring or generator, I will have this excited. The pole winding is excited. This kind of a B field is there. If it is motoring, I will feed power to the armature, and that will generate a torque. Will drive a mechanical load. Clear? If it is generator, there is some prime mover will drive the rotor, and because of that rotor, there will be induced EMF in the rotor, and that will feed the load current. Clear? So now let me assume the second thing. Let me assume the second thing. Let me say somebody is spinning my rotor. Okay. So now what I'm going to do is there is a rotor sitting there. I have a flux density around this like that. This is my PG. This is my theta is equal to 0. Okay. This is my theta is equal to 180 degree. Okay. It is like this. The magnetic field is there. I'm not drawing them. Okay. If you want, I will show the magnetic field lines coming like this. There are magnetic field lines coming like this, and there are magnetic fields going out like this, radially. This is how it is. It is a highly permeable material. For your information, there will be some shaft also inside. Shaft will be a not a permeable material. So the magnetic flux lines will actually go around this like this. There can be much better drawings, but I'm also in a bit of hurry. Okay. Yes. So magnetic flux lines are going to be something like this. These are going through the rotor portion. So now what I'm doing, I'm placing some conductors there. I'm placing some conductor there. And we know we want the conductor to be a turn. So I'm placing a turn. That's one green coil. That is one green coil. Next, let us say for another example, let me take blue color and let me say there is a blue coil. Two coils are kept there. Particular instant it is at this position. Okay. Now, for it to work as a generator, it has to induce a voltage. That means it has to induce an EMF. When will it induce an EMF? EMF is nothing but the rate of change of flux linkage. So flux linkage should change with time. That means I should understand flux linkage. I should understand flux linkage. The question to you is, what is the flux linkage of the blue coil? What is the flux linkage of the green coil? Question is clear? Green coil is 0. The flux linkage of blue coil is maximum. So let us say the whole flux is called flux per pole, pi p, and let us say n number of turns are there in the blue coil. The blue coil will have a flux linkage of n times pi p. The green coil will have a flux linkage of, the green coil's flux linkage will be 0. Why? This is the axis of the green coil. No line is passing through the axis. No line is passing through the axis of the green coil. Okay. Whereas blue coil, every flux line is passing through the axis. Every flux line is passing through it. So that is what you call as linkage now. Though the same amount of flux is being produced by the stator, the blue coil manages to link itself with all the flux lines. The green coil doesn't do with anything. So let me put one more color on one more coil. Suggest a good color. Yellow, purple. Here? Okay. Now let us say you have the coil here. What happens here? What happens here? You can take that even separately here. The lines are all going around like this. Right? There are many lines. I am not able to do that very, sorry. This makes it worse, sir. So, Then you have these lines like this. Sorry about my drawing. If I go on correcting it, it gets worse. There, some lines will be there. If I take some axis like this, okay, there can be some lines crossing like this. Some lines will cross. Some lines may not cross. Okay. Some lines will cross and some lines may not cross. So its flux linkage is lower. Its flux linkage is lower. So qualitatively we know for the same flux P, flux per pole, the flux linkage is lower. The flux linkage is lower depending on it is whatever dependent on the position. Okay, when they are aligned, entire flux. Unaligned, zero. I'm using the term aligned and unaligned for you to understand now. The question I'm now posing to you is, I have to go to psi numerically. That is n into phi p. What is phi p? Flux per pole. How do I calculate that? I'm now getting quantitative. I'm now getting quantitative. I want phi p. How do I evaluate phi p? If the current increases, the flux will increase. If the current reduces, which current? Field current. Right, but the field current is fixed now. And for this field current, how much is phi p? You are telling me a qualitative relationship between them. Phi p increases with IF, phi p reduces with IF. Agree with that. But I am trying to understand what is phi p? What is an expression for phi p? How do I calculate phi p? Huh? Try. There's no unique way, but tell me, yeah. Cross section of the pole, what? Is the question clear to you? The question clear to you? For the question is clear to how many? Just raise your hands. Is the question clear or not clear? Then why did you not tell me? What is the question? What is the question? Expression for flux per pole. Is that? Now the question is clear. Now try and answer. Okay, the clue is certainly there. So you have know the BAG. You know the flux density in the air gap. Flux density and flux are related, no? Flux density and flux are related. What is the relationship? Flux density has to be multiplied by certain area. But you will do that in a case where it's a constant flux density. For example, if you have a system like this, where your flux density is constant, you will multiply by area. But here, the flux density is variable. What did I say earlier? I have to do integration. I have to do integration with respect to what? Integration with respect to what? So, if I am saying here, what is the flux per pole? It is B. B is over this, right? I can either consider the stator or the rotor, doesn't matter, or the air gap in between. So, from here to here, this surface, that surface, I have to integrate it over that surface. Okay. If it crosses into that surface, it will also cross this line. Whether it crosses. Okay. So the integration has to be carried out over the surface. Yes, we have defined that. This is the next step of clarity. This is the next step that you have to do an integration. That it has to be a surface integration. And this is the surface. Okay. Once you have defined the surface, you can define an elemental length of the surface. You can define an elemental length of the surface. What is the elemental length of the surface? It has certain R, it has certain d theta. D theta is an elemental angle, that is R. And L is the length normal to the board. L is the length normal to the board. So, what will be the flux entering through this small area? BAG of theta multiplied by LR d theta. That is what? Flux. Is it full flux or infinitesimal? Infinitesimal. This is your next step. I know a surface. I know I have to carry out an integral. What is the integrand? What is the integrand? This is bg of theta. You have to multiply by LR d theta. Once you have determined the integrand, next is what? You have to do the integration. How to do that? And you need the limits over that. What is the limit over that? You have to do that 0 to 180 degree here. Okay, here this integration is over complete pole for you to get your flux per P. So what will you get as a result? You will get the area under this. You will get the area under that multiplied by something. What is this integration 5P you will get as an answer? You will get this area. Correct? Integral BAG d theta. Your answer is proportional to that area. Correct. This is 5P. This is 5P. And n times 5P is your peak flux linkage. N times 5P is your peak flux linkage. Okay. Now, this fellow is not going to stand at the same place. Let me use only my BAG of theta. Let me use my BAG of theta. I'm slightly simplifying it. This is 0, this is 180. And I have conductor. I have my conductor sitting here. So what will be the flux linkage of the red conductor? N times 5P. It will be the flux linkage of the red conductor. Now let me say I'll get a blue conductor. The blue conductor is here and here. They are always 180 degrees away, right? The forward conductor is at some theta, the return is at some 180 plus theta. Now for the blue conductor, what I should do? What should I do for the blue conductor? I'll try somebody who can do it. What should I do for the blue conductor to calculate that? What should I do for the blue conductor, Alok? Never fritter away your opportunities. Never fritter away your opportunities. The present is the best instant. The future is shaped by your present. Take care of your present. Future is shaped by your present. Don't be anxious about your future, but shape your present. Not doing adequately in your present is frittering away, and you're also frittering away your past gains. Please remember that. You're sitting here because of hard work. You're sitting here because of your hard work. You're sitting here because of your parents' hard work. Make best use of it. So for the blue conductor, what I should do? Flux linkage of blue conductor. Similarly, it is not 5P. It is some other number. It is n into some other number. What is that some other number? Let me take the blue color. What should I do for the blue conductor? That psi for the blue is n times some other flux. What is that some other flux? Integrate. Let me call this angle as some theta 1. Then this is 180 plus theta 1. Theta 1 to 180 plus theta 1. Of what? What should I do? The same BAG of theta. The same BAG of theta. That has to be multiplied by, this is BAG. How do I get d phi? LR d theta. Same integration, limits are changed. The limits are changed. So therefore what will happen? You will get some result. Now that will be proportional to this area. This positive area is gone. and this negative area is getting subtracted. Clear? Let me go for one more position. This is some theta 2, and this is also at 180 plus theta 2. So what is my psi yellow? What is my psi yellow? Same thing, n integration from theta 2 to 180 plus theta 2. This is multiplied by BAG of theta r d theta L. I just have to do this. So further white area is gone, positive area. Further negative area is added up. Further, but this may not be 0. When it comes to 90 degrees, when I look at 90 degree, then totally 0. The area is totally 0. So it is maximum at n phi p at 0. When it comes to 90 degree, it becomes 0. What is the shape? Depends on the actual BAG of theta. Depends on the actual BAG of theta. Okay, this waveform is a little difficult to predict, but you can take simplified version. For example, you can take the BAG of theta as a quasi-square wave. You can take that as a quasi-square wave and do this exercise. I would encourage students to do this exercise, very highly. You take that as a quasi-square wave and try to do how your flux per pole comes. That is feasible and that will be useful. Okay, all right. So I've got my psi p because of that. We know psi p is varying. We know psi p is varying with what? The position of that. The psi p was high at 0, it was n psi p, n times phi p. At 90 degree, it became 0. Some way it became, right? Something like that. I don't know what. That you have to calculate and come down. And in this some way, it will go up like this also. But this is not sinusoidal. This is not sinusoidal. Had BAG of theta been sinusoidal, then the integral of a sinusoid is a sinusoid. Then an integral of a sinusoid is a sinusoid. Had BAG been sinusoidal, then flux would have been sinusoidal. Why? Integral of sine. Integral of sine is cos. That's again a sine function of the same frequency. Only the amplitude and phase of the sine change. Only amplitude and phase of sine change. Did I ask a question? Why do they use sine waves for generator? The very first session. What is the answer to that? Sine remains a sine. That is the speciality of sine. You integrate, it is a sine. You differentiate, it is a sine. Second derivative, sine. Third derivative, sine. Fourth derivative, sine. Any number of derivatives, sine remains a sine. That is the speciality of sine wave. That is the smoothest waveform. Sine is nothing but a projection of a circular motion on particular diameter. Circle is the smoothest polygon. Circle is the smoothest polygon. Circular motion is the smoothest motion for changing direction. It always changes. You don't even know that it is changing the direction. Okay, circle is the smoothest polygon. Its projection on the diameter is the smoothest function, sine. So why do you need it in power networks? Why do you need some function like that, which is always smooth? Why do you need that in the power network? Speciality of sine is correct. Why is it useful for power network? The power network has inductances and capacitances. The power network has inductances and capacitances. They will have the effect of integrating or differentiating this. So if you imagine a network with inductors and capacitors, the best supply for that is only sine. Okay, that is only at one level. There are other things that are very useful about sine. When you go from single phase to three phase, when you go from single phase to three phase, again its utility increases. So that's something, bear it in mind. We'll come back to this. So this theta, what is happening is, it is changing with time. This theta is changing with time. It is some omega, okay, t or t minus t naught. This is changing with time because it is rotating. Because it is rotating. Now what I should do, I should differentiate this. What is my back EMF? What is back EMF? d psi by dt. d psi by. So the flux linkage is differentiated with respect to time. Originally what I am doing, the air gap flux density is integrated with respect to space. The flux linkage is differentiated with respect to time. But the space and time are not unconnected. The space and time are not unconnected. Theta is proportional to time. It spins at a constant speed. Therefore, theta and t are equivalent, related by omega. Therefore, what happens? You integrated and came to something. If you differentiate it, you will go back to the same. You will go back to the same. So, what will you get as the output of the induced EMF? The same waveform you will get. The same shape waveform. The same shape waveform. So, whether I look at the blue or the red or the yellow, all of them will be producing an induced EMF that has the same wave shape as what? Air gap flux density. In fact, in an electrical machine, there is no direct way of finding out how the air gap flux density is other than by rotating it. Somebody gives you a machine that has a field winding or a permanent magnet. You don't know how the air gap flux density distribution is. The best thing that you have to do, rotate the machine and see how the induced EMF is. And the induced EMF will also show the variations in the flux density due to slots and other things. Okay, that will also show that now. So that is now. So what have we come to? Your flux density, that is as a function of angle. Flux density as a function of angle. From there we went to flux linkage. And from there we went to induced EMF. What is the wave shape of the induced EMF? Same as the flux density. Had the flux density been sinusoidal, the induced EMF will also be sinusoidal. If the flux density is trapezoidal, the induced EMF will also be trapezoidal. The same wave shape will come out of it. So both of them may have their advantages and disadvantages. What would be the advantage of a sinusoidal flux density? What would be the advantage of sinusoidal flux density? It is sine wave shape you like. If this fellow is a generator, if this machine is a generator and somebody wants sine wave, you can produce sine. This will not happen in DC. Of course, you're going to get only DC here, right? We have not put the commutator rate. Okay, we are going to get. So, if it is a generator, you normally prefer a sine voltage because it has to feed loads. But if it is not a generator, if it is in a motor, okay, this waveform is better than sine because you know Fourier series, right? You know Fourier series. What is the fundamental component of this waveform? The fundamental peak will go above this. The fundamental peak will go above this. The peak of the flux density is limited. Why? Because you have iron. Everything has limited capability. You can carry 20 kg, he may carry 15 kg. The porter can carry 30 kg. Porter cannot carry 600 kg, 60 kg. Correct? It has its limit. It can be 1.5 Tesla. You cannot cross that. For that 1.5 Tesla, you can create a higher sinusoidal peak. Okay, don't disregard non-sinusoidal waveforms. The non-sinusoidal waveforms can pack a higher fundamental component for the same flux density. Take a square wave, plus V minus V. What is the fundamental component of a square wave? 4V by pi. 4V by pi is greater than V. Similarly, a trapezoidal waveform or even a quasi waveform, trapezoidal waveform particularly, can give you higher peak of sinusoidal flux density. So when it can pack a higher peak, it can deliver greater torque. It can deliver greater torque for the same size. Okay, that is why in brushless DC motors, it is chosen to be non-sinusoidal. There are many reasons. And the DC machines really work like this. In the DC machine, you are not concerned about sinusoidal voltages. So what are you going to do? You're going to produce DC. What are you going to do with DC? There are different fellows. They will be producing this waveform. We'll just quickly close that here. This page, okay. Let us say all these fellows are producing some waveform. Okay. Let me finish. So some waveform. Now let me draw trapezoid. Okay, for me easy to draw. So this fellow, let us say, produce a trapezoid. This is one coil. There is a next coil. This coil will produce some trapezoid. And it goes on like that. I'm not drawing the subsequent ones. The third fellow will produce some other trapezoid. All of them are just phase shifted. All of them are just phase shifted. So it's not trapezoidal, it's a smoother version of this in a DC wave. What do? You put a commutator. By doing the commutator, what do? You rectify this. You rectify this and you add them. You rectify and you add them. So when you rectify and add them, what happens? All of them are positive. So the red is positive, black is positive, blue is positive, and more such waveforms are positive. And when they are added, all their DC components add up. All their DC components add up. What happens to a ripple? Ripple is all phase shifted. They cancel out. The ripple is all phase shifted. They'll cancel out. So despite having a highly non-sinusoidal flux density distribution, DC machine works nicely. Clear? I am not getting into the details of commutator. I leave that to you read. I am telling you two things functionally that a commutator does here. Rectifies. So all these rectified EMFs are added. A set of these rectified EMFs are added. When these rectified phase shifted EMFs are added, what is happening? All their DC components get added up. And they all have ripple. What happens to the ripple? When they have phase shifted ripple, what will happen, Alok? The ripples, when they are phase shifted and you add, what will happen? The ripples will reduce. And they can perfectly become zero. In fact, three-phase power also. Okay, power, voltage and current. Power is what? Product of voltage and current. Let us say voltage is sin omega t, V sin omega t. Current is I sin omega t minus phi. If you multiply the two, what you will get? VA times. What is the resultant frequency? Omega t into omega t minus phi. So add and subtract, what you will get? 2 omega t minus phi and phi. Phi is DC, double frequency. If you multiply sinusoidal voltage and sinusoidal current of the same frequency omega, the power has DC component and double frequency component. Okay. If you take R phase, Y phase and B phase, all their DC components will add. What will happen to the double frequency component? They will cancel out. The double frequency components will cancel out. The cancellation of the double frequency components is what makes the three-phase power supply even more advantageous than the single-phase sinusoid. Fine. The similar thing, ripple cancellation, happens in a DC machine. This ripple cancellation is attempted in what is called carrier interleaving that you do in advanced power electronics. In carrier interleaving, you try to have every phase will have a ripple. You will have phase shifted ripple and you will make sure that they cancel out each other. This idea is used in various places. Okay, that is an old idea, comes in DC machine. So you will get a back EMF. I'm not getting into the details of the back EMF expression. Okay, so we have come to a particular point from where we started. Magnetic field, right? Evaluating magnetic field, shaping magnetic field, creating a strong magnetic field in a rectangular air gap, creating a strong magnetic field in an annular gap. That's a radial magnetic field. And what happens when you put a coil there? What is the flux linkage of a coil in the air gap? What happens to the flux linkage of the coil when the coil rotates? And what happens to the induced EMF? And if you put multiple coils as in a DC machine, what happens? So we have come up to the level of DC's output now. The only thing next we have to do is now there are other equivalents that we have to look at, right? One is we have to look at the torque, what really happens to the torque in a machine. And from that particular point, having understood, we will go through machines. Okay, sequence of them, DC, and from DC we'll probably go to permanent magnet DC. Okay, and there we'll go to brushless DC. So we'll see there may be array of machines. We'll see what is common and different about them. That is somewhat serious discussion on DC, more in-depth discussion. Okay, this should give you an idea on how to deal with many other cases. And relying on that, we'll look at a spectrum of machines, about 5-6 variety of machines, like field-wound DC, permanent magnet DC, brushless DC, PMSM, synchronous machine, induction motor, etc. Okay, we'll look at a spectrum of machines. From that particular point, we should be able to come up with some other ways of controlling. So let's see how much we can do. Thank you. So we should convene by. Okay. Today we're a little short on time. So what happens in this kind of a case is just taking it like this, right? You will have some waveforms like that. Another phase will just produce something phase shifted like this. Okay. Sorry that I'm not. Maybe I will erase and then do this all. Okay. So because the effect of accommodator, you will be rectifying it like that, and another phase may produce something like this, which will be a little phase shifted from this, go up this. And yet another phase will be further, phase shifted. So I'm just drawing a series of, don't worry about the exact wave shape, but see that they are all some rectified versions of a periodic waveform, alternating waveform. And all the waveforms have a DC component. The red has a DC component, the blue has a green, the black has a DC component. And these are all added. Some n number of these are added, which are all phase shifted. All those versions will have the same DC. The DC will add up. But the phase shifting, one will be phase shifted from the other by 30, another one will be by 60, another one will be 90, another one will be 120. So when you have several of them, the sum will be 0. Just as you had second harmonic power in the single phase case, right? R phase second harmonic is 0 degree. Y phase is at 120 degree. B phase is at 240. They are adding to 0. So similarly, if you have components that are 90, 180, 270, 360, they will also get cancelled out. Similarly, if you have components which are phase shifted by 60, 120, 180, 240, 300, 360, they will also get cancelled out. So these ripples cancel out and they add up. That is why, though the flux density is like that, though the induced EMF is like that, the DC output is beautiful. The DC output is beautiful in a DC machine. And the DC output is really high because this is non-sinusoidal. Had it been sinusoidal, the peak would have been limited to this value. Because it is non-sinusoidal, right? Let me take the same color. If I take the fundamental component of that, the fundamental component will actually go higher than that. That's the point I was trying to say. Now it's not the fundamental, you don't have to worry. What you have to be more concerned about is the DC component. The DCs are getting added up. So let me put that, sorry. If I have rectified a sine with some peak, that will have some DC. Now, if I am rectifying the same peak, this, which will have higher DC, let's say this is 1, this is also 1, which will have higher DC, the second one will have higher DC. So the non-sinusoidal waveform, like trapezoidal waveform, has a higher fundamental component, and its rectified version has higher DC component. Okay, as you can see, that trapezoidal waveform's DC component is much higher than the DC component of the sine. The sine, if it is 1, 2 by pi will be the DC component. Here this will be much higher than 2 by pi, the second one. Okay, so it is not a disadvantage, it really becomes an advantage. So this is how you do with your back EMF. And now when this back EMF is there, next is there is load. At the output there is a load, and therefore there is current is flowing. So what is going to happen with the current is, let me draw a developed view. Okay, and this is North Pole, this is South Pole, which basically means the conductors, these are all the flux lines are like this. Flux lines are like this. The flux lines are like this. And there are conductors sitting there. There are conductors. Okay. All these conductors are moving at a uniform speed omega. It is not that this conductor is moving faster, this conductor is slower, because all of them are having the same rotational motion sitting on the same periphery of that. So all of them are moving. Okay. So what really happens is this is a high B in one direction. That has got a high B in one direction. This has got a high B in another direction. Okay. And the direction of the flux line is different. The movement is the same. And therefore, the induced current will be in a different direction. The induced current will be in a different direction. So under one of them, if it is cross, other one will be dot. Okay. So this will be one possibility is this all can be dot and all this can be cross. Another possibility, depending on if you take the exact thing, whether it is this way, that way, or all this can be cross and all this can be dot. So the conductors under one pole will have current in the same direction. It could be this direction or that direction. That can change with rotation or that can change with something. So now that is the next thing that we'll now look at. It will be one way in motoring, it will be another way in generating. It will be one way in motoring, it will be another way in generating. Okay. So we started off with how do we establish a magnetic field, which we did, taking this particular case. And then what we have done, we put some conductor in the armature, in the rotor, and we studied the flux linkage. And then as it rotates, we studied how the flux linkage is going to change. Correct? And from that, we try to derive how the back EMF is. And after the back EMF comes your commutator that gives a complete DC, adds up all the DC in the coils and subtracts out all the ripple, cancels out, and provides a very high value of DC. And that DC is fed to the load. So the load draws this current. That current has to flow through the armature. Okay. That can be two parallel paths or P number of parallel paths. That depends upon how the armature is really wound. There can be different kinds of winding connections. Okay. The armature can have multiple parallel paths. So through all these paths, the load current is flowing. So the load current, if it is, let us say IA divided by the number of parallel paths, if you call as P, there will be IA by P current will be flowing through each one of them. IA by P will be the current flowing through each one of them. Okay. And equal current flows through all of them. Equal current flows through all of them. So if I take this situation right under that, I'm drawing the same conductors right below this. So I'm saying that all these are having dot. And probably there's nothing here. And all these are having cross. And all these currents are equal. All these currents are equal. I should visualize the MMF for this. I should visualize the MMF waveform for this. So what is this? This is in the armature. This is in the armature. So for simplicity, let me just draw this like this. And this is the air gap. This fellow is going to drive some current, some flux line across the armature. There may be flux lines which does not cross the air gap. That doesn't matter. That is what is your harmonic, what you call leakage and all that. But there will be some which will go here. Okay. If I take this dot, how will be the flux line around a dot? Circle, right? So let me put that anti-clock circle. The slots won't be like that. The slots will be shaped differently. But I'm not worried about the detail. I'm worried about the concept, right? If it is like this, see, this is not crossing. This is not crossing the air gap. You understand? But some of these lines, when they are together, they will cross the air gap. There will be line around all these three. And what will be the direction? Anti-clockwise. So here it is crossing in this direction, here it is in the opposite direction. Okay. So this is almost like, if you look at from the stator point of view, this is like the south pole, this is the north pole. They are not exactly under that. Okay. And if you look at which one is the biggest one, maybe I did a slightly misleading one. Okay. Let me. The strongest of the lines will be when it covers all the dot points. When it covers all the dot points. So ignore this. There is a, maybe I should have slightly redrawn that differently. I may look at some line like this. Okay. I may look at, it should have been symmetric. Okay. Had I drawn 3, that would have been better. So this would be there and that would be higher. And if I see this and that, here what is there? It is enclosing lower number of ampere conductors. It is enclosing higher number of ampere conductors. And both of them are crossing the same air gap. So which is higher H? Which is higher H? So outer one is higher H. Why? The current is high. How high is the current enclosed? It can be some IA divided by P. That is the number of, that is the current through each one of them. And how many number of conductors will be there? If you take Z as the number of conductors, this is the number of parallel paths. Let's give some other, what is the convention you use for parallel path? Okay, you put IA by A. You put IA by A. And there are totally Z conductors. Z by P will be under one of them. So this much is the armature ampere conductor. This much is the ampere conductor. This ampere conductor is across 2G, twice the air gap. So that is going to be your MMF. So following the old idea, I'm taking this as my contour C. I'm taking this as my contour C. So what do I have? Integral H dot dl over the contour. And this integral H dot dl over the contour has two components. There is an iron portion, there is an air gap portion. I'll say this is approximately integral H dot dl over air gap. I've ignored the iron portion. So now if I do that, what am I going to get? Current enclosed. This is going to be current enclosed. And half of that here, half of that there. Half of that here, half of that there. And this is a positive direction, this is negative direction. So this exactly happens at the interpolar region. This is other interpolar region. So what will happen under one particular pole is, this fellow will be the negative peak and this fellow will be the positive peak of the armature MMF, and the armature MMF will go up in steps like that. Okay. Sorry, I should. Let me redraw that. So the armature MMF will go up from negative value to positive value under one pole, and under the next pole, the armature MMF will not clear. Huh? Face says not clear. Huh? Every time there is a gap, there is an increase in the conductor. Okay. So many steps. There are too many steps that this can be approximated as a triangle. This can be approximated as a triangle. Okay. So I'll come to the detail of this. If this is not dot and cross, instead it is cross and dot, what will happen there? This whole fellow will be ulta. You understand? So The armature MMF is 90 degrees away from the main MMF, from the main flux. The armature MMF is peaking at the interpolar region. The armature MMF is peaking at the interpolar region. Whether positive peak or negative peak is the question. You understand? In generation, it is like that. In motoring, it is the other way. Okay. And the other way, if you look at it, is this peak, and there's a direction of rotation. This direction of rotation. There are two magnetic fields. One fellow set up by the stator that shows as BG, and it has a peak somewhere. Where will have its peak? Right below the pole. Right below the pole. Let's say under North Pole. One. If you take the armature, it will create a peak MMF. Where will it be? At the interpolar region. Between this North Pole and the next South Pole, or between North Pole and the previous South Pole. Correct? So they are going to be 90 degree leading or lagging. If the rotor magnetic field leads the stator magnetic field. If the rotor magnetic field leads the stator magnetic field, means rotor is the boss who is pushing. That means power is flowing in through the rotor. That means from the prime mover. That is from the prime mover. It is a generator. If the stator magnetic field is leading by 90 degree and the rotor magnetic field is trailing by 90 degree, that means the stator is calling the shot. The power is flowing from the stator. That is from the electrical power supply and going out through the rotor. That means motor. There is no time to go through steps, conventions and all that. But I want you to catch the essential steps that you have to see. Okay. So what did we do prior lunch? We went into flux linkage. We went into induced EMF. Correct. Unless the second magnetic field comes, we cannot go to torque. Now we are trying to handle the second one. The second one is from the armature. Very simply, all the conductors under one North Pole, if they are dot, conductors under South Pole will be cross. And they will change if it is motoring or generating. Okay, you can understand the same flux direction under the pole and the same movement. Motoring or generating, the induced current will change. It is very obvious to you. Right? And when that changes, what happens? The armature MMF waveform flips. What is a square triangular wave gets inverted. From motoring to generating, the armature MMF simply inverts. When it inverts, it would have been leading the stator by 90 degree. That becomes lagging the stator by 90 degree. If the stator magnetic field is leading, that means work is being by the stator side. That means it's motoring. If the rotor magnetic field is leading, then that means work is being done by the rotor. That means it's a prime mover driven generator. Clear? The principles have to be clear. This is across the motors. There's a stator magnetic field and rotor magnetic field. Many machines produce this. It's a DC motor, it's an induction motor. Many of these machines, synchronous motor, PM synchronous motor, many of them have stator magnetic field and rotor magnetic field. Except switch reluctance machines or reluctance machines, which have no windings on the rotor. Most machines have winding in the stator. Again, a winding or permanent magnet in the rotor. There can be permanent magnet in the stator also. Both are possible. Correct? You don't have both permanent magnet. What I am saying is stator can be winding, rotor can be winding, possible. Stator permanent magnet, rotor winding, possible. Stator winding, rotor permanent magnet, both combinations are possible. But both permanent magnets don't exist. Both permanent magnets don't exist because you cannot control. You cannot control. That can probably do for some special thing that you can create up. You can always come up with something. There is no such thing as impossible, as long as the basic laws are not violated. You can do that. But none of the common well-known motors will have that. That is one. And then many other motors, I'm just going to create this thing to go into that. There are motors which will have exclusive field windings. There are motors which have exclusive field winding and which create a magnetic field. And then the other one will be called an armature. And there may be magnets, instead of the field winding, will have permanent magnet to create the field winding. And there may be motors which does not have a separate field excitation. For example, induction motor. How the induction motor generates is a little different. That's something that we have to sit and understand. So many of these that I said can be generalized for motors that have windings or permanent magnets sitting on those two cases. Okay. So now these two magnetic fields are always 90 degree. They are at 90 degree with each other. Okay. It is 90 degree electrical. So if they take a two pole case, then this 90 degrees like this. So what is happening is one magnet is like this, whose axis is at 90 degree. Another magnet is there whose axis is at 90 degree. What will the magnets want to do? They will want to align themselves. The magnets will want to align themselves. Allow me to rotate and align with that so that we can create stronger magnetic field. We create a stronger magnetic field, but they will not be allowed to align. They will not be allowed to align. What is happening here? The stator is fixed. That is your B of theta. And what will happen to the rotor? The moment it crosses the north pole and goes under the south pole, dot will become cross. That's all. So the direction of the stator magnetic the armature magnetic field cannot change. You understand? By intelligent operation, it is such a way that both are at 90 degrees. And there are some complications. They'll say I have a brush and advancing. My sincere suggestion: don't get into all that until you have mastered the basics of what needs to be done. In very simplicity, that is all it is. Stator produces a field winding produces a magnetic field. The rotor also produces a magnetic field, and that is leading or lagging by 90 degrees. The rotor magnetic field is always at the interpolar region, peaks at the interpolar region. They're 90 degree. Okay, and that is what it creates. So because of this armature MMF, the main field will change. Okay, there's saturation and armature reaction. That's again I'm not getting into because I want to focus on the quintessential electromechanical properties. So these two are stationary. The armature is rotating, but the armature's magnetic field is stationary. Why? Rotates. But if the conductor, call the conductor as A under north pole goes to under B south pole, dot becomes cross. Then conductor B, north pole to south pole, dot becomes cross. No matter whether the conductor is A, B, C, D, P, Q, R. If it is under north pole, it will be dot. Under south pole, it will be cross. You understand? Therefore, even though the armature is rotating, even though the conductors are rotating, the magnetic field doesn't change. The magnetic field doesn't change. It is stationary. The DC motor produces two magnetic fields which are stationary, though the rotor is rotating, and they are at 90 degrees. And they produce torque. And torque is again a kind of a vectorial function. It's a scalar product of two quantities. One quantity representing the stator magnetic field and another quantity representing the rotor magnetic field. And the vector product is highest when the angle is 90 degrees. The vector product is highest when the angle is 90 degrees. And that is what it produces. Okay. Is the DC motor thing clear? Yes? Okay. So, with this, I'll draw that. This is it's a representation of your stator magnetic field. And this is a representation of your, stator magnetic field. This can be your rotor magnetic field. In the case of DC machine, it is stationary. Okay. But both can rotate. Both can rotate. Say at the same synchronous speed. Then also it will produce a torque. Then also it will produce a torque. Okay. So with this, I come to the other end of the spectrum, a synchronous machine. Synchronous machine. So what happens in a synchronous machine is you have three-phase windings. You will have a three-phase winding. Okay, or I think I'll have to say how the winding comes in there. How is this produced in a synchronous machine? How is this produced in a synchronous machine? You have three-phase windings. Okay, I actually need some work to get there systematically. You have three-phase windings, and these windings are fed with three-phase sine currents. Windings are fed with three-phase sine currents. This produces a revolving magnetic field. This produces a revolving magnetic field. Okay, it is actually good to go in there and see what do you mean by winding. These windings are sinusoidally distributed windings. Okay, we have to understand that. And what will be the effect of one sinusoidally distributed winding? What we'll do is you will provide a constant current. Okay, the MMF will be sinusoidal. The MMF will be sinusoidal. Like we got triangular MMF in DC machine, this will be sinusoidal. Along the so-called axis of the winding, it will be having a peak, and after that it will vary co-sinusoidally. That is for every winding. Similarly, Y phase will produce another sinusoidal distribution around Y phase axis. B will produce again another sine axis. If you add two sine, the result is a sine. If you add two phase shifted sine, the result is sine. Similarly, if you add two sine which are sinusoidally distribution in space, that is also resultant is sine. So all the sinusoidal distributions actually result in sine. And when they are along R axis, Y axis and B axis, and the three currents are sinusoidal, they actually add to become one vector. They become a revolving vector. If time permits, I'll take you into the details of that. So right now, but anyway, you would have studied this in machine and everywhere, motor control, three-phase windings. Okay, these are distributed winding. These are sinusoidally distributed winding. And these are three-phase currents. When you feed into them, you produce a revolving magnetic field. If the frequency of the current increases, the revolving magnetic field will become faster. Okay, that is how it works. So that is how the stator produces a magnetic field. This is true about synchronous machine. This is true about induction motor, wherever we have three-phase windings. Okay, now what happens in the rotor? What happens in the rotor? In the case of a synchronous machine, okay, the rotor has one coil. Okay, this need not be one conductor. There can be number of conductors. Because of this will be driving a flux in this direction. This will be and this is the so-called axis. This is the so-called axis of the winding, and this will rotate. This will rotate. At what speed it rotates? Synchronous speed. So there is a coil that produces a stationary magnetic field with respect to the rotor, but the rotor rotates at synchronous speed. The rotor rotates at synchronous speed in a synchronous machine. Therefore, it is the two are at the same frequency. The two are at the same frequency, and they produce a torque. What interestingly happens in a synchronous machine is, in the case of a DC machine, it is stationary. This fellow is constant, and this fellow is variable. Let me draw that separately. Let us say this is my stator magnetic field. See, I'm being a little fuzzy here because I'm not defining what, but whatever represents the stator magnetic field strength, it is in that axis. And the rotor magnetic field is dependent on A. It is dependent on A, IA. This can be like this, or this can become like this. If I increase the current, it can further become like this. This is controllable. This is variable. This is variable. This results to variation in torque. This results in variation torque. Assuming that this torque is a cross product of two quantities. One quantity represents the stator magnetic field, that is constant. Another quantity represents the strength of the rotor magnetic field. That quantity is proportional to armature current, and that is variable. And they are always at 90 degree. Vector product depends on vector 1 magnitude, vector 2 magnitude, angle. Vector 1 magnitude is constant. Vector 2 magnitude is variable. Angle is constant. Angle is constant. That is DC motor. Okay. Now, if you go here, this is the revolving magnetic field of the stator, and this is the revolving magnetic field of the rotor. But in this case, the stator magnetic field and the rotor magnetic field will be at certain angle, that you call delta. This is also constant, this is also constant, but delta is the variable. The delta is the variable. The value of the cross product of two vectors can be changed by magnitude of one or magnitude of two or angle between the two. Magnitude of one is constant, magnitude of two varies, and angle is constant in a DC motor. In a synchronous machine, magnitude of one is constant, magnitude of two is constant, the angle between the two varies. The angle between the two varies. That is why it is called load angle or torque angle. The name itself is load angle or torque angle. That's synchronous machine. Here, both the magnetic fields are rotating at synchronism. Both are at synchronous speed. Okay, because they are in this thing. So, what happens in an induction motor also? What happens in an induction motor also? Both the stator magnetic field and the rotor magnetic field are spinning at synchronous speed, and they are roughly 90 degrees. Okay, it would take a while to understand how we go about doing that. Maybe I'll finish the induction motor also now, because I think doing the fundamental machines is more important. So, we are now talking of the case of an induction motor. Okay, I'm looking at a developed view, and I'm having magnetic flux. How is the magnetic flux? Sinusoidally distributed. Let me attempt that. Do you understand what is this? Stator, rotor, gap. This is, I am attempting to draw a sinusoidally varying flux density. The flux density is high, top to bottom. Flux density is high, bottom to top. You get that? This is a picture. If you take a few more minutes and draw that, you can do a better job. This is what? Sinusoidally distributed flux density in an air gap. Okay, that is how it looks. There are lines, lot of lines cross the air gap at where it is the peak under a pole. Under the other pole, lot of lines cross in the opposite direction, and the density of the lines vary. At the interpolar region, hardly any lines cross. They vary in a sinusoidal fashion. What I have attempted to show is the density of the lines are varying in a sinusoidal fashion. It is not accurate, you can draw better, but even if you draw better, still you will have to understand what is that. It is in a sinusoidal fashion. Okay, who has created that? The stator, the three-phase currents flowing through the stator has created that. And these fellows are moving at a speed of omega s. These fellows are, and this is the rotor that is moving at a speed of omega r, both in the same direction, omega r being slightly less than omega s. So what happens? You have conductors sitting here. The conductors are uniformly spaced. These are who? They are rotor bars. There are rotor bars. They are uniformly spaced. But this fellow is cutting a lot of lines. This fellow is cutting very few lines. This fellow is cutting a lot of lines in the opposite direction. This fellow is cutting very few lines. Further, some fellow will be cutting a lot of lines in the opposite direction. You understand? All of them are moving at slip speed. Or rather, the rotating magnetic field is moving past this at slip speed. The magnetic field is moving at omega s. The rotor conductors are moving at omega r, which is effectively the stator magnetic field is moving at a slip speed with respect to rotor conductors. Is it clear? Example, synchronous will be 50 hertz. rotor speed equivalent is 49 hertz. Slip speed is 1 hertz. So these fellows are moving at a frequency of 1 hertz equivalent. Clear? Very low frequency. And all of them are moving in the same direction in same director. But the flux line here is positive, the flux line is negative. So what will that mean? The induction is in the other direction. The induced EMF or current are in different directions. Okay. Will there be an EMF induced in this conductor? Yes. Why? It is cutting the flux lines. It is cutting the flux lines. Here I'll tell you, there are two equivalent approaches are studying induced EMF. What I took you through earlier was flux linkage of a coil. Flux linkage of a coil. And then rate of change of variation in flux linkage with time. Induced EMF. The other way you can look at is conductors. You can look at conductor, the flux cutting by conductor. If a conductor doesn't cut any flux, no EMF. There is flux, the conductor doesn't move, no EMF. Conductor moves, but there is no flux, no EMF. There is a lot of flux lines normal to the movement of the conductor. EMF is high. EMF is high. Lot of flux, the conductor moves very slowly. EMF is low. You understand? Lot of flux in the opposite direction and the conductor moves very fast. EMF is in the other direction. Correct? Okay. So going by that, this fellow is cutting a lot of lines within a unit time. This fellow is cutting very few fellows in unit time. And they are at the same speed. So this EMF will be high. This EMF will be high. So let me put that. This fellow's EMF is high. What happens to this fellow? It's a little less. What happens to this fellow? Less. What happens to this? Much less. Okay. This. Huh? Yes. And from here, this fellow, the next fellow, then from here to here. I think, yeah, I have not drawn that exactly equivalent to that. I will. Okay. No problem. No, that is why I didn't want to draw that. I wanted to stop there. But since you're saying that, okay, because I knew that this problem was coming up. Let me stop here. This is sinusoidal. This is sinusoidal. Why? The flux density distribution is sinusoidal. The flux density distribution is sinusoidal. Spatially, somewhere it is at the peak. Somewhere it is at cos 10 of the peak. Somewhere it is cos 20 of the peak. Somewhere it is cos 70 of the peak. Somewhere it is cos 90 of the peak, that is 0. All the fellows are moving at the same speed. And therefore, the fellow who is cutting where the flux density is highest has the highest induced EMF. Next is lower, lower, lower. And this is one sine, quarter of a sine. From here to here, what happens? Okay, this is my horizontal axis. So these fellows will be clear. What will happen subsequently? The pattern will go like that. So the EMF induced in the conductors of the rotor bar are sinusoidal. The first conductor will have some amperes, call it I. The next conductor, that may be, let us say, 5 degrees away electrically, that will have I cos 5. The next conductor, another 5 degrees away, will have I cos 10. The third conductor will have I cos 15. The sixth conductor will have I cos 60. Okay. The 12th conductor will have I cos 70. That is how EMFs are. It is discretized sine waveform. It is a discretized sampled sign. Clear? That is how it is induced EMF. Now EMF is induced in these conductors. EMF is induced in the conductor. Earlier we took the approach of rate of change of flux linkage with time of the coil. Flux linkage is always associated with a coil. Here we are taking the approach of cutting the flux lines. Cutting the flux lines by a conductor. Both are equivalent. Okay. So this is how the induced EMF are. Will current flow through the conductors? Yes. Why? Shorted. The trouble here is, the first time when I thought about this is high EMF. This is zero. This is lower, 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 zero. And the two sides, they are shorted. The two sides, they are shorted. So what does it mean? One fellow has an induced EMF V. Another one has V cos 10, cos 20, cos 30. Another one is V, whatever, minus. So it is between plus V and minus V, many conductors. All of these are parallel. All of these are parallel. What can be in parallel? Only equal voltages. Unequal voltages are in parallel. Unequal voltages are in parallel. Can you do that? Safe landing from heaven. So if you connect battery, one having 12 volt, one having 10 volt, one having 8 volt, better don't be there when a connection is made. Make the connection remotely using a robo. So what is happening here? The internal resistance is what is reducing. They all have internal resistances. These are all not EMF sources alone. The conductors have certain internal resistance. So the two sides, they are shorted. So all of them are divided by their resistances. So you will have currents. You will have currents. How will the currents look like? The same way. The currents will look the same version. The currents will look very similar. So the currents are also sinusoidal. Currents are also sinusoidal. This is sinusoidal current distribution. This is sinusoidal current distribution. In your courses, you would have studied about sinusoidally distributed winding. When you pass a DC through that, the flux in the air gap is sinusoidally distributed. This is current is being distributed sinusoidally. Okay. This sinusoidal distribution of current, what it will do? What it will do? This produces a magnetic field. It is like your armature current. In the DC machine, the armature current, all of them are equal. Here, they are sinusoidally varying. They are sinusoidally varying. Let me go to the next one. So let me say, I am having some sinusoidal current like this through the conductors. I am having sinusoidal current through the conductors. What will be the resultant air gap MMF? What will be the resultant air gap MMF? Or let me change this. Okay, for our convenience, let me draw a sine wave. Okay, let me draw. Okay, you are capable of understanding. Let us say this is the conductor. This is how the conductor currents are in the rotor. What will be the EMF? The MMF due to this? From this point to this point, the current is positive. The MMF will increase, or it will be in one direction. And from the positive zero crossing to the negative zero crossing, it will fall down. Okay, so this will increase from here. It will be zero here, be reaching a maximum here. There. So this fellow is 90 degree. This fellow is 90 degree. 90 degree with respect to what? 90 degree with respect to the current. And that current is what? 90 degree with respect to the EMF. And that EMF is what? The stator magnetic field. Stator magnetic field. Okay. So this rotor magnetic field is at a 90 degree angle with respect to the stator magnetic field. So two vectors, the vectors are at 90 degree, which is the best thing for you. That is the best thing for you. Just like in a DC machine, very surprisingly, this gives you two vectors at 90 degrees. What will happen with the current inverts? What will happen with the current inverts? The red current inverts. The black will invert. If it inverts, what will happen? If this fellow is lagging by 90, he will start leading by 90. If it lags by 90 degree, this is motoring. If it leads, this will become generation. So when it will lead, when the slip is negative. When the slip is negative, instead of going at 49 hertz, if it goes at 51 hertz, then the flux lines will be moving in the opposite direction. So the entire induced EMF that we drew in the previous page will reverse sign. The induced EMF will reverse sign. And when this sign reverses, the magnetic field also will change. The motoring will become generation. Are the principles clear? Okay, these are the three principal motors. These are the three principal motors. Here, who changes? The first vector doesn't change. The angle doesn't change. The second fellow has to change. How does the second fellow change? Changes through slip. Changes through slip. If omega s is equal to omega r, slip is 0. Basically, there is no cutting of flux line. They are stationary. Nothing. If it is 0.1 hertz, then they are cutting. 0.1 becomes 0.5. Induced EMF increases by a factor of 5. You understand? If the induced EMF increases by a factor of 5, the induced currents will also increase by a factor of 5, provided it is still resistive. Provided it is still resistive. The rotor bar need not be resistance. There can also be inductance. But fortunately, the frequency is very low. 0.5 hertz, 1 hertz. Therefore, omega L is very low. Omega L is very low. So if the slip becomes high, the inductive nature comes to that. But in this lecture, I don't want to get beyond that. I will encourage you to look at that. At low slip, the rotor bar is resistive. So the induced EMF and the induced currents will be proportionate to each other. They will be proportionate to each other. If the inductive nature starts, then there will be a slight phase shift. It will not be 90 degree. It will become 90 degree plus delta. Some additional lag will come. Okay. So these are the three principal motors and how they produce torques. Is it clear? No. The second part, you look at a DC motor. Give him a mic. Pick up a mic. No, the question everybody should listen. Come, or maybe come speak here.
So thing is, induction motor. If you look at it, if we somehow with respect to the speed it is rotating, and we align it to the frame of reference to the speed, like omega s, we'll say 50 hertz speed. We can say that induction motor also has a armature component and a field component to it back, and it can resemble into a DC motor.
No, at zero slip they will not work.
No, not zero slip. I meant it is rotating at omega. The
Correct.
AC is omega r, omega s. Rotating at omega r.
That is correct.
Yeah, but if we align our vision with omega s, it is like if we
correct. Okay. So if he says that if you also rotate at omega s, it is stationary for you.
Yeah. So
that's what he's saying.
It is same as DC motor only?
No, I'm not sure if it is same as DC motor, but I agree that if you also spin at the same synchronous speed, it is constant. That is agreed. Okay. So an induction motor also produces a revolving magnetic field at synchronous speed. It also produces a revolving rotor magnetic field at synchronous speed. The rotor revolves at omega r. The rotor produces a magnetic field that revolves at omega slip with respect to the rotor. Omega r plus omega slip becomes omega s. Okay, this is how it produces. The interesting point is the synchronous motor cannot start because it can produce torque only when both omega s are omega s. Okay, so I should start spinning that somehow, and only then it can produce torque. In an induction motor, what can happen? Initially, omega s is 50 hertz, omega r is 0. Slip is 50 hertz. Okay, you have to make sure that things are not too bad for you. If there is a sinusoidal flux distribution, it will cut. It will cut. And therefore, EMF will be induced. And current will be induced. What frequency current? 50 hertz frequency current will be induced in the rotor. 50 hertz frequency current will be induced in the rotor. The rotor's magnetic field will start spinning at 50 hertz, though the rotor itself has not started to spin. The rotor itself has not started to spin. Now these two fellows are already there. They produce a torque. And because of the torque, the motor accelerates. Because of the torque, the motor accelerates. The motor, let us say, becomes 1 hertz. Increases to 1 hertz. So the rotor speed is 1 hertz. The slip speed is 49 hertz. So the rotor will produce 49 hertz with respect to itself, and the rotor is spinning at 1. There is torque. It will accelerate. The rotor speed becomes 10 hertz. Slip will be 40 hertz. They will add up to 50 hertz. It will produce torque. And rotor becomes 40 hertz. Slip is 10 hertz. They will again 50 hertz. They will do that. Finally, it will go to the speed at which it has to work. If there is no torque, this fellow also will go to 50 hertz. Under light load, this fellow will also go to 50 hertz. It will spin that. That is why it can self-start. Because the rotor bars are seeing a magnetic field which are moving with respect to themselves. Even though the rotor is not rotating, the rotor bars are seeing a moving magnetic field. They are cutting their moving magnetic field, not by virtue of their motion, but because the magnetic field is moving. As a result, there is a rotor magnetic field. There is an interaction between the two, torque is produced. The motor starts spinning. Okay. So the rotor magnetic field is always at a frequency that is the sum of rotor frequency plus slip frequency. That is to cover the 3 fundamentals of the 3 motors. Is it clear? Yes? Clear? Some of you are in the, what is that mode called? What did I say? Tri-state mode. Huh? Is it very heavy? What's happening? Okay, yes. Go ahead. Yeah, use the mic. Come on.
Sir, in the next graph, you saw the variation between MF and the induced current. We know MF is equals to N into I. So,
Kanna, you have to move from there. We moved. This is how it is like this.
Yeah, black one is MMF and red one is induced current. And we know MF is N into I.
Can you answer this question? You know what he's asking? He says the red waveform is I and MMF is N into I. Therefore,
White phase difference.
Can anybody answer? Did you? It's a very. It's good that you asked. For this, is the question clear? Is the question clear? No. No. You repeat your question. Let the question be clear. Get up. Talk to them.
So the red curve which is the zone, it is the induced current in the rotor bar, and MF and black one is MMF.
So let me do this. So very good that you are. This is the current, and this is the. You said MMF, no?
Yeah.
Let me use the same term. This is MMF. Okay.
Yeah, and MF is equals to N into I. So, then why there is a phase difference between the red curve and black curve?
Is the question clear? Now answer this question. Can some, Now answer this question. It is the induced EMF in the rotor. So what he's trying to say is, this is not what you're imagining it to be. It is something different.
Is it due to the inductance property of the rotor?
No. Sit down. Somebody will answer your question. Yes. What is it? What is it? Go ahead.
The current is the given supply in the stator, where the black one is the induced EMF in the rotor. So how?
Okay. She is using a term called induced EMF in the rotor. That is not the MMF that you think of at all. Okay. So let me start with the easier part. I forget your name. What is your name? Rajan. Okay. So Rajan uses a formula that comes from here. If the current is I, the MMF is Ni. Okay. So what does it mean? Why is it like this? Why is it like that? How are the flux lines here? How are the flux lines here? This is the most representative flux line. And the direction could be something. Let us say this is the direction, depending on the sense of the winding. Some direction is like this. Okay. So what is MMF? Integral H dot dl is I enclosed. I enclosed is Ni. I enclosed is. And what is integral H dot dl? You take over this itself as the contour. You do this. So what it will turn out is, this is H iron times L iron plus H gap times L gap is equal to this Ni. That is what he is talking of. That is what he is talking of. But when we did the armature MMF, that is the place where you slipped off. Okay. This is a very important question, but I'm happy that you asked this question. Where you with this part is okay? This part, did you understand? Okay. Where did we do the armature MMF? Did we do the armature MMF somewhere? This is what? This is what? Armature MMF. That's a waveform. That is a waveform. Okay. That is not proportional to current. The current here is constant. The current is IA. This IA results in an armature MMF wave which has a triangular wave shape. You get that? Okay. Maybe you did not notice this. No, take note of this. Okay. This is not the first time. I would have done that in a sinusoidally distributed case. Three-phase sinusoidal distributed windings. Okay. Here also there is a constant current. That is, the winding will carry, let us say, 10 ampere current at a particular instant. The MMF will be a sinusoidal waveform. The MMF will be a sinusoidal waveform. Okay. Let me clarify that. Where is the difference coming in? When you get into machines, you have to understand that this is not what you are dealing with. This is not what you are dealing with. Rather, you are dealing with a stator and a rotor. And this is the geometry you are dealing with. You get me? Is this machine geometry? Huh? How are the flux lines? How are the flux lines? They are all radial. They are all radial. So let me use some color, other color. So they are all radial. If it is radially inward, this has to be radially outward. So the H here and the H here are opposite. The H here and the H here are opposite. What is MMF? H into gap. What is MMF? H into gap. So when this is sinusoidally distributed, what happens? High, this becomes low. I am attempting to show a sinusoidal distribution. Here the distribution is high. It is maximum or negative maximum. Here it is positive maximum. Here it is 0, 0. Okay. This, if I plot H in the air gap, what is the direction of H? Radial. Or B. B is equal to mu naught H. In the air gap, this fellow will be you get that? What is this? H air gap as a function of theta, or it can also be B air gap as a function of theta. Whatever is B divided by mu naught, you're going to get H. And H air gap, you multiply by the gap. What you will get? MMF. If you multiply that by G, what will you get? MMF. That is what we are talking about. How will the MMF waveform look like? Same. This can also be. You understand? When we say MMF of a winding in a machine, we are essentially talking of the MMF distribution. It is difficult to understand the MMF, but you first I want you to think that you are talking of a machine where the geometry is 2 cylinders. Correct? The stator outside is one, rotor is 1 cylinder. Between the stator inner periphery and the rotor outer periphery, there is an annular air gap. There is an annular air gap. The air gap is very small. The air gap is 1 mm or less than 1 mm. It's very small. And the flux lines are radial in the air gap. Can be radially inward, radially outward. If it is radially inward under the north pole, it will be radially outward under the south pole, vice versa. That is how the flux lines will be. You have to move away from this point where the flux lines are all straight lines parallel to each other. Okay. And if it is radially inward, if B is positive, radially outward, B will be negative. Therefore, B in the air gap as a function of theta is an alternating function. Is an alternating function. It can be sinusoidal, it can be trapezoidal, it can be flat topped, it can be closer to quasi square, but it has to be alternating. Why alternating? If there is a north pole, there has to be south pole. If the flux lines come from stator to rotor under north pole, they have to go from rotor to stator under south pole. If it is B is positive somewhere, B has to be negative somewhere. So the flux density in the air gap has to be an alternating function. At a particular current, right, there is a flux density distribution. Air gap flux density distribution, which is an alternating function. That is sine or it is close to sine. Trapezoidal, quasi-square wave, flat top, etc. Got it? and that is B of theta. What is H in the air gap? B divided by mu naught. Because in air gap there is no confusion. B is equal to mu naught H divided by mu naught. So H of the air gap is also such a same alternating function. And that H is what? Magnetic field intensity. What is the distance of the gap? G. If I multiply H into G, I'm getting MMF. I'm getting MMF. That is what you call as the MMF. Air gap MMF at that point. You understand? That multiplied by G is what you call as MMF. That will be an alternating function. Clear? Okay. Since he said that, let me also finish. What is a sinusoidal distribution? What is a sinusoidal distribution? I have only two conductors here. Okay. Let us say this is dot, this is cross. How will the flux lines look like? How will the flux lines look like? The direction is one. Then that is how the flux lines will look like. That is how the flux lines will look like. For the given polarity, a sense of winding, if this is like this also will be like this. That is anti-clockwise, this is clockwise. And this line will be called the axis. This line is called the axis of the winding. This line is called the axis of the winding. Okay? Nothing will flow through the axis. No magnetic flux line will cross the axis of the winding. That is like the central median in a road when the traffic is well behaved, or when the traffic is made to well behave. No traffic will cross the central line, and that line is like that. The lines will be above, lines will be below. Clear? That is what is called as the magnetic axis of the coil. And if I join the coil, I'll get a vertical line, but the magnetic axis is horizontal. Okay. Now, what will be the MMF distribution for this coil? What is the MMF distribution of this coil? You take any line. You take any line, and you do H dot dl over that line. Do dot H dot dl over any of that line. What will you get? Only this I. That is, let us say, n number of turns are sitting there. N number of turns are sitting here. So that will be Ni. So this integral H dot dl, iron, let us say, is infinitely permeable. The drop is very low, and mostly it is in the gap. So now H dot dl in the gap is Ni. And what is H dot dl in the gap? It crosses here, it crosses there. There is 2G. So this is Ni by 2G. If this is plus Ni by 2G, this will be minus Ni by 2G. This is plus Ni by 2G. How much is this? How much is this? That is also Ni by 2G. So if I do this curve C1, I can take curve C2. My answer is same. My answer is same. You understand? So how does it change? It is always Ni by 2. It is plus Ni by 2 here. It is minus Ni by 2 there. So this fellow will be plus Ni by 2. And at the conductor, it will become minus Ni by 2. This is where the conductor is. And again at the next conductor, it will become plus Ni by 2. Okay. This is armature MMF. This is the winding MMF. Air gap MMF. This is air gap MMF due to this winding with a constant current. This winding is called a concentrated winding. This winding is called a concentrated winding. I mean, I didn't want to get into windings very seriously because too many things in a day. This is more intended to give the points that you have to. Basically, it is more like an advice on how do you reach Jammu Kashmir from here rather than taking you to Jammu Kashmir. Okay, that is what you can do in 1.5 to 2 days. So, something like that nature. So, you get this. This is called distributed. Sorry, concentrated. There is only one winding and that winding is at the same, only one axis. Now, I'll do a different one. I have the same picture. Now, I'm redrawing that. For you to remember, there's a rotor, stator, and an annular gap. Okay, you said what's your name? Rajan. You remember this is the thing. Now, I'm having, let us say, 3 conductors here, and I'm having 3 conductors here. So, what will be the flux lines now? I'll have many flux lines around them. I'll have flux lines around this. But remember, I can also have a flux line here. I'll also have the gap is very exaggerated. The gap is very exaggerated. So, all these flux lines, the first curve, what will be the value here? I enclosed by 2. Here also, I enclosed by 2. Here, I enclosed by 2. Here, this line, interior line, that is not enclosing I. That is not enclosing I. It is enclosing less. Okay, Ni by 3. N is becoming N by 3 into I by 2. And what happens here? Minus N by 3 into I by 2. Here, minus Ni by 2. You get me? So this fellow will be and this is when the 3 conductors are there. This is where the 3 conductors are located. This is where the 3 conductors are located. This will be a stepped waveform. This is a distributed winding. Why? There are 3 windings. Each winding has an axis. The axes are not the same. It has 3 different coils. The 3 different coils are effectively this is the axis. That is for the combined 3 coil. It is only for the middle coil. This coil has an axis like this. The other coil has an axis like this. Okay, that is called a distributed winding. And here, the MMF is not square. The MMF is now a stepped waveform. I can arrange the steps such that the stepped waveform is close to a sine. I can construct number of steps and size of steps such that this is close to sine. If I do that, that is called a sinusoidally distributed winding. In that case, you cannot say my MMF will be N into I. For a constant I, it will be a sinusoidally distributed MMF wave. Clear? Very good. Okay, so what you have is a 3-phase one. What we'll eventually do is for R, Y will be here and B will be here. That is how a machine will be constructed. And together it will produce a revolving MMF. But let me also say, IR will be like this, IY will be like this, IY and IB will be like this. Okay, this will result in a revolving MMF. Note where R is, where is Y is. R is here, 120 degree later MMF will reach Y, 120 degree later B will reach here. What are the currents? R, Y is lagging, R, B is lagging this. Okay, that is the correct phase sequence. You are looking at the observer is standing here and they are going past. R goes first, Y next, B. So this is RYB sequence. So the windings are advanced ahead in space. The currents are lagging. You can do this with 2 windings, so-called alpha and beta, where beta is leading alpha by 90 degree in space and beta is being injected with a current lagging alpha by 90 degree. That will be the equivalent to that. Okay, that is what you will get into the vector domain, and that subsequently takes into some other things. Okay, so this is a summary of what are very essential for you to know in your undergrad thing of machines: DC, induction motor, synchronous machine. I have not covered the so-called special machines yet. Okay, I hope this has given something, right? Clear? Yes? How many of you think that you have now better understanding? Raise your hands. Okay, put down. How many of you think you haven't gained anything? Raise your hand. You can't not be raising hand both. Right? What is your takeaway? What are you studying? Huh? Which year you are in? You have completed the DC motor course? But we discussed DC motor too. You understood? Okay, it's all that if you have not understood the AC motor yet, if you are in second year. But DC motor, did you understand? Okay, that's good. How many of the second years understood the DC motor better? Raise your hand. No fuzzy logic. Clear 0 or 1. Okay. How many are second years here? Okay. All right. So we'll break now and come back. Or yeah, we'll break and come back. Yeah. Yeah. Less than 15 minutes. If 10 minutes possible, come back. Come back in 10 minutes time. Third and fourth year. What did you understand? Did you understand anything better about DC machines? Yeah. Be specific on what is. Give her the mic, Kanna. Yeah. Better conceptual understanding. Tell me what that is. Yeah. Speak.
Sir, actually, even when you started with the magnetic field, from there it actually gave a better understanding of machines as a whole, because machines, the core starts with how the magnetic field behaves, how it goes through the conductors and all. So I personally got a better understanding because I had trouble visualizing what machines would look like or how the magnetic field looks like. But now I have a better understanding of how it behaves. That was my point.
Very nice. Can you quickly cover? I first want the second years to tell me about the DC machine. Then you can also speak. Quickly say whatever you.
Much practical knowledge is what I thought.
What is practical knowledge?
Practical
We have not run the motor.
visualization.
Visualization. Visualization is of the magnetic field.
Yes.
Okay.
Direction of magnetic flux. Direction of magnetic flux
Direction
in
of-
stator and
Direction of magnetic flux. Okay, that you are saying the air gap magnetic field. That is the direction.
Difference between DC and AC.
Will by magnetic circuit, then flux generation in stationary part, then step by step forming of the the magnetic field in rotating part also, that I understood very well.
Sir, I got a better understanding on the visualization of the air gap and the how the magnetic field is going around the rotor and everything. That was a better understanding.
Same magnetic flux distribution and some Maxwell equation that there is.
Sir, I got to know like where we are using the strong flux, like the practical knowledge of like in galvanometer or in the motor, how we are implementing the. Why do we need strong flux? That part was interesting.
I felt that everything was just put together more in a concise way. That we were already like we do have a basic understanding of these things, but it felt more of a recap kind of thing.
I understood about the DC machines also, and about the three phase also. I understood the more about the slip part, like where when there is a slip, when the load increases, the torque actually increases, and it helps to accelerate it. When there is more load, the torque increases. So that's a good part that I understood.
I could visualize the entire machines part into a bigger picture because I was struggling a lot with the like many formulas and can't relate all of them together. So I can't like got a bigger picture after that.
I understand that why armature behind 90 degrees and when was it happened. and when was stator 90 degrees ahead at that situation, what when I understood that part.
I learn how the formulas are. I can't remember the formulas and how we can derive it and how they are related. So I learned that we can't by. I understood how to derive it, not instead of by adding.
I understood that how the strong magnetic flux will be in radial air gap will form the diagram.
Okay, pass it back. So are there any questions still for the second years? Any questions still that you want to be addressed or you want to know? Because I want to move to your third years and fourth years now. Is it fine? No questions. So I presume that's okay. Now move to third years. Huh? Yeah, third years. So you can say what you have understood on the basic machine part. And if there is some question that is still there, go ahead. Everybody, who are all third years here? Who are all third years here? Only 3 of you. Huh? 4. Lot of what happened because attendance is already done, therefore they have gone. Huh?
Sir, I understood that, but still, I still have a confusion between lap and wave winding.
That forget it. Okay, now that's not what I can do now. We will not do that. Okay.
Basic of how this works,
Clearly say what you have understood. If you can say 1 or 2 things clearly on what you have understood, that will work better. Like many of the second year said, they understand the magnetic flux lines. They were able to visualize. That's the main takeaway I found there. Like what was your thing?
like how it's changing.
Okay, any question other than lap and wave?
No.
Nothing on the AC machine. AC machine is very clear. Lap and wave is only for DC. Huh? Forget it. Second year over, no? Find that out. Good.
So we got the better understanding of machines and how the radial magnetic field gets created and all.
So how radial magnetic field is created, you understood.
Then armature MMF, how we can draw the
on the armature MMF.
Yes.
Okay, then. Fine. Any significant question remains on the DC AC machine?
No.
Okay. You are also third year?
Check. Yes, sir. So starting from a single conductor, then folding into a loop, and then increasing the number of turns, and then connecting it to the machines was something new visualization which we got today.
Very good. What is your name?
Shishir Bajpai, sir.
Shishir?
Shishir Bajpai.
Bajpai. You are also third year, huh? Mahek.
Yes, sir. Sir, I got a better visualization of how actually the conductors are placed around and then how stator and rotor magnetic fields interact, and because of that torque is developed and basically the motoring action and the generating mode.
Very good. You understood that. Torque and then motoring generating. Very good. That's nice. Who else? You, Rajan. Very good. Go ahead, Rajan.
I mainly see a new, I mainly observe a new perspective to look after the machines. Now I no need to remember the diagram of DC machines and induction machines. I can directly draw using
math. Wow. Very good. Good.
And I got a good insight in induction machine. And all the things like how commutator behaves and those things.
Very good. Good. Yeah. So from the third years, any significant question remains on the DC AC machine? Nothing. Anyway, Rajan has understood everything. He can also tell you. I won't say everything, but many things. But that's really good to know. That's is expected. So third year is over. Only 4 of you now. What happened to the rest? Go ahead. Fourth years. Huh? See, you will not be invited with tambul and pam 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 and that. Oh, please come and speak. Right? We cannot do that. Right? Yeah. Get a band and bam 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 bam. We come. We welcome Amit to share his views. Now we ask Namita to share her views. We cannot do all that. Go ahead.
Yeah. So first of all, the things that
you are in fourth year or third year. Fourth. What's your name?
Yash.
Huh?
Yash.
Yes.
Raj.
MTech Yash. BTech Yash. Huh? Okay. You are first year or second year MTech? Second year. Okay.
Okay. So like the questions which we generally don't ask The we think that it is given, it is just there, but you got to know what's behind that. For example, the inductors are like they have coils, but why? That we got to know today, like that questions.
Very good. Interesting. Other 4th years. Yeah, Ujjwal. Yeah. Good, good.
This session was quite helpful for me in understanding how the stator and rotors actually interact, such the concepts of induced fields and even MMF and EMF. Even it was quite helpful for me to understand why the structure of the poles and rotor is in the same way, just because of the last lecture that you told. Even this lecture was helpful to understand the topic that how three-phase power is better than the single-phase power. Along with it, the concept which we taught that there are different parallel paths in a conductor, but different voltages get induced. That was a new thing that I came to learn in this class. And apart from that, even the question which Rajan asked, that it was never striking in my mind. That was the new thing that I did.
Rajan's big contribution to the class is he raised the question.
So that is the thing that I learned.
That is why I say don't keep quiet. Many people in his position would say, should I ask something? Or why should I ask? Or it may be too simple. For multiple reasons, they may not ask. That's very good. That is the purpose.
I like to how we move from the inductor design to the motor design. The basic part we from magnetic core to we move to the machine design.
We didn't do a machine design. We probably looked at the machine construction and operation.
Construction is happen from basic means that the thought process is new, and then I get a perfect picture, visualization of magnetic field and how they are interaction and how people that.
So, anybody else? Yeah, finish 4th years. Oh, Kriti and that.
Every time like when I revisit the machines and all the concept, either I get more confused or I understand something. So this lecture was like where I understood most of the things. Like you have told us how to visualize the EMF also in 2 parts, with the flux line, with the conductors and all. So this is the where I got the most of the clarity here in this.
Okay.
Yes, sir. So I got better understanding and better visualization of the rotating magnetic field and how it interacts with the rotor, so that the rotor rotates.
Very good.
So it was like mostly all this induction machine and synchronous machine. It was a revision quite, and it is always very confusing to visualize the rotor and stator and how they interact. So I got a better clarity at that.
We already studied about this magnetic and magnetic circuits and all these curves we have seen, but we were not able to relate with that shapes and conductors. So today I got interesting perspective about stator shape, like how it evolved from that magnetic circuits only. So that was something new for me.
Alok is not studying in this college. He's not in 2nd year, 3rd year, 4th year. He's not in MTech also. Huh?
So today I get better understanding of the machines, that interaction of magnetic field in machines, how this construction helps to run the machine. And
so I will tell Alok not to give his degree because he's not part of the institute.
Hello. So it was good to understand the concepts from you. मतलब basically वो flux के visualization जो आपने starting में मतलब initially linear लेके फिर कैसे बीच में अगर हम bars iron core वगैरह डाल रहे हैं तो कैसे affect करता है वो, और फिर actually why that stator shape is made like that ताकि वो strong magnetic field strong आए, वही समझ के ज़्यादा better लगा. यही नया था कुछ जो सीखने मिला. Thank you so much.
Yeah. The 4th years complete that, and let me know if you have any questions still for the 4th year on the basic motors. Everybody done? Okay. Pass it back. And now the MTech students, say any questions on the basic motors, machines? What did you learn? First year, yeah. Yash won't come now. He's MTech second year. He's senior. So he'll come only later.
So this session gave me a better understanding of how to approach, how to start with the analysis of a motor. So what should be the starting point and how can we go around the analysis. So that was very helpful.
What is the starting point? How should we start?
So like today we started with a simple conductor and then we moved to the actual construction of motor. So how can we relate from a simple conductor to a why that particular construction is chosen or how that came, that kind of understanding.
Very good. Okay. Others, yeah. Other MTech first year, only one is there, huh? Huh? Only one MTech first year is there? Right.
Today I got a better understanding of rotor and stator and the magnetic field and like the analysis of machines and all.
Can you be
better
little
understanding.
clear on what is that? Can you point out something and say what was clear or something?
About the electromagnetic interaction, like producing torque and all.
Okay. You're in which program?
Second year, sir.
Okay, first year MTech is all over, no? Anyway, you finish. Yeah, Mike has come to you.
So I got a better understanding on the visualization of magnetic flux lines and radial lines and construction of an electric machine and all.
Okay. Okay, other MTechs finish. Yeah? Who is? Very good, very good. Very nice. Good to know. Yeah, finish. Go ahead.
Hello.
Who is speaking? Yeah.
Sir, I would say, means with your lectures, I understood means what mistakes we had done while trying to study this subject. How should be the flow? What is the importance of basics and how it should be related? And while studying, we should also visualize the things. How we should actually draw, in fact, those flux lines. So this is what I would say.
Others.
Sir, as you said yesterday, there are three phases, like new, incremental, and reorganization. Mine is incremental and new organization in this thing. So yeah.
Very good. What was incremental?
No, this thing was incremental. How we take contour and take integral of h dot dl, that thing, and reorganization was this thing. Flux line will cause this thing. Every conductor will have a step in the
MMF waveform by a winding. Did you know about the rotor bars conductor in the squirrel cage motor? Sinusoidal current distribution. Did you know about that? Sinusoidal current distribution in the rotor.
Somewhat. I know.
Okay. How many of you knew that the currents in the rotor bar of the induction motor were sinusoidally distributed before the lecture? Okay. Fine. So are there any questions now on this? The time is very short. So this is basically covering the entire magnetics, right? Fields, magnetics up to the basic of the three conventional machines. No questions, right? Everything clear? Okay. Adam, anything to add? Nothing. Everything okay. Fine. Madam? That's okay. Yeah. So now we are going to step on to the so-called special machine. We're going to step on to the so-called special machine. I'm just going to draw an array of machines here. Nothing more than that. Okay. So what is it I'm drawing? It is also a shaft in the middle. The shaft has a low permeability. It is high 10. Okay. This is a 4-pole machine. The moment I draw this, I would also encourage you to draw that, and I would encourage you to draw a few flux lines and tell yourself how they are going. Right? Can you tell me if this is north? If this is north, where is the south pole? This. How about this? South, north. So if that is the case, the conductors here, what will be the dot or cross? What will be the dot or cross here? If it is north pole, flux line will come like this, right? And it will go like this for the south. So what will be the direction of the flux lines? Or rather, if it is dot or cross here, both of them should be dot or cross. Dot or cross here? Dot. This is all dot. This also dot. If this is dot, this side will be cross. Okay. So you can just have this for your reference to start with. Now, what are we doing here? We are establishing a magnetic field. We are establishing a magnetic field using pole winding. This pole winding is a direct extension from the first level of winding that you are all knowing. So what is the first winding we did? Single turn, we did multiple turn. When we did multiple turn, what we do? One turn like this, one turn like this, one turn. All of them have the same axis. All of them have a same axis. This is kind of a helical coil, spring kind of a coil. Same axis. That coil is the most easiest for you to imagine. But the coil that are there in the induction machine is, for example, if there is a conductor here, that conductor comes back here. That's a drum. The conductor goes inside, turns back, and comes back from here. In fact, not here, because it's a 4-pole machine, it will be 180 degrees here. The return will be there. Okay. And in this end, it will end in the commutator. Similarly, for this fellow, there will be some fellow here. It will be returning there. Only if it returns 180 degree later, it is called full pitch. In the other cases, the AC winding, they'll use that half pitch. So you'll get that. The construction is different. That is where Rajan's primary thing started. You are looking at a winding that is around a drum. You are not looking at a winding that is around a cylinder like this, but it goes up the cylinder, other end of the cylinder, comes down. You understand? Or the cylinder is like this, goes like this, comes back, goes like this, comes back. That is what you have to visualize. This comes the next level from where the conductors are. There are annular space. The stator and the rotor are coaxial, and there is an annular space, and the lines have to be radial. And then the next point is the winding conductors are like this. Okay, that is why the conductors are there in the armature. So the armature is fine, but the pole windings are projecting. The pole windings are projecting, and they are electromagnet. What can be done with an electromagnet can also be done with a permanent magnet. Okay. Can I convert the DC machine into a permanent magnet DC machine? The question clear? This is a 4-pole DC machine. Can I make it a 4-pole permanent magnet DC? Please do that. Please do that. 4-pole permanent magnet DC. So the clue is you start with the lines. That fellow also should produce similar lines. That fellow also should produce similar lines. Try to replace what? The field winding with permanent magnet. The second years can try this. Then stator only, no. The stator has a field winding. The stator should have permanent magnet. Is it the rotor or the stator? Not quite. See, the yoke is not visible. Somewhere, somewhat right. Except that the geometry of the permanent magnet should be better. Somewhat right. Correct. Make the geometry better. The permanent magnet should spread itself out. Card has not put any condition that the permanent magnets have to be only on the rotor. There is no constitution rule also. It is not illegal to have permanent magnets in the stator. Right? How the MTech students have done that. No, Pade. Huh? Oh, this field winding has to be replaced by a permanent magnet. When I said permanent magnet DC machine, what is permanent magnet? There's a field coil. Field coil is producing the field. Instead of a field winding, a permanent magnet should produce the field. You understand? The field winding should be replaced by permanent magnet. Clear? Show the construction, Kanna. Show how it will look like. Where will you fix the permanent magnets? Huh? I don't want. You will say it is old, not fashionable. They come with new garments, new things, everything. No. I'll also tell you why. Firstly, why not? That's my question. And do I know to use a permanent magnet instead of an electromagnet? To challenge my own intellectual ability, right? For me to learn. This field winding, I want it to be replaced. Now, right now, the excitation is through a winding. I want it to be using a permanent magnet. Permanent magnet is given to you. Otherwise, you won't get a permanent magnet. You have to do that, whatever you are saying, to get a permanent magnet. How will you use that permanent magnet in the construction to realize this? Yes, it is replacement of the field winding by a permanent magnet. Yeah, that will be same. But instead of field winding, I want a permanent magnet. You're almost right, except that the permanent magnet, every magnet will have two poles, right? You have to indicate where the two poles are. Magnet is not a single pole. Any magnet, permanent magnet comes, will have two poles. Correct? So which is the pole, and then it has to be better spread. It has to be, here you will get flux density only under this. But the flux density should be over 120 degrees at least. Huh? Yeah, good. You are in which year program? Huh? Fourth year. Yeah, okay, but draw that. How is it going to look like? Complete that. Show the picture. Complete the picture. You go and draw that. You go draw that. What's your name? Which year you are in? Go draw that. Draw that. Amma, this must be there. There should be yoke must be there. There should be closed path. Then you see what needs to be done there. Turn it on. If you apply your brain, you can always learn. If you don't apply your brains, you can't learn. Structure will be same. I don't know what it, why it enhance the field. Yeah, there is a yoke. The flux line should not go out. Otherwise, it will not be there. This is the air gap. Okay, where is the yoke? Stator yoke. That is not the yoke. That is only air gap. That is the air gap and that is stator yoke. Okay, fine. So that's the rotor. This is the rotor. And the shaft is there in the middle. Okay. Good. Shona. See, let us say you start with this, right? Got where we considered Rajan's question, right? We have an electromagnet here, correct? We have an electromagnet here. Let us say this is dot, cross, dot, cross, dot, cross. Can I not replace this with the permanent magnet? Right? How can I replace with the permanent magnet? This comes like that. Okay. So what I'll do is, I'm going to, in this place, I'm going to put a permanent magnet. And where this may be the north pole and this will be the south pole. That is a replacement. Correct. The same thing in this pole structure, I can put a north and south here. This is my magnet. When I'm putting it like that, why should I put it at the middle? Right? I can put it here itself. You understand? This can be my permanent magnet where this is the yoke. You understand? That is what Shonak has done. That is what Shonak has done. So the line will be like this. So what is the advantage that Nisha was asking? What is the advantage that you see now? Earlier, you needed the pole, the core material. Then you needed a coil. The coil can't hang. The coil has to be put in some bobbin or something. And it requires a lot of space. It requires a lot of space. Now the space is reduced. The space is reduced. If you draw it properly, okay, this is same. Then there is only this strip. Only that strip comes. Then the yoke comes. This height is greatly reduced. The height of the pole is greatly reduced. So it's radially shrinking. It radially shrinks. The outer diameter will be lower. That is the advantage of a permanent magnet. That is why people have fallen for that. But the trouble is permanent magnet requires rare earth metals. And rare earth metals are rare. Yeah, this is north and south. This is south and north. To create this magnet is a separate job. It is actually an array of permanent magnets that is created inside. Normally, I will never leave the lines like that. So let me complete the lines there. Okay, so the lines go, complete themselves. Go ahead, Ujjwal. Yeah, that is south. The top is south. In a bar magnet, north is there, south is there. How are they getting attracted? There's a yoke. The field lines are all confined inside the yoke. Field lines don't go outside. There is no insulation for magnetic field. There is only containment. There's only, you put a highly permeable material. Now, if my uncle presents me this permanent magnet and I want to keep it safe, what I should do? This will be driving magnetic flux lines and gradually it will get this thing. So I should take some iron, okay, and put iron all around. Then all the flux lines will confine inside that. It will not go out. That is what a yoke does. So this is permanent magnet DC. So you come to how to do that, right? So this is the first transition. Now the permanent magnet DC is a reference for you. I am now asking a question whether the permanent magnet can be shifted to the rotor. Permanent magnet can be shifted to the rotor. And in the stator you can have winding. The stator you can have a winding. So I want you to come up with a permanent magnet rotor. Okay. So I want you to come up with a permanent magnet rotor. So let me define the problem. This is the stator. This is the air gap and the rotor. And this is the shaft. And I want to make this rotor, stator gap. Okay, have no confusion about it. I want you to make the rotor as a permanent magnet rotor. Okay, you can make it either 2-pole or 4-pole. I will leave that to you. Question is clear? Very high residual magnetism and with very high coercivity, and which will not get demagnetized quickly. It won't. Only field excitation won't make the motor run. Only the armature current is given, the motor will run. Otherwise it won't run. Except that the rotor, the field strength cannot be reduced. Sometimes we want to reduce that to work, for the motor to work at very high speeds, above the rated speed. That's all. One question is whether the permanent magnet DC machine will it start rotating by itself? No. Permanent magnet only provides the field. Only if there is armature current, there will be torque generated. We'll go till 6. We'll wrap up by then. I'm fine, but you all have to travel. Done? Anybody? Stator wearing a full the yoke there. You are stuck with the old DC machines pole. Now you see, my stator is cylindrical. My stator has no projecting poles. My stator has no projecting poles. The only thing you're doing is you're not drawing a yoke around. Put another circle. Put another circle. That circle, let it be bigger. Bigger than the air gap. Make it bigger. Good. It will mislead you. Okay. Better. Draw some flux lines. This is the DC machine. Okay, you have done that. Now you do for the. This is correct. Complete it. Complete it. That is correct. But now I want you to fix the permanent magnet onto the rotor to see whether you can have a flux distribution in the air gap. That has to come by injecting current through the stator. That is not done yet. We are now doing the permanent magnet rotor. I want you to tell how do I construct a permanent magnet rotor. No. No. That will be somewhat like a stepper. It will be reluctance. There's no permanent magnet anywhere here. Just a minute. Amma? This is the yoke. This is the gap. This is north and south. Huh? This is north and south. This is north and south. Yeah, go draw that. Go draw that. Draw that in the middle of the board. Somebody showed something? Ask something? This is in the stator. There will have to be a gap between the two. See, every permanent magnet will have a north pole and a south pole. I want you to indicate that. Okay. And the lines will have to be radial. So I want you to take little care on that and say that. No, don't worry about. There are no permanent magnets here. We'll put windings here later. Don't worry about the stator. We'll put windings on the stator later. Okay. No. No, we cannot have permanent magnets in both places. There is no control over that. This is your, you see, this is your permanent magnet DC excitation, and here you are only projecting the rotor poles. This will only change the reluctance. There is no, what I want is I don't want any permanent magnet on the stator. I want the permanent magnet on the rotor. You are giving name. I don't want to give name. How will the rotor rotate? Look like? That is why you are complicating the picture. Okay. Show me how I can fix permanent magnet in a rotor. There's not a unique way. There are a number of ways. But I want you to come up with at least one way of fixing that. There's no control. There's no control. It will just come and stop somewhere, that's all. Can we make rotor? That is also fine. You can go and draw somewhere next to that. You have changed something. What have you done? Why you have changed something? What will happen is from this north to south lines will go. North to south lines will go. North. Is that what you showed in your notebook? Bring your notebook and check. She thought she will innovate something. Who had drawn? Kirti. You can draw by the side here. Come. Change that. Go change quickly. Or you can remove my rotor and then you can let her finish first. Mahek, finish. Mahek, finish. Finish. Only one can touch the board at a time. Why did you... Hey, the class is very spread out. Come here, man. I'm walking several kilometers a day. Come closer. Come closer. You remove this. Remove that. Or you can just modify that also, whatever. Fine. So please see Mahek's rotor. Okay, for this rotor construction, draw the flux lines. For that rotor construction, That is what can tell you whether it will work or not work. Draw the flux lines. In all these magnets, the internal construction is such that the lines will never come from the sides. The lines will never come from the sides. There will be an array of magnets sitting inside. They will make sure that the lines really don't come out of sides. Okay, the lines come out of sides, then that will be disaster. Wherever is north, wherever is south, that is where the lines will come out from. So for Mahex, how do the line look like? Yes. What are you doing? You have gone into some ball pen repair. What are you doing? That's not how the lines are going to go. When you're doing this, right? When you're writing, let us say north and south, the assumption is no lines will come out of this. The lines can come out only like this and going like this. You understand? So, this is south. There will be lines like this. You understand? Huh? Now complete it. Complete it. You're not trying anything, Kana? Huh? You got only one. I'm not able to see anything from that. You're testing my eye. Huh? I have to go to an ophthalmologist, eye doctor anyway. Huh? What happened? Just have to project. Okay. These are all out of syllabus. No, not to worry now. Huh? Okay. Draw some indicative flux lines. Draw some indicative flux lines. Very good. You maybe choose another color. If you press the pen, you can choose red color then. Choose red. Yeah, keep some dots on. Now draw another line. Don't worry. Draw another flux line. Draw another flux line. See, you have to sync with the class. You have to sync with the class. If somebody has proposed an idea, you must jump in and see whether that's going to work or not work. You understand? You can't be going 24 people in 48 directions. That time is over when you have to come up with that, right? When someone proposes, yes, you have to see whether that's going to work. Lines on this side. So I want you to see if Mahek's idea will work and Kriti's idea will work. Or both will work. Or none of them will work. Huh? Don't toss a coin. No. This is going through the gap. This is going, it has to cross the yoke. Go to the yoke. So don't exaggerate the air gap beyond what you need. Otherwise, it will mislead your drawing. It will mislead your drawing. Already we are exaggerating the air gap because of the practical difficulty. It's too small. If you unnecessarily exaggerate, she did. Huh? Yeah. So remove just these lines. These lines, remove them. Yeah. Can somebody draw the flux lines for Mahek's picture? Raghavendra, you try? Raghavendra, you want to try the flux lines for Mahek's picture? Try. Okay. Is it fine? How many of you understand what she has done? What has she done? What has Kriti done? She has taken a cylindrical rotor. She has fixed 4 things on that, top of that, right? And north, south, she has indicated some of them has gone, right? And it goes and comes back there. Okay, fine. Here you can see the lines are only going out of north and coming into south. Other 2 sides, no lines. You have to now assume that somehow it is ensured in the manufacturing process that the lines cannot come out like that. Okay, yeah. You want to draw lines and show that?
You have tried like this. So north, south, north. The magnetic flex lines are.
No, where is north alone cannot be separate there. No, north and south have one permanent magnet is there.
Sir, this one is a one pole. This one is another one. This one is another one. This one is
2 poles have to coexist in a magnet. No, you cannot make a permanent magnet which has only 1 pole.
Okay, sir. That's why, sir. This is completely one pole, sir. This is the area, for example. This is one pole. It is having north and south pole.
Then the lines will leave from this.
Like this.
Is there air gap here?
Yes, sir. This is the air gap.
Between these 2?
Yes, sir. It is the air gap, sir. Actually.
No, this sectoral region.
Yes, sir. It doesn't have any connection like this is C.
So you are cutting the rotor there.
Yes, sir. Yes, sir. Like
that's not what you usually do. Okay.
Not cutting, sir. Here it is.
You draw a bigger one of that version. I'll come
Yes,
and
sir,
see that.
I will.
Mahek, you draw the lines here. Come. Huh? Which will never pass the air gap. Let's see. Let's see. Let us see. Let us see. I will try to correct it from that particular point. So if it is not crossing the air gap, it is not going to work. That is what they are saying. Okay. So what should you do? Push this to the right. Not out of the rotor, towards the edge of the rotor. And it will not go through the gap. It has to cross the gap. The lines have to cross the gap. That is how it has to be. So for this, the magnet has to come here. Shift to the right. Okay, go back. Thank you. All right, did you see these 2? Are you able to hear me? Yes. So, somehow I was expecting more of you to give me some solutions. This is the rotor. So, one is I can place permanent magnet like this. This can be the so-called north pole, so-called south pole. This will be the north, this will be the south. And this will be the south, this will be the north. This will be the north and this will be the south. These magnets, it is all presumed that the line will only come out here and get in this. The line will not go from the side. Some measures have been taken. So this can be like this. So this line can go like this. If you look at the rotor alone, the complete flux line will not be visible. You have to put the stator. So you have to put the air gap. This is the air gap. And you have to put the stator yoke. So this line will cross. Okay. Maybe I should choose a black color pen. I will have a line. This is north pole. Will go out like this. Will turn here. This is south pole, right? This. You see that? And here let me take. This is north. This is south. So, right? Similarly here. Remember, the air gap is exaggerated. The air gap is exaggerated. It is so small that many times it is convenient for you to go across the air gap into the stator yoke. Clear? This is one possibility. What is happening here? She is just pasting it onto that. She's just sticking it onto that. What I can do next is I can cut that portion . This is now my north, this is my south. This is my north, this is my south. This is south, this is north. This is north, this is south. What has happened now? I push this fellow inside. I have cut some groove and pushed that inside, and my air gap is here. Again, the air gap is very exaggerated now, and the stator yoke is here. Clear? How will the lines look like? How will the lines look like? North, it will cross. South, it will come inside. Got it? So, this is called surface mount because it is mounted on the surface. Surface mount permanent magnet rotor. This is called surface inset, INSET, inset permanent magnet rotor. So in this case, you have to cut this metal and you have to put that into that. Mahek overdrew something. You can actually have the rotor gap in this, and I can have my permanent magnet sitting inside. Sitting inside. Not very deep inside. Mahek almost reached this. This top is north, this is south. This is north, this is south. So this line will go out, come back like this. So this is north like that, south like this. And this is south, north. So it's like this, just like this. So here again, south and north. North is here. Sorry, I'm losing my control. Okay. Here the permanent magnet is slightly inside. So what do you actually do in this case, the last case is, you have holes. In your lamination stack, you have holes. And take your permanent magnet, dung. It is easier said than done. The permanent magnet will stick to iron. We'll come on to that. If you have your hammer with you, the permanent magnet will come and hit the hammer and hit your face also. You have to be very careful with that. This is called, I've written it here, interior, because it sits somewhat inside. Interior permanent magnet rotor. Okay, I want you to visualize these things. You should be able to visualize these things. These are all 3 different constructions that you can think of. One is on the surface, cut that and push it into the surface. Other one is slightly deeper into the surface. Okay, so 3 different ways you can look at in making a permanent magnet rotor. Make a permanent magnet rotor. So once you have made a permanent magnet rotor, now what happens? Now what happens? What kind of flux density they produce? What kind of flux density they produce? One is, it can produce somewhat like a flat topped flux density. Flat topped flux density. If it produces a flat topped air gap flux density, this will be the wave shape of the induced EMF. That will be the wave shape of the induced EMF. And if the wave shape of the induced EMF is that, what can be your current? What can be your current? That becomes a problem. Correct? So the product of the induced EMF and current is power. And there can be multiple phases. If you add the power should not have fluctuations. The power should not have fluctuations. So what I can do is, this is the induced EMF in one stator winding. I can inject about a 120-degree pulse of current. This is 0, this is 180, and this width is 120. This width is 120. I can again inject another 120-degree width. Here again, I can inject a 120-degree width. Here again, I can inject a 120-degree width. So what am I doing? I am injecting 120-degree width of current only when the back EMF is flat. Only when the back EMF is flat. As a result of that, the power is flat only in these intervals. The power is flat only in these intervals. Let me draw the power. Okay. The power delivery from here is like this. The power delivery from here is like this. What is the power delivery here? Same. This is the power delivered, or the mechanical power developed, whatever you call. The only trouble is it is only 120-degree pulses. So don't worry. Go to another fellow. This is a second winding. This is a second winding. In this case, let us say they are phase shifted by 120 degree. This has got a 120-degree phase shift between here and here. Okay. I'm not able to draw that very clearly, but it is phase shifted like this. So what do I do here? I'll inject a current for a 120-degree width. Here again I'll inject a current for 120-degree width. So I'll be able to generate power here also. I'll be able to generate power here also, here also. Okay, this is for 120-degree width. Similarly, I have a third phase. Similarly, I'll have a third phase. So 120 degrees, somebody is generating. 60 degrees, no. 120 degrees, yes, 60 degree. There are 3 fellows doing it. So what will happen? Out of 3, 2 fellows will generate power. Out of 3, 2 fellows will generate power at any instant. They will add up. That will be constant. That will be whatever P I have indicated, 2P will be the total output. 2P will be the total. Why I have not done this is I am very tired now. What I should do is, I should draw EB1 as a trapezoidal waveform. I should draw EB2 as another trapezoidal waveform exactly phase shifted by 120 degree. I should draw EB3 exactly phase shifted by another 120 degree. And in all these cases, I should excite the phase with a positive pulse, negative pulse. Positive pulse and negative pulse for 120 degree width when the back EMF is constant. Okay. If I do that, if I call the flat is E, capital E, okay. If I call this as capital E, if I call this I, then this P will be equal to capital E into I. The total power output of the machine will be 2 times E into I. The torque output of the machine will be 2 times E into I by omega. This is what is brushless DC. This is what is brushless DC. Okay. How can you do that? You need three-phase windings. You will have three-phase windings. The three-phase windings are now on the stator. Is that clear to you? Okay. Now, the same permanent magnet rotors, let me not use yellow now. Let us say I have a sinusoidal flux density. Who is having? I'm still talking of permanent magnet rotor only. Okay. The permanent magnet rotor could have trapezoidal flux density, a flat top, or it could be sinusoidal. Now I'm saying it is sinusoidal flux density. So if it is sinusoidal flux density, the induced EMF is sinusoidal. The induced EMF is sinusoidal. Now it is not, it will have a three-phase induced EMF, right? This is 120 here. Let me take some other color. This will be the induced EMF of another phase, and this will be the induced EMF of another phase. They will be producing three-phase sinusoidal induced EMFs. In this case, I have to inject three-phase sinusoidal currents. I have to inject three-phase sinusoidal currents. So the current could be phase shifted or in phase, but three-phase sinusoidal current. If I inject that, I'll be able to get a steady power. So three-phase power is steady when it is sinusoidal voltage and sinusoidal current, as we discussed a while back. Single phase V into I is DC and double frequency. Three phases, the double frequency gets nullified. It is DC. Yet another way of coming up with an unpulsating power is flat-topped waveform and quasi-square wave, what we saw in the previous slide. That is what is used in the brushless DC. So in the same permanent magnet rotor, when the flux density distribution and therefore the induced EMF is closer to trapezoidal, is a flat-topped, where you have to inject quasi-square current waveform, you call the machine as brushless DC. You call the machine as brushless DC. When it is closer to sinusoid, like in a synchronous machine, alternator, you call that as a PMSM, permanent magnet synchronous machine. Is it clear? Yes? Okay, that is to sweep you through that. Where did you start from? DC, permanent magnet DC, brushless DC, and permanent magnet synchronous machine. Is the flow clear? The flow clear? Now what I'm going to do, I'm going to make synchronous machine. That is not permanent magnet. That is a wound field synchronous machine. So how will I do that? Sometimes it obeys. Sometimes first save that, please. Don't be in a hurry. Okay. So here you are now going to do the inverse process. What did you do from DC to BMDC? You replace the field winding by a permanent magnet. In this case, you have to replace the permanent magnet in the rotor by a field winding. Question is clear? You have to replace the permanent magnet in the field winding by a winding on the rotor. Winding on the rotor. Yeah, do that. How do you do that? You take any of these. Okay, you take any of these. Doesn't matter. Okay, try to replace this by a winding. You're able to hear me? So slight disturbance. You're able to hear me? Only then you can get three-phase power. Only then you will get, two of them will, if it is less than 120 degree, you won't get that. Only when it is 120 degree, two of them will conduct at any time. Huh? Then there will be a time when third will also produce some power. Thanks. This is also correct. This will be called salient pole. But you can also have cylindrical. Getting some idea? Think through. Getting something? No. At least don't ever do one mistake. Drawing flux lines which are going out of yoke. If I ask about 10 students in your age group, 4 or 5 of them will draw flux lines going out. I'm talking at a national level. 4 or 5 of them will draw lines just going out. Another 3 4 at least will draw lines going through the air gap itself. What do you mean by air gap? The line will not cross from stator to rotor. From the stator it will go into air gap. It will go via air gap only and go back to the stator. You understand? That cannot happen. Why? Air gap is a very high reluctance path. The gap is small, so it has to enter into the rotor. You go draw this. Why have you got fixated into this? Yeah, make that. Yeah, change that into this. You draw one 4-pole rotor. There, go to the new slide. Okay. You draw one 4-pole PM rotor and your equivalent. நீங்க பண்ணணுமே. Is it okay? Actually, there is one cross is called this, no? The Christian tradition, they have crosses. They have different kind of crosses. So there is one cross there, this round. Is there anybody who knows about that? No. The crosses are all drawn differently. Like, not these two parallel lines. That will be short, right? Sometimes the end will be floral. And some end will be a little different. The endings of them particularly. Okay. I don't know. Good. Where are the coils here? Show your coils here. Correct. Okay. Indicate the flux lines. Okay, indicate 1 or 2 lines there, indicate 1 or 2 lines in your. The equivalence will be established only when you draw flux lines. They should be able to produce a very similar pattern of flux lines. Yesh's head is spinning now. Yes. Yesh maintained it while it as long as power electronics and other things, but machine has made him. Rather than machine spinning, his head is spinning now. How can it go like this? These are flux lines. You remove your flux lines. See, he is smart at removing the lines. I had to ask him earlier. How will the lines be like this? Draw the lines for this. This is north, right? This is south. Now draw a line here. Complete the flux line. And draw one more line on this side. You have to draw more carefully. Okay. This line will, there's air gap is not very clear in your case. Whether there's air gap at all, I don't know. Is this air gap? Or is it the stator yoke? Make sure you have a rotor, you have an air gap and stator. Okay. Stator has to be identified between two circles. Yoke very clearly. Huh? Now draw that here. The same effect must be here. The same effect must be here. So one of them is they are a little tired. Right? Everybody is tired, right? How many of you are tired? Raise your hands. Raise your hand. If you're tired, raise your hand. No. How many of you are not tired? Raise your hands. Nota is not allowed in this poll. Nota is not allowed. This election commission doesn't allow nota. Right? How many of you are tired? Raise your hands. How many of you are not tired? Raise your hands. Very good. So, for those of you who are tired, don't worry. We'll close by 6 o'clock. For those of you who are not tired, don't worry. We are going to work till 6 o'clock. That is what it is. You got it? So what he has done is, this he has replaced by a salient pole. Thank you. This he has replaced by a salient pole. That's called a salient pole field. Right? It can also be cylindrical. It can also be cylindrical. So now I'm going to tell you that. So what is your priority? I'll finish this because other control and all that are going to be very complex for all the people that's coming up there, right? Okay. So let us understand how the winding is. I prefer to draw windings with some axis like this. This is the axis of the winding. Why? The lines are like this. See, I am drawing it rather loosely, but you have to make sure that the lines are radial and they turn very smoothly and very smoothly here. So please get that, otherwise some of these can mislead you. These are how your lines are going to be. So this is a winding. This is a winding producing this one. How can I replace this? How can I replace this with a permanent magnet? I should make sure that this is my axis. I should make sure that this is my axis. So where will my permanent magnet be? Where should my permanent magnet be? This is my north pole here. This is my north pole and this is my south pole of the permanent magnet. Okay, that is how they get replaced. So when I have to do this, I have to do this kind of windings. So if it's a 4-pole, this will be a 2-pole. This will be a 2-pole field winding. If I need a 4-pole field winding, sorry. If I need a 4-pole winding, what are all going to be my axis? And the return may come here. Return may come here. They could be connected in some fashion, like where the lines are going around this and coming back into this. Okay. So Until now, I did not say how the three-phase windings are connected, which I thought I had told you somewhere previously. In all this BLDC, permanent magnet and induction motor, you will have three-phase winding. How is the three-phase winding created? Okay. This is my R phase. This is my R phase. If I want this to be my R phase, the main conductors of R phase have to be here. The main conductors of R phase have to be here. I am only drawing one. There can be a belt. Then let me take the Y phase. The Y phase axis is going to be like this. The Y phase axis is going to be like this. If the axis is to be like that, its conductors have to be across the two. And B. Okay, this is the B phase axis. The B phase axis is like this. Its conductors have to be normal. This is how the windings will get conducted. This is concentrated three-phase winding. You can make it distributed. That's how the three-phase windings come. Clear? So we have gone from the whole spectrum of what is it? DC, permanent magnet DC, brushless DC, permanent magnet synchronous machine, wound field synchronous machine. There, what is his name? Shashwat did the salient pole synchronous machine. And what I have drawn is the cylindrical rotor synchronous machine. And the induction motor, of course, same as the synchronous machine, the rotor bars, which we anyway discussed. So that is how the entire spectrum gets covered. So the special machines are not many special, they are actually intermediate. You can move very smoothly from one to the other. Okay, that is exactly what it is. The special machine meaning is typically that you will need a power electronic converter to run them. Fine? Okay. So it's about 25 minutes remaining. Is there anything specific that you want? Is there anything specific you want? So where did we start from? We started from magnetic fields this morning, right? Diode was long story. That won't end now. Electronics, diode, right? BJT, MOSFET, MOSFET characteristics, and after that the switching transition. The switching transition is very important. I want all the power electronic students. I think everybody here is a power electronic student. Maybe the second years might not have studied and they were not there. The third, fourth, and the MTech students particularly have to be extremely good at that. Look at the data sheets, what they are saying. Okay, that's something there. This is the simplified switching transition. We are not included any parasitics here. Okay, you have to get better than that. And true about research scholars, any research scholar being here too. Fine. So, and then we did the power converters, where we did the DC-DC, right? Buck, boost, synchronous buck. And we did chopper, right? Single 2-quadrant chopper, 4-quadrant chopper, and we went into the inverter, correct? Single phase and 3-phase inverter. So today, we started our journey from current carrying conductor, magnetic field, and then Ampere's law to evaluate that, Biot-Savart law. And then we went to do coil and multi-turn coil, and then we used iron, and then we understood how we can direct magnetic field lines, how we can produce strong magnetic field lines in a rectangular area. Then we transformed our idea into how you can produce strong magnetic field in a circular annular region. In an annular region, the space between those two is called an annulus, the annular region. How do you create that? That is essential for machines. So then we did that. So how the kind of construction of a DC machine. And from the construction of the DC machine, we went into the air gap flux density. And it is a flat top air gap flux density. From there, we went into the armature. We put a coil in the armature. And we saw, firstly, for that flux density distribution, what is the flux per pole? Flux density to flux per pole is a huge gap. Okay, that is not addressed in the books. So you have to do that. That is a surface integration you need to do under the pole. Then you will get that flux per pole. And after the flux per pole comes your flux linkage of the coil at different positions. At different positions of the coil. Here, there was one question that somebody asked me. It is worth that I answer that again. Okay. Now, let me draw a set of flux lines like this. 1, 2, 3. For simplicity. Again, I'll say 1, 2, 3. This is the pattern. Okay, assume that all these are radial. My drawing is inaccurate. Assume all this is radial. I have not completed the lines. So, This is how the flux lines are at a given instant. Now I have a conductor. I have a conductor. This conductor is sitting here. The conductor is sitting here is what happening? That has got the maximum flux linkage. How do you say that is a maximum flux linkage? I take the line connecting these two. That is what is called as the face of the coil. It is what is called as the. So sometimes when the books define flux linkage, what they try to do is see how much flux is cutting the face of the coil. An n-turn coil is seen to have n faces. So it is n into 5. Okay. You have 1, 2, 3, 4 turns. Flux going through this. You multiply that by 4 to get your flux linkage. That is one understanding of what is flux linkage. But flux linkage is theoretically important because the law of induction says it is a rate of change of flux linkage is the induced EMF. It doesn't change rate of change of flux. Okay, you should know the significance of that. For the black coil, this is the flux linkage. Entire n into 5. Then let me take some other color. For the green coil, what is the flux linkage? Nothing. Why nothing? You take this line. None of the flux lines are crossing that. None of the flux lines are crossing that. Then let me take some other one. Which color I have not used? Purple. Let's say these two lines are not linking that. These two lines are not linking that. You understand? These two lines are left out. These two lines are left out. So that has a lower flux linkage. So what line I am considering now? I am considering the line joining these two. These two lines don't cut. Again, these two lines are not cutting. This is how you say. Clear? This is from flux to flux linkage. And flux linkage, d by dt of that is the induced EMF. Induced EMF has the same wave shape as the air gap flux density distribution. Correct? And from the induced EMF, there is generation, power goes out, comes in. And there is current in the armature. And that sets another magnetic field. And that magnetic field, if it leads the stator magnetic field, then that means the rotor magnetic field is leading the stator. That means it is a generator. The stator magnetic field is leading would mean it is a motor. Who is doing the work? That's what it decides. So all these are, and what happens in a DC machine is you have two magnetic fields, the stator and the rotor, that are normal to each other. The stator magnetic field is constant, as your IF is constant. The rotor magnetic field can vary because you vary IA, and the angle between them is 90 degrees. That's how you control. All right. Very interestingly, in a induction motor, you get a similar situation. What do we get? It's a revolving magnetic field. The revolving magnetic field. So the rotor conductors always see some flux moving past them. As long as the speed is not synchronous speed. At any speed other than the synchronous speed, they will see some flux lines moving past or moving the other way. When the flux lines are moving past, what will happen? There's a cutting of flux line. There is induced EMF. If there is induced EMF divided by the internal resistance is induced current. And they will produce some kind of sinusoidally distributed current. And therefore, they will produce certain magnetic field. And this magnetic field produced by the rotor, if it leads the stator, which will happen when in the supersynchronous case, that will become an induction generator. Normally, this will be lower. So the slip will be positive in an induction motor case. So the stator will lead the rotor magnetic field. So that is, they are at 90 degrees. And the rotor magnetic field strength varies because of variation in slip. Because of variation in slip. Okay. That's the other one. I'll do that. Okay. How do I give a 20-minute course on vector control? Can we go ahead? Can we go ahead? Anything interesting? Anything other than this? See, Yash wants me to say this. Can we go ahead? So these three-phase windings produce a revolving MMF. And how is the three-phase winding? What you have to imagine is when this figure is all very simplified. That is what I was trying to tell the story. What is not shown is this structure. This structure. And this R phase winding means R fellows are sitting here. And it is sinusoidally distributed. So that is what this R means. Okay. So this is super simplified picture. Many times you don't know what has all been abstracted there. Be careful about it. But given that, what I can say is theoretically, I can say I can have two windings, call it alpha and beta, carry certain currents I alpha and I beta, which can produce the same MMF, which can produce the same MMF revolving at the same speed. That is possible. That is possible. So this I alpha and I beta, go ahead and replace. So here there is current IR, there is current IY, there is current IB. These two are equivalent. Equivalent means they are equivalent, they are not identical. Okay. So this I alpha and I beta can be a representative of IR, IY, IB. Why? IR plus IY plus IB, they are three quantities, but they are not independent because they add to zero. There is an equation relating them. If the equation relating them, there are no three independent quantities. There are only two independent quantities. So they can be equivalently represented by this I alpha, I beta. Clear? This is what you call as space vector transformation. If you do the mathematics behind this, is the space vector transformation. So now, let me say there is this alpha axis, there is this beta axis. And I have my MMF here. Whatever is the revolving quantity is here. Okay. This is spinning at omega s. This is spinning at omega s. So if I bring in some fellow who is also spinning at synchronous frequency, this will be constant. This will look stationary. This will look stationary. Okay. So what I can do is I can put some other axis. Let's say I give some name. I can give some name to this. Let me say D or Q. Conventions can all change. Okay, hold on to the principles. This D axis itself spins at omega s, let us say. And there is a Q axis. And this Q axis also spins at omega s. Then what will happen? This will look stationary. There is a D axis component and there is zero Q axis component. I can choose any D and Q, D dash and Q dash, both of them revolving at omega s. If I make D overlap with this phi, there is D component is non-zero, Q component is zero. If I call this Q, then the Q component is non-zero, D component is zero. That is all. There's a multiple choice here. You can do anything. I never get into all that. So you get the idea of this. Now for this, let me define a transformation. This is the qualitative idea. Let me define a transformation. This is alpha, this is beta. And then this is D, and this is D will be spinning at omega s, and this is Q spinning at omega s. And the angle between the two is same phi. Why? They are quadruped with respect to each other. So I can write that. For example, if the D axis current, the D axis current can be written as I alpha cos phi plus this is then I beta cos 90 minus phi. So I beta sin phi. Then IQ is equal to, this is going to be I beta cos phi and I alpha or minus I alpha sin phi, just I alpha cos of 90 plus phi. That is minus I alpha sin phi. I can write this in a matrix form also. I can write this in a matrix form. That matrix is called the transformation matrix. So you can transform alpha beta into dq. The systematic way of looking at it. So it's clear? 3 phase into 2 phase, 2 phase into dq. Okay. Now I have a machine. I have a machine. Now the machine has a 3 phase current. And I'm going to take the 3 phase currents IR, IY, IB, IR, IY, IB, and I'm going to convert them into ID, IQ. This with phi being known to me. This with phi being known to me. And when I have this ID, IQ, this is my measurement. This is my measurement. So this is my feedback, and I can actually feed ID star and IQ star, the references. I can feed ID star and IQ star as the references, right? And this is the feedback coming from that. This can go to a controller. This can go to a controller. This is the current controller. Now, the current controller will produce certain voltage output. The voltage output, let us call that as VD star, VQ star. It will produce voltage outputs. Under any steady condition, the voltage outputs have to be non-zero. If the voltage output has to be non-zero, unless otherwise machine won't run. The VD star and VQ star is 0, means the 3 phase voltage is 0. Machine won't run, right? VD star, VQ star have to be non-zero. But the current error, what is the error? This is the error. The error should be 0. The error should be 0. Is it possible that the input to the box is 0, but the output to the box is non-zero? This is my controller. Is it possible? Yes. When you have infinite gain at DC. Infinite gain at DC. Is it possible to have infinite gain at DC? Yes, if you have an integrator. Integrator is 1 upon S. S tends to 0 or j omega. As omega tends to 0, it is infinity. So if you have a PI controller, the DC gain can be infinity. The DC gain should tend to infinity. And that is possible with a PI controller. This is a current controller. There is one for the D axis, and I'm not going into all the clarifications of this now. So I want to say, so what are you controlling? You are controlling 3 phase voltages or 3 phase currents. If you look at the 3 phase currents, the currents are at 50 hertz or 40 hertz or 25 hertz. Correct? If you want the current error to be 0 at that frequency, the gain of the controller at 50 hertz has to be infinity. If my current reference is 50 hertz, I want current tracking error to be 0. The gain of the controller at 50 hertz has to be infinity, and that is not possible. That is not possible. Because if you have an integrator, you can only get the infinite gain at DC, at no other frequency. So, if you manage to convert the 3 phase currents into DQ, you are doing the control at DC. So, you can have infinite gain. You can have infinite gain. And this is your VD star and VQ star, and you can go ahead. This is one point. Okay. And the next one, if you see what is what and how to go forward, depending on how you have arranged, depending on how you have, set up the notations, etc. You have set up the notations, etc. You will have IQ will have the meaning of torque. IQ could have the meaning of torque. So IQ star, which is essentially torque reference. IQ star will be essentially torque reference. So I will have plus and minus IQ here. And I will have a Q-axis current controller. I will have this is a current controller. So this current controller will give a voltage output. Now, if I have ID star is usually linked to flux, and this is plus, minus, this is ID, and this will give me another controller that will give me an output. Okay, this is at least a component of AD star. This ID star can be 0 if it is a PMSM, because you don't want any current to be injected in the D axis. Or ID star can be rated. You can say ID star will be 0 typically in PMSM. Why? Already there's a magnet doing the job. Please don't interfere with the magnet. That is the meaning here. And ID star can be correspond to rated flux if it is induction motor. Okay, that is how you get that now. Where you will get this IQ star, that is a torque reference. Who will set how much torque? That will come from the speed controller. If your speed is all right, you don't have to adjust your torque. If the speed is low, you have to increase your torque. If the speed is high, you have to reduce your torque. So the torque reference has to come from the speed controller. So this will be your speed controller. And this will have the speed reference, and this will have the actual speed, and this is the error. Okay, this is how the control loop will look like. The only other complication that you will have is, the only thing that you will have is, you write down the equations, right? This is the voltage equation generally for any coil. This is the voltage equation generally for any coil, IR plus d psi by dt. You have R phase coil, Y phase coil, B phase coil. But the flux linkage is a function of the same coil current and other coil currents also, because there is mutual also. So there is a lot of complication. The particular flux linkage of R phase stator winding can be influenced by not only R but Y and B, can also be influenced by the windings in the rotor. So to avoid those problems, you will go into alpha beta domain, where alpha and beta are 90 degrees with respect to each other. Alpha won't interfere with beta, beta won't interfere with alpha. Okay, so you say V alpha, I alpha, T psi alpha, and V beta is equal to I beta times R plus D psi beta by dt. They are fairly decoupled there. There are some things that will influence alpha, there some things will influence the beta. This there now. When you go to the other transformation that I saw, okay, the previous transformation, I'm worried about going back. No, don't do anything. Already Yash says within 20 minutes, complete vector control. Go to that other transformation. Here. This is I alpha cos phi. This is I beta sin phi. I alpha sin phi and I beta cos phi. What happens? There is a kind of a mixing up happens between the two. Certain kind of mixing up happens between the two. Okay. So that is what you call as a cross coupling. So let me write that down here. If I say VD, VD will have an IR drop. Agreed? That is fine with me. And there will be something called LD times DAD by DT. I agree. Plus, or it can be minus, depending on your convention. There will be some omega times psi q. There will be some omega times psi q. Similarly, VQ will have certain RIQ, all right, plus LQ DIQ by DT, all right, but minus R plus omega psi d. The last term in the right hand side is the problem. That is what is cross coupling. That is what is called cross coupling. Okay. So what I will do is, but I can calculate that. But I can calculate the cross coupling term at any given condition. If I sense appropriate quantities, I can make an estimate and I can calculate that. So if I'm able to calculate that, I think I should not be in a hurry to change slide. What I will do is, I'll say this is one component of VD star. I will calculate what is my cross coupling term. I'll calculate my cross coupling term, and this will be the what is called as feed forward compensation. So what is the feed forward compensation? I'll calculate the cross coupling term and I'll add or subtract accordingly. This will now become my VQ star. This will become my VQ star. Similarly, here also I will calculate the cross coupling term. I'll go for a feed forward compensation, and this will be my AD star. When you do that, there is no decoupling. There is no coupling between the D axis and Q axis, and this is decoupled control. So when you want to change the torque, only IQ star will change and only IQ will change. IQ star will change and it will correspondingly modify VQ star. And the system will not create any changes in the D axis. And when you want only the flux to change, it will change only the flux. It will not change the torque component. Okay, this is the decoupled control. It is like DC motor only. Very good. Yes, is right. Okay. Yes. Yes. Correct. IQ star and ID star. One will correspond to active power, another one will cover to reactive power. And here the torque component or IQ star comes from the speed controller. There the DC voltage controller. The DC voltage controller will give a particular component of what should be the active power. So the same thing can be flipped around. The same thing can be flipped around. In fact, there is a paper which was actually Professor V.T. Ranganathan's idea long back. It is called the vector control of high power, front end converter. It will have my name. I think JSS Prasad. Okay, you can note down the name. Okay, JSS Prasad is the author. JSS Prasad, and it will have my name, GN, and it will also have V.T. Ranganathan. Okay, you will have these names, and this is in a journal called Sadhana. This is in a journal called Sadhana. This title is something like vector control. This vector control of some three-phase something. You can search for this. This exactly does that. From that, it flips it around. How do you apply it to a grid connected converter? And does that. That is exactly how Professor V.T. Ranganathan used to teach and used to advise the industry on that. So that you can do this. Okay. So this is the controller. This is the controller. Plant also I should say something. Okay. Plant also I should say something. So let us say, what is a DC machine model? It's now going beyond that, right? So minus back EMF. What are we modeling? A DC machine. And the difference is 1 upon RA plus SLA. And this is what? That gives you your armature current. This gives you your armature current. If you multiply by torque, you will get torque developed. Then plus minus, you do your load torque and you do this J omega plus b 1, that is going to give you omega m. And omega m is related to back EMF. This is your plant model. This is your plant model for induction motor. Okay, DC motor. This also has one more, which we are normally not worried about. This minus IFRF, I'm writing it a little differently. 1 upon LF, and I'm going to integrate. Normally people don't do that, I will all do it myself. All right, I'm writing this equation. I wrote that using some Laplace. Here I'm writing it entirely in time domain. This is also part of the system. This is also part of the system. This is the dynamic model for DC machine. So what I will say now is, you can take this. If you look at this particular portion, that is electrical side, that relates the voltages with current, flux, whatever. This alone is an ideal electromechanical energy conversion. Ideal, there is no loss there. The losses have gone on the left side or on the right side. And this portion is a mechanical subsystem. This portion is a mechanical subsystem. Clear? Every machine can practically come into this bracket. Every machine can practically come into this bracket. So, if I take an induction motor and take that induction motor in the, let us say, in the DQ domain, or it can be anything else also, it doesn't matter. So, I can say VDVQ. This will give me what? ID, IQ, PSI-D, PSI-Q, etc. This is the electrical portion. Based on that, there is a torque developed. This depends on the physics of that machine. This will now change. And in this case, the torque developed here, it will be proportional to actually IQ, the Q-axis component. And from here, you will have the usual mechanical subsystem. Okay, this is one. Again, you have the electrical subsystem, there is a mechanical model, and this. This will also hold good for PMSM and many other machines. So finally, what you normally see is, I will write this as an electrical subsystem. And typically, there is speed or back EMF or speed, something will be like a disturbance input to this, and this will be currents and flux linkages. This will be the output of this. And based on that, there will be torque developed. This will change from machine to machine. This will change from machine to machine. This is where the torque equation, other things come. And then from here, minus TL and 1 upon J omega plus B, Js plus B. Okay, this will be your omega M. This is the plant model. This is a plant model. So the plant model for the current loop is only to control the current type. So the inner loop is current loop. So the plant model for the current loop is only this. And the variation in this will be ignored. That will be taken to be too slow. This is your plant model for the current controller design. Using this, you will design the current controller. After you have done that, the current control is designed. There is current control loop, followed by this will be the torque developed. But you don't need a separate controller usually, because if you control IQ, torque will take care. So that there is nothing for the torque. Then you will go for the speed controller. So there is the current loop, and then the torque block and the mechanical block. This will become the plant for speed controller. Okay, that's how you will go step by step from the inner to the outer. So that is in a nutshell, how do you do this kind of high dynamic control across machines. Thank you very much. Saved. He's now breathing. Okay, I think thanks for this. So we're just ending now. Just going to say thank you and end then. Anybody wants to say anything? That's the end. Of course, I've checked with you on what the second year, third year, fourth year wanted, right? So that I wanted to get onto that now. Does anybody want to say anything? Online people, are there any questions? If there are any questions and comments, we can take it from them. Yeah. And online audience, do you have any questions? Any questions or comments? You can either unmute and speak, or you can write it in the text box. Huh? Only two, no problem. Fine. Yeah. So just in case any questions. Yeah. All right. Fine. If there are any questions for online audience, please, unmute and speak, or just put it in the chat box. Okay. From you all, how is it? Everything okay? Good. So thanks for being there now. So is this going to create any impact on you? What kind of impact? Good to know. How many of you think that it's going to create some impact? Raise your hand. Very good. That's a very big number. So what kind of impact? Anything suggestive, indicative? Impact will be seen only as we go on. What kind of impact? What change? How to learn? Okay. How to learn what? Anything. That can include how to deal with people. Very good. Anything else? Yeah. Maybe pass on a mic quickly. Pass on a mic quickly. Battery is not there. Your mic is drained off, man. You guys have worked so hard that the mic is not able to stand. Go ahead.
Yeah, I mean,
the equation should not be taken for granted.
Yeah, equation should not be taken for granted. Like when, for example, we are in second year, third year, what we do is we learn the equation, we solve questions. That's what generally a student do. But it's not just limited to that. We should look where that equation is coming from.
Correct.
What is the theory behind that?
Correct.
That should be the main motive, the main concept.
Very right. So equations should not be memorized and blindly applied. The minimum you should know the applicability of the equation. You should know where is it applicable, when it is applicable, at what range. Nothing is applicable universally. As I said, even the celebrated Newton's laws of physics are not valid under the quantum condition. When the masses are very small and the speeds are very high, it is not valid. It's not that Newton was wrong, but everything has its validity. That is something that you have to. And not just that, that is the minimum. You have to see where from it comes. And if you can derive that yourself, that's very good. Most of what you are dealing with in your basic subjects, you should derive them. You should really derive them, work from the fundamentals and come that. And sometimes you will see that there is no single way to derive. There are actually even multiple ways to derive. Okay. So remove black boxes to the extent possible from your basic lessons. You will have to deal with black boxes in life. There's nothing can be done. Certain things have to be taken, but not at this stage. Okay. That's very good. Yeah. Anything else? The microphone will come to you. Yeah. Somebody just raise your hand. We'll pass on the microphone. Quick. You don't. Give to Raghavendra.
With this workshop, we are able to see bigger things with a very known, for example, how mission is we should able to see with the magnetic circuit. So when we analyzing the mission or something, like previously we have done some analysis based on the, if you take the diode or something, we are seeing like a switch only, like uncontrollable switch only. But what exactly happened inside, how electric field affecting on that actual, everything is now it is insideable. So if you are doing some hardware things also, we are able to find out the problem, like how it will be gone, how we will rectify these things, like, so it's more practicality with from the basics.
Correct. It is more relating to the basic. Yeah, correct. So I'll just add one point. The practical implementation is yet another dimension. The practical implementation is yet another dimension. The workshop is not really at that level. Yeah, time permitted, I would have shown what kind of exercises are given to IISc, but some other time I can do that. Okay, you have to develop that. Converting any circuit into a real life circuit, from paper into real life, there is a challenge, there is learning. You should not shy away from that. You should do that, and that by doing is how you can learn that. You can start with simple electronic circuits on circuit board, and then simple power supplies and circuits on general purpose PCB, and go on to decide advanced ones with PCB. And there are many active researchers. God's grace, we have got very good funding also, so there is no problem. So I was telling a number of people where to do, how to do that. The time to do that in the engineering curriculum is during your projects. That is when you can practically implement something. Historically, over decades, the projects have been a very, very important component of BE BTech programs. Unfortunately, in the last 1 or 2 decades, they have lost their importance. Mostly the students. It closed because students didn't do. And the professors keep asking, then they come, they don't come. Why they don't do? Many times, 7th semester, they will either get a PhD admission or they'll get a job. Either way, they say they're not interested in that. So please understand that your higher studies that is guaranteed when you have come to a place like an NIT. You have crossed JE and you have come here. You are guaranteed to get a job. Whether you get a job or not, or what kind of job, should not hamper your performance in 7th and 8th semester. And it's a very, very valuable opportunity. Execute projects. Do that. Particularly in power electronics, unless you build anything, nothing is worthwhile. Because the non-idealities that I cannot model, I cannot discuss will kill your circuit. Okay? You have to deal with that. So I would very, very strongly encourage that. So whenever there is an opportunity, maybe there's a mini project in 3rd year, do it well. And the final year BTech project, please do it well. Okay? If I can help from wherever I am, please do reach out to me. MTech projects, 1 year. Make sure that at the end of the MTech project, you are a very good design and development engineer. You are very familiar with data sheets of different components. You are familiar with assembly layout practices. You are familiar with testing procedures, right? Minimum, make sure that you are a very good design and development engineer. So, okay, please take that as your goal. Doing the project itself is only one part of that. The complete goal should be that you should become a good design and development engineer. That's what enables to do your research, right? And as a byproduct, whatever power supply you wanted, something that should come. Okay, that's something that I wanted. Yeah, he had something to say. Go ahead.
Sir, of course, the teaching content that has been covered here has been excellent. It has helped us identify a lot of gaps in our understanding. But more than that, I would like to comment on the teaching technique that is used by you. We have learned a lot on how to teach, more than about how to learn. This is amazing. Like, it was a new, eye-opening thing for me. So thank you for that. And your energy is amazing. Thank you for that.
Okay, thank you. What was that teaching technique you said? What is
just the way you used to start with a topic from the absolute basics and the concept behind it, how the most basic component of an electrical, that is electron, how it flows. Then from there, what effect it creates. And then from there, we get a graph. And from there, we get the equation. The flow was, nobody has taught us like that, taught us in that way before. So that was really amazing.
Okay, thank you. And good to know it like that. Yeah, Kriti wants.
Thank you, sir, for giving us the lecture. Like, starting from the question, what is electronics? We have come this far. Like, what I have understood is in these 3 days, you have just concluded the whole, most of the major subjects of the electrical engineering, right from the basics in a very short time. Like, you have made us question each and everything, right? Be it power electronics, be it machine, everything. You have made us visualize and visualize everything. Like, question, as sir said, right, from the basics we have started with the question what is electronics, and we have ended up here till machine. So it was a very fruitful for us that we have given a different picture since we are in 4th year now. So this was the first time like we have been exposed to this kind of concepts, like, okay, we can understand this thing, concepts and everything in this way also. So thank you so much, sir, for that. And also, sir, your energy is extremely, we should give a big round of applause for sir, because 3 days, 9 to 6, standing and delivering the lecture continuously is not easy, because we are sitting here, then also we are yawning and feeling less energetic. But
Because you're sitting, you're yawning.
thank you, sir, for that.
He says you should be energetic. And the other side of the story, if you ask my wife, she'll tell you how tired I am later in the night, what other issues I have. Don't get into that. Have only this energy part of it. Good luck to you. Thank you. Yeah. Anybody else? Somebody wanted? Yeah, somebody wants it here, reaching out here. Yeah. Yeah.
Sir, thank you, sir. I was very interested in the major electronics part. Like while you were explaining about the major power system, power electronics part, and I was able to understand it. So we can learn it, but I was very lazy while understanding this part. So this was a major issue, sir. While you are explaining the each and every part in a detailed way. And how can you apply the electronic components to make a power circuit using the MOSFET and
very good. Okay. Thank you very much. Yeah, somebody was asking. Yeah.
Good evening, sir. I am also a PhD first year. Right now, my coursework is doing. I am also working under Dr. Amol Rahulkar, sir, and Dr. Das, sir. So for that, actually, my project is related to BLDC motor. So it is very helpful for me to your workshop is very helpful for me.
So I would strongly suggest that you are now in your first year, right? I would strongly suggest that you start doing practical exercises that will help you with that. Okay. So I can send you a set of exercises on electronics, which will use op amps and gates and things like that, more analog and a little bit of digital electronics. Each experiment is, will take just like 2-3 hours for you to finish, one afternoon, let us say. So what you can do is, there's a lot of instructions in them. The very first section will be a simplified analysis. It will be a simple amplifier circuit. The simplified idealized analysis will be one section. Next, it will talk about the different non-idealities. How will you deal with them, compensate them, and whether there is any input resistance and what do you mean by that, how can you measure that. Okay, everything will have some 7-8 sections. You should do the homework, and then finally the last 2 sections you will come and assemble, take your readings and do that. Okay.
Yes.
So you'll need about, if you prepare one night and the next morning, afternoon, you will be able to do this. So you should complete one exercise at a day, and that will be about 10-12. So you should do that in 2 weeks' time. That is the electronics with only breadboard. Then I can share another set of exercises with you through Professor Das, right? Yes. That would be building power electronic circuits. Okay, that's about another 10-12. That can take a little longer for you because of assembly and other things like that. But I would strongly encourage that you do those. Yes. So this would be for, let's say, 2 weeks, and that could be for about 3 or 4 weeks. If you set aside, let us say, about 1.5 months, 2 months in summer, and make sure that these are all done, then you will have necessary background. So you will have a lot of hardware skills, and you will have the concepts, many things, and related to what you need to apply, etc. Okay, every exercise will have homework. You will have to done a few hours of homework before you start the experiment, and then the experiment, and then there is any troubleshooting something till the end now. Yes. That's something I will very, very strongly suggest. I will suggest this to almost all the research scholars who are starting. I will also suggest this to MTech project students who are starting. This helped in many places. At IISc, it's a regular one. It's being done. One is part of a course, another one was also part of a course. At NIT Trichy, people have tried this. At BNIT Nagpur, they have tried this. Okay, so that's something that I can share with you through Professor Das. Okay. You just send me a mail copying him. I'll send that to you. Okay, I strongly recommend that.
Okay, thank you, sir.
Sure. I think she wanted, no? Yeah. No, the girl next to you. Okay, somebody was there. Okay, anybody else? Rajan.
Yeah, so physics has always been my favorite subject, and the way you approach everything with the electric field and vector analysis, so it helped me a lot in understanding everything. And really, like, I will say thanks a lot to you, sir.
Welcome.
And sir, like in 11th, 12th, we read a book, H.C. Verma, for understanding physics. So is there any book to understanding the basics of like machines? Like that book was example using of our day-to-day life. So any book which is developed in Indian ecosystem on developed on Indian ecosystem, which can help which can illustrate everything with the Indian mindset.
In physics, what is Indian mindset?
No,
No, but what is that you want from me?
like for physics we were having two textbooks. One is I. Rodo and one was H.C. Verma.
Okay.
So H.C. Verma was explaining everything with the Indian examples.
Okay. What do you mean by Indian example? Says that in Indian example is falling.
Yeah, he was explaining SHM using those
dosa.
No, monkeys and that one was there. One typical example was there. That
But you have no grown up, no? Whether any example Indian is given, European is given, you should be able to learn now, right? As a child, I can understand.
Yeah.
You have to say, this is what your brother does, why don't you do?
Yeah, is there any book which can
I don't know, book for what? That's what I'm
for mainly electrical machines?
See, whatever I taught, dealt with, I myself have read very few books. You may be surprised. Because I believe that if you read, you have to read something in depth and you have to understand. That is more important. It's not that you go on reading hundreds of stuff. That's not what it is. I myself have read very countable number of books, and chapters, etc., etc. It's not that I've read 20 books, etc. Most of these are, when you read, you have to try to understand. Okay, that's one thing that I would like to say. And typically, few books will help is what is my situation. For all electronic, I would say Cedra and Smith is very good. Cedra and Smith is very good. The gap in Cedra and Smith I found is what I tried to bridge. That is electric field. Okay, the charge density to electric field to the final voltage is being skipped and it is jumping into that. So that is what I'll recommend. And I'll recommend any electrostatics book which talks about this Gauss theorem, these basics that I covered with. So the basic magnetostatics and electrostatics from any electromagnetism book, right? That is my second recommendation. The third book I would recommend is Fitzgerald and Kingsley. Fitzgerald and Kingsley. I would recommend that you read Fitzgerald and Kingsley's one chapter 4 or so, something on where it talks about a wide view machines and induction motor, the squirrel cage rotor. It said that. So the closest I would say is Fitzgerald and Kingsley. Okay. It's a little terse, but with this background, you will be able to understand that. Okay. The only other book which is not a published book that I know is very good in this kind of a thing is my Professor V.T. Ranganathan's class notes. Okay. If you want, I'll have that. I'll send that to you. It is not a book, but that's a class notes that he used to do that. That is something that talks about PLDC, PMSM, right? Vector control, how do you model, etc. So if that is really at a level where I think, what's your name now? I'm so, yes. So now see, I'm forgetting that. That's the level of my energy at this point. So that's one. So I would have very few suggestions in this kind of thing. Okay, but these are all very good suggestions from my point of view. You can actually pick up Cedra and Smith and read the chapters. They'll make sense to you. You pick up magnetostatics and electrostatics in an electromagnetism and read that to you. Okay, I strongly urge everyone, particularly the BTech students, second year, third year, and all that. It will be very useful for your gate. It will be useful for you to handle anything, like in your interviews and other things, and you're able to connect and in your work, right? So I would strongly recommend that too. And certainly Fitzgerald and Kingsley for machines. Okay, these are, I would say, standard recommendation any day. Yeah.
Okay, thank you, sir.
Thank you. So stay in touch and anybody can reach me out. You can always send me an email for any further discussion. I'm just curious. Is it possible to keep a tag from now and see what changes have occurred or anything happened there? Is it possible? Or how is it possible? Are you going to do something here and say, oh yeah, it's good, and go back to business as usual, or something is going to change? What's going to change? Is the question valid? What's going to change? No. Yeah, good. You don't need permission to take your mic. Yeah.
So thank you, sir, first. So what we can see that the perspective can be changed from this point. Like if you are seeing anything, you can question why it is, how it is, and why it is not getting changed in other forms. That three things can help pretty much for understanding any problems in electricals. And I'm also trying for my PhD also. So same way I'm also thinking. So that is I can follow regularly from that. Previously it is like simply like follow, sometimes reverse back, but now it's I have to do like that way only.
Very nice, very nice. Well, I'll have a few things, okay, where it can be measurable and seeable. I would strongly encourage the PhD scholars and the MTech project students to carry out these hands-on exercises that I suggested. Okay, that's one thing that I'll look forward. That's doable. I'll share it with him, and you can do that, and you can prepare a report, and when we can catch up, we can catch up. That is one. Okay, and how many of you are doing your BTech projects now? Raise your hands. Right? So can we expect very good outcome from your BTech projects? Can we expect good outcomes from your BTech project? Yes? Yes? That should be one. That should be one. Are there any BTech mini projects in the third year? How many of you are doing? Can we expect better outcomes from this? Huh? Okay. This third and fourth, I'll check up with your HOD. You should report to your HOD on what is your progress. We do that. And I can have a remote meeting with you. The fourth year students, one meeting. Third year students, I can have a separate meeting. And with the MTech or the PhD students, I can have a separate meeting on that. Okay. Are these three implementable? Very good. I can talk to some faculty on how certain things can be done with you on the machine. And you are also dealing with machine there in Go. Huh? Oh, but you said no. You said only power electronics. Okay. So anything the faculty are interested, we can always have and see how it can be done. There can be other. I've already said that both electromagnetism and electronic devices, I wanted this, and machines, you already know what has been that. So that's the next request now. Okay. And you all have a standing invitation from me to visit IISc. Okay. Whenever you are interested as a group, small group, big group, please let me know. Let me know reasonably in advance. Okay. So we can do that, but we may not be able to arrange hostel or accommodation now. That's very strict, this thing. But you can always come for a few hours, first visit and go. And some of you are interested, you can come and, maybe for 2-3 days also you can. If there is something that is clearly interesting to you, you can probably spend for 2 or 3 days and learn something better. So that's something that also I'll invite you for that. Okay. So thank you very much. And thank you all for staying here for the third day until now. So good luck to you all.